need to publish less.
Should we start?
Yeah, we are ready. Prabha is also logged in. How are you?
So, hello, everyone. I'm good, sir. How are you?
Yeah, we can start.
Yes, sir. Hello, everyone. Welcome to the day 5th of QFA 2021, and Professor Prasanta K. Panigiri will be chairing today's first session. I request Professor Panigiri to start the session.
So, thank you, Diksha. So today we have 4 talks in this session, extending up to 4:30. The first term is by Professor Prabha Mandayam. Prabha is very well known to this community, and she has a very nice career. PhD with John Preskill, very good. Not have to mention his name twice. Then had a short tenure in Chennai Mathematical Institute and Institute of Mathematical Sciences before she moved on to IIT Madras to the physics department. Now, as you might have seen, IIT Madras is a very active group of people and provides one of them. Her main interest is error correction and using quantum information as a tool to explore fundamental questions in theoretical physics. So, now I think 40 plus 10, 40 minutes per talk, 10 minutes maybe for discussions. Yeah, now you can start. Yeah.
Thank you very much, Professor Prashanta, for that very kind introduction. I really apologize if you hear the background noise. I hope WebEx is cutting it out, but anyway, let me share content and see if it works out. So, are you able to see my screen?
Yeah, we are able to see.
Okay.
Yeah.
And let me just try to make it full screen. Okay. Is this good? You're able to see it full screen now?
Yeah, we are able to see full screen. Please go ahead. Yes.
Okay. All right. Well, thank you to Professor Shubhashish and other, Professor Shubhashish and other organizers at IIT Jodhpur. Thank you for inviting me to present my work. I'm very happy to be a participant and also to attend this conference. It has been a very interesting and exciting program for the last 4 days. I wish we could have had this in person and one would have had the opportunity to visit the Jodhpur campus in person, but times are such that we do this online. But anyway, it's good to be here. So I'm going to today talk about some recent work. Unfortunately, I did not put the archive reference here, but it comes on a later slide, on achieving fault tolerance against amplitude damping noise. Okay, so this is joint work, I should mention, with Akshaya, who was my PhD student here at IIT Madras, and Long, who is a graduate student at Singapore, and my long-term collaborator, Hui Kuhn, who's also part of CQT Singapore and Yale and US College. Okay, so since I have only 40 minutes and I might have packed it tight, so let's move on to talk about what is this talk about? So I will first motivate the need for, very briefly, because I think it is nobody's case that quantum error correction and fault tolerance are very important challenges today in quantum computation. I will just motivate the need for, or rather talk about the challenges involved in developing quantum error correcting schemes and fault tolerance schemes in today's so-called NISQ era, which is the noisy intermediate scale quantum devices era. And then I will also motivate the need to go beyond Pauli noise. I will mention what I mean by Pauli noise. And then I will jump right into our work, which is about developing universal fault-tolerant circuits for a kind of non-Pauli noise model, which is the amplitude damping noise model, using a specific code called the 4-qubit code. I will also highlight one of the interesting insights that comes from our work, which is the need to identify noise structure preserving gates. So the idea is, normally when one talks about fault tolerant quantum computation, the idea is to construct encoded quantum gates, which is quantum gates which are going to work on the encoded state, right? But it is not what we observe, at least, is that if you have a specific noise model in mind, which is a non-Pauli, particularly a non-Pauli noise model, then not every gate is amenable to fault tolerance, even though gates may satisfy a nice property called transversality, which is sort of the holy grail of standard fault tolerance. So even though gates may be transversal, the idea will become clear hopefully in later slides, that is not sufficient. You really have to identify gates which have a certain invariant structure under the particular noise under question, right? So we make this interesting observation, and I just wanted to highlight this, and I will again revisit this towards the end. And then I will also present what is called a fault tolerant threshold estimate and briefly discuss what this entails for the future. Okay, so, well, the need for quantum error correction. Today we are, as is often mentioned, we are in an era of noisy intermediate scale devices. We have various groups and companies showcasing devices which have, say, 50 to 100 qubits. But as we are encountering this regime where, in the last 5 years, there was a dramatic shift. We went from having barely a handful of qubits to today we have about 100 qubits, then we're really seeing the effect of noise come into play now, right? And the key challenge that confronts scalability of these quantum processors is noise, right? And this is noise not just in the quantum bits, but also in the quantum gates, right? So the gates are also noisy. The bits themselves undergo decoherence. And both of these pose a serious challenge to realizing the potential of these quantum processors, right? And our hope is that ideas from quantum error correction are going to help us resolve this challenge, help us overcome this challenge, and guide us towards scalable and robust quantum computers, right? So what is this decoherence that affects our quantum bits? This is very simply the loss of coherence due to uncontrollable and unwanted interactions of the quantum system with a bath or an environment, right? And this is what we often refer to as noise. The full framework of decoherence, of course, forms a study of open quantum systems, where we study how a given system bath interaction can lead to a particular decoherence process. I would just like to mention one example of this, which is what I will repeatedly invoke in this talk, which is the energy dissipation in a two-level system. You can think of this as spontaneous decay. You can think of this as population decay. But the key idea is that you have this two-level system. It could be an artificial two-level atom. It could be the two levels of an ion trap. It could just be a two-level atom, right? And this forms our quantum bit. And this is sitting inside a cavity, and it, of course, interacts with the cavity modes. And when it interacts with the cavity modes, hopefully many of us know here what the Jaynes-Cummings interaction model is. I'm not going to get into the details, but if there are students here, then I just put this here as a kind of reference. One can study this system bath interaction using this Jaynes-Cummings model. And if we then trace out the bath or the environment, which is essentially the cavity modes here, then the evolution of the system state alone is described by not by a unitary evolution, because the system alone no longer evolves unitarily, right? The Jaynes-Cummings interaction, which leads to a unitary evolution, is a unitary evolution of this two-level atom plus the cavity modes. The two-level atom in itself does not undergo unitary evolution, rather it undergoes a kind of dissipative evolution. And this is what is modeled by a quantum channel, right? And in this particular case, if we make certain approximations and restrict ourselves to a single, to the single photon sector, right? The zero or the single photon sector in the radiation field, because we have this two-level system and the only modes that come into play are the vacuum and the single photon state, then this leads to what is called the amplitude damping channel. This is often in the literature referred to as a T1 process. It's a well-studied model and a well-studied process. And the action of this channel on the standard basis, right? This is the 0-1 basis, can be expressed in terms of two matrices. And these are the so-called Krauss operators that we associate with any quantum channel. And this sometimes they're also referred to as noise operators. And these, this is the description of these two noise operators. So you see that there is this parameter gamma here, which denotes the probability of transition of this two-level atom from the excited state to the ground state. And corresponding to this gamma here, there is a square root 1 minus gamma term here, which kind of damps the one state, right? So if you observe a photon here, then you know that the E1 operator has occurred because the photon comes out because of this decay here. I hope you can see my pointer, right? So the photon escapes out because of this decay here. But if you do not see the photon, then you know that this decay has not happened, which means with high probability you are in this zero state, right? So that kind of damps the one state, the probability of seeing the one state, right? So that's what these two matrices are about. Note that this gamma itself is a function of time, right? And typically, if you solve this Jaynes-Cummings model under some reasonable assumptions, you'll see that this gamma actually decays as an exponential in t, right? So at t is equal to 0, right? I don't know whether I wrote this right. Yeah, indeed. So at t is equal to 0, you simply have the state that you prepared, right? But as you tend towards this time t1, right, which is indeed called the coherence time, then you see that with high probability, your excited state would have decayed to the ground state by release with the escape of a photon, right? So this gamma is a function of time, which comes by solving these master equations or the time evolution equations, taking into account this interaction. And this T1 is what is often called the coherence time, right? So okay, so just to complete this picture and to introduce some other words here, this map, you know, how density operators of the state itself evolve can be represented like this. In terms of these two operators, it's what's called an operator sum representation. And this map itself is what is called a completely positive trace preserving map. And the common terminology for this is that it's what's called a quantum channel, right? In this particular case, what I've described is the so-called amplitude damping channel. Just to give a sense of what these coherence times are like, I've just put in a slide here. This might be somewhat dated, but this tells you what, this is a different coherence time I must mention. This is what's called the T2 time, which comes from a phase damping noise. And these coherence times, as you can see, we evolved from being around nanoseconds, right? Because this is 0.001 microseconds. To today, we are at about 1,000 microseconds, right? So we have steadily seen an improvement of these coherence times. And of course, this coherence time is a measure of the amount of time that you can preserve a superposition state, for example. And so the amount of time that you have to do gate operations on the qubit before the information in the qubit is completely lost, right? So, but still, as you can see, we are very far from a state where we can actually do, say, thousands of gate operations, which is what ideally is required to be able to do a large enough computation like a factoring algorithm, for example. Okay, so this kind of motivates the need to be able to improve this coherence time, other techniques to improve this coherence time, other than what we do as experimentalists or via engineering the systems cleverly in the lab. So quantum error correction provides a way to do this. And what quantum error correction says is that you encode that instead of talking about a single qubit, instead of talking about a single two-level atom, you think of a collective state of, let's say, 4 qubits. Right, so introduce some redundancy in the picture, and instead of doing information processing with single qubits or the so-called bare qubits, you do information processing on logical qubits, right? So that's what this subscript L here denotes. That's a logical qubit, where these logical qubits are now states of multiple qubits. In this particular case, what I want to describe is storing the information into 4 qubits, right? Storing a single qubit worth of information into 4 qubits. And in particular, the 4 qubit space, of course, is a 16-dimensional space. We choose a particular 2-dimensional subspace of this 16-dimensional space, right? Because we are interested in storing a physical qubit into this logical space of 16 qubits, right? And so we end up with this 2-dimensional subspace. This code, of course, goes back a long way to this pioneering work of Debbie Lung and Yamamoto and others. So, and in fact, this code was designed particularly to address the issue of the T1 process, or the amplitude damping noise, right? And I will describe the code properties in greater detail, but just note that both the 0 logical state and the 1 logical state are entangled 4 qubit states, right? And this encoding can happen via an isometry. For example, here is a circuit that does this encoding, right? And of course, this encoding involves various non-local gates, namely these C naughts here. So this is exactly how the encoding process circumvents the no cloning theorem, because if I simply say introduce redundancy, you cannot simply make copies of arbitrary states in your computation, right? So you need a way of doing this in a way that overcomes the challenge posed by the no cloning theorem. And so this is done by using these additional 3 qubits, which are the ancilla qubits. And note in particular that this particular encoding circuit requires you to prepare a plus state, right? And then you have these 2 0 ancilla states. And of course, it involves entangling unitaries in the form of these C naughts, right? It can be shown that under the action of this amplitude damping noise, the single qubit errors can actually be distinguished using this 4 qubit code, right? So when we say that such a code is actually successful in protecting against certain errors, if it can actually distinguish or detect the action of these errors, and hence, provide us a way to correct for the errors. So the first step is error detection, and the second step is error correction, and we'll see this breakdown in subsequent slides. It turns out that in this case, the errors can be detected and corrected up to order gamma squared, where remember gamma was the noise parameter of the amplitude damping noise. And if this gamma is small enough, in fact, if gamma is less than 0.5, we can actually show that this code improves the coherence time. And the way we estimate how well a code performs is using what is called the fidelity, right? So typically, what I've just described is a quantum error correcting code. It is characterized by a code subspace and a corresponding recovery map. I still haven't told you what the recovery map is in this case, and I will come to it in a few slides. And the performance of a code is benchmarked by this measure called the worst case fidelity. It's basically an overlap between the action of the code, the noise, and the decoder. So remember, this is a composite map. E is the noise, R is the recovery map. And it's simply the overlap of this, of the action of this with the original state. And ideally, we would like the error correcting procedure to guarantee us some kind of worst case fidelity, right? That every state in the code space is preserved with a certain fidelity. And that's what this worst case measure actually does. It's a minimization over all states in the code space. So just to give you a sense of why error correction is useful, under this kind of amplitude damping noise, if I had a bare qubit, which was unencoded, a single qubit, then the fidelity function here, there is no recovery in that case, right? It's simply the noise. One can easily show that this fidelity function actually decays as 1 minus gamma, right? It's a linear fall in gamma. On the other hand, if I use a 4 qubit code, and then I ask what is the, and I use this recovery, and then I say what is this fidelity, what is this worst case fidelity, then one can show that this actually goes as a quadratic in gamma. So what we have done is we have improved the fidelity up to order gamma. And hence, if gamma is small enough, you have essentially improved the coherence time of this qubit by doing this encoding and decoding procedure. So this is the sort of goal of error correction, that you would like to preserve quantum states by making reasonable assumptions about the noise. You would like to identify what is a good code space, what is a good recovery, and so on, right? Now, there are a few other challenges, right? This was the sort of abstract framework of error correction in some sense. That's what the previous slide told us. Now, what are some practical challenges here? Well, a continuum of different errors can occur on a single qubit. So unlike in the case of classical error correction, where once you have this framework of encoding and decoding and so on, then a huge part of the challenge is already solved because there are exactly two noise models. The classical bit can either get erased or it can get flipped, right? A bit flip or erasure. These are the only two noise models that one has to worry about. But in the quantum case, of course, any completely positive trace preserving map is a valid quantum channel, right? And it may vary from architecture to architecture what exactly the fundamental noise model of that system is. What is the fundamental decoherence process of that particular qubit system, right? So you could have, there are all these well-studied models, erasure, phase flip, amplitude damping, depolarizing, etc., right? So the standard approach of what we call standard quantum error correction aims to discretize this continuum of errors into a finite set of unitary errors. And of course, the Pauli basis provides us a natural way to do this, that you break down any error model on your qubit in terms of the X, Y, Z, and identity, right? And because this forms a basis, it's a natural, what's called a unitary error basis, right? And so if you construct or develop error correcting machinery basically for these Pauli errors, then by linearity, you would have an error correcting machinery for any arbitrary single qubit noise. And this observation leads us to this beautiful structure of stabilizer codes and so on, which I'm not going to delve into in this talk, right? This is the standard, what I would call the standard framework of error correction, is to break down arbitrary noise in terms of Pauli noise and then correct for it. So when I say Pauli noise, I mean noise models which naturally have a Pauli breakdown, right? Noise models which naturally have a Pauli breakdown are, for example, bit flip noise, which is simply identity or X, phase flip, which is simply identity or sigma Z, depolarizing, which is some combination of identity X, Y, and Z. These are all what we think of as Pauli noise models because the noise operators or the Krauss operators are themselves simply Pauli operators. But if you go back and look at something like amplitude damping, whose Krauss operators or noise operators I wrote down here, you stare at it a bit and you realize that this actually cannot be expressed simply as a scaled Pauli, right? This will have to be written as a linear combination of two Paulis. In fact, the first operator can be written as a combination of identity and sigma Z, and the second operator can be written as a combination of sigma X and sigma Y. And I will show this in subsequent slides. So this is what I would refer to as a non-Pauli noise model, because it's not natural for this model to think of it in terms of the Pauli errors. That is a sort of artificial decomposition that we do in order to fit it into the framework of standard error correction, right? So if one sticks to the standard framework, then it turns out that the shortest error correcting code actually requires 5 qubits to protect against arbitrary errors on a single qubit. So if one sticks to the standard framework of breaking down the error operators into Paulis, you cannot find a single qubit error correcting code which uses less than 5 qubits. But then, of course, I just showed you a 4 qubit code and I claimed that it can actually correct for single qubit damping errors perfectly because it removes completely the order gamma term in the fidelity, right? Remember, the order gamma term is like the single qubit error, the single qubit damping error, right? So what is happening? Well, the point is, if you were to break down your noise into Paulis, it seems that you may lose out. You may lose out in terms of the resource requirement for certain noise models, particularly these kind of non-Pauli noise models like amplitude damping, right? So what we have in the case of amplitude damping is actually a shorter code which offers as much fidelity or almost as much fidelity as the regular 5 qubit stabilizer code, because this also protects up to order gamma squared, right? So of course, one research program is to then look at these kind of non-Pauli noise models and ask, are there such good quantum codes, tailor-made quantum codes, which will help us to implement these codes with fewer resource constraint, right? But then error correction is just one part of the story. And now we come to the next part of the story, which involves fault tolerance, right? So I'm going to take a brief pause here. If there are any questions, please go ahead. Okay, so if there are no questions, then let me proceed. So remember the circuit that I showed you for the encoding of the 4-qubit code.
Hello, Prabha.
Yeah.
Hi, this is Baladitya. So
Hi,
I have
Bala.
a quick question. Hi.
Yeah.
So just to understand the terminology, so you are calling amplitude as so in your model, the amplitude damping is a scaled superposition of Pauli errors, right? Is that
I will write it. I will eventually write it as a linear combination of Pauli's, a convex linear combination.
a convex linear combination of
Yes.
Pauli's? Okay.
Yes.
Okay.
Yes.
So
Yes.
okay, got it. Thanks. Yeah, just to
Yeah,
clarify.
sure. Yeah, sure. Yeah. So the idea is that every noise can, of course, be written as convex linear combination of Pauli's. Every noise operator on a qubit. But the argument I'm making is that in doing so, and in viewing this as in the standard error correction framework, one seems to be losing out in terms of resources. That you require additional resources actually in order to implement such error correcting codes. Okay, so moving on to the next idea, this circuit that I showed you here works well, or this error correction procedure which I mentioned here works well, assuming that these gate operations are all ideal, right? It assumes that the C0 does exactly what it is supposed to do. It assumes that this ancilla qubit 0 is a perfect 0. It assumes that this ancilla qubit plus can be prepared perfectly in the state plus, and so on and so forth, right? And the decoding also assumes that your measurements are perfect and so on, right? But in practice, of course, this is not the case. So the theory of fault tolerance basically tries to address this next level issue of, all right, you have a procedure now to deal with this noise, but is this procedure implementable when you have faulty operations, right? So how effective really are these quantum error correcting protocols if you have faulty gates, faulty preparations and measurements, right? For example, it's possible that you actually may do better with just a bare qubit because the complexity of implementing these 4 different C0s and the complexity of preparing the plus state and so on, so not so much the complexity, but the fidelity with which you can do all of that simply kills the procedure, right? And if there's any students here who have, or any of you here who's actually implemented an error correcting protocol on, let's say, one of the IBM Q processors, you will see that indeed these gates are all extremely noisy, and the encoding, you actually lose out a big chunk of fidelity even in the very encoding process. And if you then pile on more and more qubits and try to do a 5-qubit or a 7-qubit code, they only involve even more gate operations, right? So the theory of fault tolerance basically addresses this issue and says, here is a threshold, right? Here is an estimate of when this quantum error correcting protocol is actually effective. But then there are several steps that go into even making the protocol effective against faulty gates and faulty measurements and preparations. So the idea of quantum fault tolerance is to allow for reliable computation, not just with noisy quantum gates, but also with faulty quantum gates. Of course, this is not possible arbitrarily, but this is possible provided the noise is below a certain threshold value. And this is the term fault tolerance threshold that you often hear spoken about in various contexts, right? So what is the broad framework of fault tolerant computation? So once we have done this encoding, right, and once we have this error correction procedure, then you would imagine that every gate operation in your quantum computation is going to be simulated now by an encoded operation, right? So what was simply a gate G on an arbitrary qubit state alpha 0 plus beta 1 now becomes an encoded gate operation on this logical qubit alpha 0L plus beta 1L, right? So the bar on top is to denote that this is now an encoded gate operation or a logical gate operation, right? Now the key idea or the key challenge in in developing a fault tolerance scheme is to show that these encoded gate operations can now be done in a way that that controls the spread of errors, right? So what does one mean by the spread of errors? So for example, if you go back and imagine that encoding circuit that I showed you, which had all these C naughts, then you know that the C naught is a gate that acts on 2 qubits at once, so to speak, right? It's a gate that couples 2 qubits. So if there was a fault at, say, the qubit before the control, right, at one of these control locations. So let me just show you quickly the circuit again. So if there was a fault here, just before this C naught acts at the control, then it seems somewhat intuitive that that fault or that error is going to propagate down to the target as well, right? And what is more, there is now an error in both these locations, in both these qubits. And then there are further gate operations being done because this is just the encoding step, right? And so these errors are now very likely to propagate through the circuit. And it can happen that these errors can propagate in what is called a catastrophic way, right? In a way that your error correcting code cannot deal with it. So the key challenge in fault tolerance is to be able to implement such operations, the encoded operation, in a manner that, for example, this is just the encoding circuit, but then now imagine I want to do a C naught with the encoded qubits, right? How do I do that C naught in a way that the errors do not propagate in a catastrophic way, that my errors are still within a number or a regime that is tolerated by the error correcting code that one is using, right? So that's a key challenge of quantum fault tolerance. And in order to do this, these encoded operations are implemented by somewhat composite circuits, right? And these circuits are often called gadgets in the parlance of fault tolerance. These gadgets are constructed out of elementary physical operations. So when one says elementary physical operations, they are assumed to be noisy. So you have a noisy C naught at the first level, right? But somehow using that, you're going to achieve an encoding and an error correcting circuit, which is tolerant to a certain amount of noise, right? So just some technical terminology here from the theory of fault tolerance. So a location refers to any of these elementary physical operations. So you have single qubit gates. You have, for example, the plus, initializing the ancilla to a plus requires a Hadamard, right? So that's a single qubit operation you have to do for the encoding. 2 qubit gates. Of course, these gates, it also includes identity gates, because there are times when you do something on a pair of qubits and the other qubits are waiting, so to speak, right? And as they are waiting, they are going to decohere. So this also has to include then identity gates as part of your set of elementary physical operations. It includes state preparation, it includes measurements, right? So these are all locations that one must consider to be faulty, right? And a location is to be faulty whenever it deviates from the ideal operation, leading to errors in the qubits. And like I said, the idea is to see that these errors do not propagate or cascade in a catastrophic manner. So one should mention a few assumptions that go into this when one builds a theory of fault tolerance or when constructs a fault tolerance scheme. The fundamental assumption out here is that the noise is IID, right? Which means that the noise acts identically and independently on every qubit, right? And of course, the exception to this is when one considers a 2 qubit gate, where you assume that both, so when I say that I have a noisy Hadamard, it's just a noisy Hadamard on a single location. But when I say that I have a noisy C naught, then the noise, it's a noisy 2 qubit gate. So there are actually 2 locations that one is addressing, but that's considered to be a single fault, right? So that's just some technicality in counting these things. And like I said, the key challenge is to design these gadgets or these composite circuits in such a way as to minimize the propagation of errors due to faults within the same encoded block, right? So like I said, obviously this cannot be done to arbitrary levels of accuracy. You have to put some threshold requirement. And where this threshold comes in is in this last phrase, right? I pick a certain encoded operation. Let's say I have my encoded C naught operation, right? Now I have to have if I say that my scheme is fault tolerant, then typically it means that this encoded gadget can tolerate at most one fault anywhere in its set of locations, right? And up to one fault, my error correction, of course, error correction then also requires its own gadget. My error correction gadget is going to correct for this single fault. But once I start having multiple faults within this gadget, that is when my error correction circuits cannot tolerate these errors. And that is when these faults are going to propagate in a way that leads to very poor fidelity at the end. So this threshold estimate is basically an estimate of how many such malignant locations I have within a single encoded block, right? So there are a few steps out here. First, you need to identify an error correcting code. Then you need to identify a fault tolerant way of implementing this error correcting code. Then you need to identify a way of implementing fault tolerant gates. And finally, you have to argue that there is some finite error threshold for this scheme that one has constructed. So my aim is to basically walk you through these steps for this amplitude damping noise and the 4-qubit code, which is essentially our recent contribution. So a formal definition of this fault tolerance threshold is that it is the critical value of the error rate. So P is what I will denote to be the single qubit error rate or the failure probability of a single gate. We treat both of these on the same footing, right? So in fault tolerant theory, you treat both the error on a qubit as well as the fault in a gate on the same footing. And you say that both of these can happen with a probability P, right? You assign some single error rate to this. And then you say that there should be a critical error rate at which point, right, or beyond which point, the fault tolerance protocol does not do any better than the unencoded version. You're better off with simply a bare qubit, right? And one of the high points of quantum computing theory was the so-called famous threshold theorem, which was developed by Gottesman, Preskill, and others, which argued that there does exist such a finite threshold. And experimentally, then what one has to aim for is to somehow keep the noise, whether it's the qubit noise or the error rate, or the failure probability per gate, has to be kept below this threshold. And then one can actually do fault-tolerant quantum computation. Okay, so a few more details about standard fault tolerance schemes, because we're going to contrast that with what we do in a few slides. So typical fault tolerance schemes, and of course, this is something that even we do, which is basically that they are robust. So I already mentioned this, to one fault in a given encoded block, and then one argues that multiple faults are suppressed because of the probability, right? They are higher orders in P, and so they will be suppressed. And this again, I mentioned counting the number of malignant pairs. So let's C denote the number of malignant pairs, which are basically pairs of faults. I'm sorry for this typo here. Pairs of faults that propagate an uncorrectable output, right? And then you get an upper bound on this threshold, this P threshold, simply by counting the number of malignant pairs for a given encoded block, right? And this, what's on the left, right, is basically what happens when the number of malignant pairs is so high, or rather your P. So basically this equation is what puts a constraint on the P, right? It says that this is the point at which the multiple faults actually start dominating in some sense, right? And this is the point at which your fault tolerance scheme is no longer useful, because the bare qubit actually does better, right? So this C basically gives you an estimate of the threshold. In fact, in particular, it provides an upper bound. So there are details to this, and I'll refer to our paper for further details. But I just wanted to show some threshold estimates now. So like I said, general purpose fault tolerance schemes are typically based on standard stabilizer codes. And these are stabilizer codes which address, which are sort of tailor-made, one can say, for Pauli noise, right? And all other noise models are then broken into combinations of Pauli errors. So this is what the standard 7-qubit code does with concatenation, which means that the number of physical qubits you need is not 7, but at least 49, right? And with these 49 qubits and assuming independent Pauli noise, this was one of the earliest threshold results that was shown. I don't know why the references are not showing up. Okay, yeah, this is the Aliferis Gottesman Preskill threshold result. And you see the number is fairly low, right? It says that you need to keep the gate failure probability or the single qubit error below something like 10 to the minus 4, right? Now, much more recently, we have this idea of topological codes, and prominent among these are surface codes, which typically use hundreds of qubits. And a threshold estimate was worked out subsequently for these kind of surface codes with depolarizing noise. And then you see that that jacks up this threshold upper bound to something like 10 to the minus 2. And that now seems within reach, right? It's just 0.01. Furthermore, what was also shown is that if you wanted to only achieve fault tolerance against a particular kind of noise, and this then immediately leads to, motivates our work as well. In particular, what was looked at was the so-called biased noise systems, right? And this is, of course, even relevant more so to superconducting qubits, where one kind of error, which is basically the dephasing error, the Z noise, was much more, was orders of magnitude more important than the X noise, right? So if the Z noise is much more important than the X noise, then I might as well work with a simple 3-qubit code, because I have a 3-qubit repetition code that works well for dephasing noise. So if I were to simply tailor my fault tolerance scheme to a specific noise model, then it was shown that you actually get a very nice threshold upper bound, right? So this result then motivates the idea that it may be useful to look for fault tolerance schemes which are tailored to specific noise models. But I must add here that dephasing again is a Pauli error, and so this also then so what I want to say is basically that this does not again deviate from the machinery of standard error correction or fault tolerance, right? Okay, so let's jump into what we do. So we assume now that the dominant noise process affecting the quantum system is amplitude damping noise on each physical qubit. What is more, we assume that all errors are of the amplitude damping type, whether they are gate errors, whether they are storage errors, whether they are measurement errors, whether they are preparation errors. This is very similar to the model that is studied in standard fault tolerance, where all these errors are assumed to be Pauli errors, right? It's just that in our case, we assume it to be well and truly the amplitude damping error. And what do I mean by an amplitude damping error? That's what I want to show you in this slide. So recall that I said that there are 2 Krauss operators involved, and one of these, like I mentioned in answer to Baladitya's question, is a linear combination of identity and Z. The second error operator is a linear combination of this kind of X and Y. I'm sorry, I have switched from gamma to P simply to be consistent with the fault tolerance threshold P and so on. So P here is the noise parameter, right? Now, what we aim to do, and rather what the 4-qubit code also aims to do, is to error correct only up to order P, right? So the first order of business is to actually expand these 2 operators up to order P, rather in powers of P, and then look at what are the errors that are important up to order P, right? So that's what we do here. Sorry for a bunch of math out here, but let me try to explain this very quickly. So this, now remember, these are the Krauss operators. So when I write this, this is the action on a particular state, right? So you imagine that there's a rho sitting here. There's a density operator rho sitting here. Then you notice that the identity operator is, of course, the leading term, right? That's actually has an order 1 term here, right? And then the order P term is basically something called an F map, right? So I is simply the identity channel. F is a particular map which is written out here, and then you have the Z error. So the first thing you notice is that the Z error is actually of order P squared, and so that is not something that the 4-qubit code will even aim to correct for at this point. But what you have instead is the identity and this sort of funny channel F, right? Now notice that this F is actually not really a CP map. It's not a CPTP channel, right? But it's a trace preserving map, right? And this has 2 terms, right? And these 2 terms are what we will call FZ and FA, okay? The F sub A is simply the damping term, because this E here is simply this E1 operator here, right? And this is the term which truly captures the decay of the excited state to the ground state, right? This is the what is often called the damping error, right? This is FA. So what is FZ? Now, FZ is a kind of off-diagonal error, right, which also has even been sort of measured experimentally. The effect of this off-diagonal error is often referred to, if you look at the literature on, say, superconducting qubits, this is often referred to as a back action error, right? This is often referred to as a back action term in the amplitude damping process, right? So the reason that I'm highlighting this is because I think for the first time in our work, we break down the effect of the amplitude damping noise to separate out the damping term and the off-diagonal term. And the reason we do this also is because it's naturally required if one wants to build a syndrome and recovery circuit to correct for this error. So this F will constitute our error term, right? This will be our error. This will also be the fault, right? So when it acts on individual qubits or when it affects a storage location, this will be called an error. When it affects a certain gate location or a measurement or a preparation, this will be called a fault, right? And essentially, when I say a fault or an error, this is the map I have in mind. It has two parts to it, this off-diagonal part and the damping part, right? Okay. So neglecting p-square in higher order terms, this can be thought of as having a no fault term, which is the identity term, and a single fault up to order p when this F map occurs, right? And the F map, like I said, has these two parts, which is often called, we call it off diagonal, but the literature this is often referred to as the back action error, right? And now some details about the code space. So I see that we are at 11:45. Can I take another 5 to 10 minutes more? And if
you can take another 5 minutes, no problem.
Okay. And any questions so far?
Not that I have seen. We'll after you finish.
All right. Okay. So the next thing we need to do is to understand how this error affects the code space and how we can now detect and correct for it. So I claim that this 4-qubit code can actually detect and correct for single qubit amplitude damping noise. And when one says single qubit amplitude damping noise, it includes both these kinds of errors, right? So it turns out that although this code was developed outside the stabilizer framework, you can still look at it in terms of the Pauli, the action of the Pauli group on 4 qubits, right? So it turns out that these two states are actually left invariant by a group of Pauli operators, which are generated by these 3 operators, right? So the 4x operator, the 2z and the 2z operators, these are all stabilizers for this pair of states, right? And they generate, in some sense, the stabilizer for this code, right? But because this is not a perfect error correcting code, this is not a standard stabilizer code, that's a technicality which we can discuss later if you wish. But it's still useful to think in terms of these stabilizers because they tell us what are the measurements that we need to do in order to extract error syndrome, in order to detect errors, right? And one can also immediately identify what the logical operations are. So what is the logical X operation that maps the 0L to 1L and the 1L to 0L? That is simply this X tensor X operation. And the logical Z operation is again a Z tensor I tensor Z tensor I operation, right? So these are the logical X and the logical Z operations. So let me explain how this error detection works now. So there is a 2-step syndrome extraction procedure where you have to extract first. So typically when you have a set of stabilizers, and for those of you who know how a stabilizer code works, you will measure the set of stabilizers, right? And that will tell you something about which are the set of errors that occur. So in this case, like I said, we have 2 kinds of errors. The damping error, FA, is actually detected by measuring these 2 stabilizers, the ZZ operator on the first 2 qubits and the ZZ on the last 2 qubits. These are essentially parity measurements, and you can notice that actually what happens is that these code words all have even parity, and a single damping error is going to make them into odd parity states. So this pair of Z measurements actually does the parity measurement, right? And this gives rise to 2 classical syndrome bits, S1 and S2. Notice that I've put down a few more syndrome bits here, the U, V, etc. Now these are the finer syndrome measurements, which one does subsequent to the S1 and S2 measurements in order to then pinpoint the exact location of the error. And so this is what a syndrome chart looks like. You eventually need all 6 syndrome bits, but the latter measurements are sort of conditioned on the outcome of the S1 and the S2, right? The second step is if this S1 and S2 were both 0, which is the case of the no damping error, you still have to check whether there was the FZ error, right? And so in order to detect the FZ error, you have to do the XXXX measurement, the 4X measurement, right? The X tensor 4 measurement. Okay. So the recovery again is a two-step process. The first step, when you have detected one of these damping errors, is somewhat easy to do because the damping operator is simply of this form, right? It's of the form X plus IY, which can then be written as I plus Z times X, right? So you fix the X error and then you fix the I plus Z error, right? And these are all Pauli operations, which we know how to do, right? But if you have the off-diagonal error, which is not detected by the parity measurements, then this requires this stabilizer measurement, right? And this stabilizer measurement, what we do is if the measurement outcome is +1, then we proceed. Because if the measurement outcome is +1, it means that your state, in some sense, is left unchanged, right? So that means that the state is not affected by this off-diagonal error. Whereas if it is a -1, then what we need to do is a kind of logical Z operation, which is to apply Z operators, individual Z operators on the individual qubits, right? So this is a very lightning quick breakdown of the error correction process. The details again are in our paper, which I think I finally referred to here, but now I just have to show you a few circuits to kind of show you the complexity involved of how to do this. This is the syndrome extraction part, the first part, which has these two Z measurements, as you can see here. I hope you can see my pointer. And then this feeds into the recovery circuit. And the recovery circuit then has, so all these parts are broken down here. So the parity measurement is basically this 2Z measurement. And this is a way to do the measurement. Always you have to invoke an ancilla. You cannot measure directly the qubits, right? So this happens by using two C-naughts to extract the syndrome to an ancilla and so on. This is what the 4X measurement looks like, right? And this is probably the most complex part of our error detection circuit, right? Now one can simply combine all these parts and have a recovery unit like what is shown here. However, such as just putting all these parts together is not going to give us a fault-tolerant error correction circuit, right? Because again, this circuit now assumes that a lot of these operations are ideal, right? All these operations are assumed to be ideal. So now one has to go to the next step and build a fault-tolerant version of this, right? And that's what I'm going to show you in the next slide. Now, this of course looks rather daunting, but let me just highlight a few parts here. Of course, this is explained here in our paper. So this ket psi here, these are the data qubits, right? These are the qubits that you actually work with, the computational qubits or the data qubits. These are the ones that you have encoded, right? The dotted lines represent what are called flag qubits. And these are the qubits that are going to flag faults in particular locations, right? And it turns out that this A out here is simply identity, right? And this C0 and Z are what the parity measurements are, which I showed you on the previous slide. P here represents other parity measurements. R represents the recovery circuit, which I showed in the previous slide. But this M prime here represents a much larger X tensor 8 operation, right? Because the X tensor 4 operation only detects and helps you correct for this off-diagonal term on the data qubits. But now you have all these additional qubits that come into play, right? And so including all the additional ancilla locations and the flag qubits, you need to do this X tensor 8 operation. But the nice part, as we show in our paper, is that this can all be done in a way that does not involve multiple qubits at the same time. They all involve single, pairs of C-naughts. So they all lead to basically just single locations, right? Okay, let me proceed now. And yeah, so that was just the error correction gadget. So this is the error correction gadget that we developed. So the technical word that I was avoiding here was the word transversal. And I come to that in the very next slide. So now what about gates, right? So I explained to some extent the syndrome, the recovery, and the error correction. But now what about the encoded operations? So the first thing you need for a universal scheme is a 2-qubit gate, right? So what is the 2-qubit gate to choose? Well, it turns out that both the C0 and the CZ gates for the 4-qubit code are transversal, which means that the gates can be done in a parallel fashion. So let me just show you this since I have this on the next slide. So this is what I mean by transversal, right? So I have one set of data qubits here, which is the psi1, another set of data qubits here, which is the psi2. One of these could be the control, one of these could be the target, right? Transversality means that I can implement this gate by coupling exactly a pair of control and target qubits at a time, right? So in some sense, I'm doing a set of disjoint control operations, right, which together lead to my logical control operation on the logical qubits. So how do we then pick one over the other, right? Both the C0 and the CZ are amenable to this, but both are not amenable to fault tolerance. And this then has to do with the structure of the amplitude damping noise. So the transversal C0 is actually not fault tolerant to amplitude damping noise. So in the scheme that we propose, the 2-qubit universal gate will be the CZ gate and not the C0 gate. It will be the control Z gate and not the control X gate, because the control X gate does not commute with the error operators. In a standard Pauli noise model, the X commutes in the sense commute or anti-commute, right? So that you can sort of conjugate out the X with the error. But in this case, the error and the X do not commute, neither do the anti-commute. Actually, it leads to an error of the form E dagger, right? Remember the E operator, which was essentially ket 0, ket 1. So E dagger will be ket 1, ket 0, which is an off diagonal with the other off diagonal entry. And this is not a part of the set of correctable errors for this 4-qubit code. So this then dictates that our choice of 2-qubit gate must actually be the control Z gate. And this is the notation that I use, the control Z gate. And so this is what I mean by a noise structure preserving gate, right? So while both the control NOT and the control Z are transversal, can be implemented by picking disjoint pairs of qubits, the fact that the error operators have a simple, conjugation when it comes to control Z, but they do not have the simple conjugation when it comes to control X, dictates that the gate of choice for this fault tolerance scheme should be the control Z gate. Okay. So the control Z, however, also requires these two error correction units, because this is how the error propagates. So this is a simple picture to show how the error propagates. So I'll wind up in a couple of minutes. This is an error before the control, and this leads to an error here, and which can be corrected. The E error is something that can be corrected subsequently by the error correcting code. And then there is a Z error here. Now the Z error requires us to do some interesting thing here, where there is some classical information that's sort of communicated between these two EC units, and then that assures that this complete unit is fault tolerant. So the bulky part of the scheme is just the error correction unit. Once you have the error correction unit, the control Z operation is very simply described. What about the full universal set? The full universal set requires all of these. It requires us to prepare the 0 and the plus, which also we show in our paper. It requires us to implement the logical X and Z, right? And it turns out that the logical X is exactly similar to the bulky error correction circuit. And then it requires a 2-qubit, I'm sorry, I don't know where this logical came from. I guess I meant logical 2-qubit gate. And as I argued, the gate of choice should be the control Z. Finally, what about single qubit logical gates, right? So the Hadamard S and T along with the control Z form a universal set, right? How do we get this universal set? Well, this requires this interesting idea called gate teleportation. If I have time and if there are questions, I'll explain the idea. But suffice it to say that it basically involves gates that we already have with us. For example, to implement a logical Hadamard, I will teleport the state in this way, right? Involving simply the logical X and the identity gates. Okay, and what I require here is the control Z. And this X bar here is a X measurement. So using the ingredients that I have 1, 2, 3, I can implement a logical Hadamard via this idea of gate teleportation. Okay, So I think this pretty much concludes what I have to say. The final step, like I said, is to estimate the threshold. And I already explained in some detail earlier what that involves. It involves counting how many, so all of these gadgets are guaranteed to be fault tolerant up to a single fault. So now if I start putting these gadgets together, if I have an extended gadget, then how many malignant pairs or how many malignant pairs of locations can I have which lead to faults which are uncorrectable by the code? So we do a rigorous estimate and we show that we get a threshold which is of the order of 10 to the minus 4. Okay. So let me just summarize what I have and then maybe I can take some questions. So what we show is that it is possible to construct a universal fault tolerance scheme which is tailored to amplitude damping noise using a noise adapted code, namely the 4-qubit. There are several key features, and one of them in particular, which is what leads to this somewhat low threshold estimate, right? So although we use only 4 qubits, we don't use 7 qubits, but the threshold estimate is still somewhere close to the what the 7 qubits does. And that is precisely because of the second point out here, that we need a non-trivial recovery unit, right? We need to do this 4x operation in order to take into account the so-called off-diagonal error. And that 4x operation, which is done in conjunction with an ancilla, in order for it to be done fault tolerantly, requires 4 additional qubits. And so that is what makes the error correction gadget complex. And that's what leads to a somewhat lower threshold estimate than what one might have hoped for. So again, this point about transversality versus noise structure preserving gates, I already mentioned that. So this is a kind of first step, I think, towards achieving fault tolerance against specific noise models. And this can, for example, be used as the first step in building a fault tolerant architecture. Of course, future directions include basically questions of scalability and optimization, right? So can we optimize this error correction gadget somehow that we actually are able to jack up the threshold? And of course, can we scale this up? So what I have shown you is simply one level of encoding. Whereas what the 7-qubit and so on do, in order to remember to achieve that 10 to the minus 4 number, the 7-qubit actually has to be concatenated to at least 49 qubits, right? So can we also then, with this approximate code, right, with this noise adapted code, can we then do a concatenation or use other, generalizations of the 4-qubit code in order to now achieve fault tolerance at multiple levels, so to speak, and not just at the first level, which is what we have demonstrated. So let me conclude with this, and thank you for your attention and time.
If there are questions, please unmute yourself and you can ask. Can I ask you
Hello?
one question? Yeah, please go ahead. Yeah.
Sorry. So Prabha, this is a very nice talk. I actually wanted to make a comment, not so much a question, that in all the practical architectures, I mean, this has been something that I've been thinking for a while, that the model of Pauli errors is actually not so practical for superconducting qubit architectures. It may be true, but because most architectures do involve these Jaynes-Cummings interactions with readout cavities and Purcell filters and all these things. So I think this is a pretty good approach to take for actual practical architectures. So now comes the question. I just wanted to see if I understood correctly that if you do have an amplitude damping model as the one that you took, you require 4 qubits to implement the encoding scheme, right?
That's right. Yeah.
Whereas if it were Pauli errors, you need 5. Is that?
That's right. Yeah. That's
okay.
Right.
So it does provide, on the encoding side, it does provide an advantage.
Yes, but that encoding, I should add this caveat that encoding is not fault tolerant. Okay, that circuit that I showed you is not fault tolerant.
Is not fault tolerant.
Yeah.
Okay.
So if I want it to be fault tolerant, then actually we require, so I did not show you the preparation circuit here. Maybe I could have had backup slides. But the preparation circuit, I think, involves, I'm not sure if it's 6 or 8 qubits at this point. I think so the way we prepare actually is very nice. this code actually has a nice structure and can be broken down as 2 bell pairs. Okay. So basically our preparation circuit is a bell state preparation circuit. And I think each bell pair requires 4 qubits. So totally the preparation also would require 8 qubits. Right?
Okay.
But that would be the case, like I said, if you wanted to do the 7 qubit steam code encoding, the 5 qubit, forget it. It's just too complicated actually. That's why nobody talks about fault tolerance with the 5 qubit. Right? To actually implement the 5 qubit encoding fault tolerantly is very challenging. But 7 qubit will already require 14 qubits typically for the encoding to be fault tolerant. Right? So yeah, so the scaling does happen, right? When you go from just the bare error correction to the fault tolerance. So that is what our endeavor was, to see that if this advantage that these kind of non-Pauli tailored codes have,
exactly,
right, at the bare level. So like you pointed out, it requires only 4 qubits. But then once you make it into a fault tolerant circuit, does this advantage even carry through, or what is the kind of resource scaling that happens? Right?
Yeah.
So I would say that it's actually not too intensive in terms of resources, because like I said, it's only 8. Whereas if you think of the 7 qubit code, then you need 14.
14,
When
exactly.
you talk about surface codes and so on, they're just, scaling.
49 and exactly.
Yeah. So I would say it still has an advantage, and thank you for your comments and so on. I also think that this is very interesting that one can do fault tolerance even, without looking at the Pauli framework or the stabilizer framework as such.
Yeah. I think we should talk more about this later, because I think this is more practical in my opinion. So, yeah.
Okay, so thank you, Prabha, for a very nice illuminating talk. In 1 hour, you almost covered from the very beginning to end. It's really amazing. I just have a very brief question, because we don't have much time. I'll send you some email queries later. This coherence which you generated, this one which you called, it's a kind of noise. Can that be useful? That coherence, can you store something there? This off-diagonal term.
Yeah. So you're talking about this FZ part that I spoke about.
That's right. Yeah.
Right. Yeah. So I think if you were to just restrict yourself to looking at only the damping part, which also we did earlier. So the first thing we did was to only look at this part. Then actually the circuits and all of that become much simpler, right? In fact, I think we even showed a threshold of something like 10 to the minus 2, right? If you only focus on correcting for the damping and you just completely ignore the second step, right, which involves that 4x measurement. But I think that leads to actually a more severe loss of coherence. In fact, there is a fidelity loss that happens. So you're not truly correcting for all the order P, right? So I would say that indeed this FZ is important. And I think, for example, in superconducting labs like the one in of Liang Jiang in Chicago, or even the Yale group and so on, they actually try to quantify this back action, right? You can actually, in terms of in your Jaynes-Cummings model, you can actually look at the coupling term and try to quantify what is the severity of this off-diagonal term, right? So I think that's another nice aspect of what we do is, suppose you say that this back action is really not important, then we have a simpler sort of scheme where you can only fix the damping errors and move on, right? And maybe get a better threshold estimate.
Okay, so thank you so much. Very nice talk. Truly enjoyed it. Diksha, you can take over.
Thank you.
Yes, sir. So we will continue this session after lunch at 1400 hours IST.
Sir, now you can share the screen.
Yes, I'm trying. Yeah, thank you. Is it appearing full screen?
Yes, sir. This
Okay.
is full screen now.
And if I move, you're able to see the first slide.
Yes, sir.
Okay, thank
This
you very
first
much.
slide now.
Okay. And I just go here. Okay, thank you very much. So I see you in an hour, yeah?
Yes, sir.
Cheers.
Sure, sir.
Diksha, are you in?
Yes, sir, I'm in. But
Can
Dr.
we check?
Jacob has not joined yet.
Professor Baimont has not joined yet.
Yes, sir.
So maybe one can see, maybe you can send him an email or a message quickly.
Yes, sir.
We send him an email, sir. Hopefully he'll respond.
Yeah.
Okay, sir. So let's now resume the afternoon session. Professor Panigiri, please continue.
Yeah. Yeah, Professor Baimont has just joined. Good afternoon
Yes,
here in India.
Good. Can you hear me okay?
So it's pleasure to welcome Professor Baimonte to this workshop. So currently he's heading Skoltech's Laboratory for Quantum Information Processing, Center for Photonics and Quantum Materials. He has a very interesting, career. If you have noticed, after his bachelor's degree, he was the first quantum programmer in D-Wave quantum computers in Vancouver, 2004 to 7. Subsequently, he did his PhD from Oxford, and he had association with very prestigious institutes all over the world, starting from Harvard, then this joint Oxford and CQT Singapore. Then subsequently, after that, he went to to the laboratory. This is the quantum science division. Sorry, he went to Torino ISA Foundation, and there was 12 to 17. In 17, he joined Skoltech, and in 2019, when this new laboratory started, he is heading that lab. He's, as you can see, in his varied career, he has a leg both in academics and industry, and with quantum programming. So obviously, he has a strong interest in quantum algorithms and uses varieties of mathematical tools to, starting from group theoretic to tensor network to formal theory for this algorithm development and application. So, Professor Baimonte, it is 40 plus 10. 30 minutes for your talk, 10 minutes for questions and answers.
Okay, it seems a little bit unfortunate, but it looks as if I'm going to have to quit the web app to actually share my screen. I don't know why that is, but it's forcing me now when I press share screen, it says I have to quit now to share.
Can somebody help?
sir.
Excuse me, sir. Can you tell me the problem again?
Well, I click share and it says open system preferences. I click on open system preferences. I allow the Cisco WebEx events to access. Then it says Cisco WebEx events will not be able to record the contents of your screen until it is quit. You can choose to quit Cisco WebEx events now or do it on your own later. If I press later, I'm not able to share and it just repeats the same process again. If I press quit now, it'll quit, I suppose, then I can rejoin and share this.
Yes, if I may, I had to go through the very same procedure the other day. So yes, unfortunately, you have to restart the program and then it will work.
Okay. can everyone hear me okay?
Yeah, we can hear you.
I apologize to the attendees for the short technical delay. I will be speaking today on the minimization of Hamiltonians by variational quantum circuits. And I will cover the basic definitions of quantum bits very briefly, just so we all agree on the same notation. Some of the aims and objectives of this research. I will briefly list the experimental justification for the physical model that we're presenting. And we'll talk about some of the mathematical properties of Hamiltonian ground states and how those can be programmed in practice. And I'll talk a little bit about some recent experimental demonstration, and I'll sort of redefine what they're doing and let that pave the way for a discussion about universal variational quantum computation. And I'll discuss then some of the error robustness and some other results that the lab that I work in have been generating, and then I'll conclude. So to begin with, we work with a very standard setting of quantum mechanics, perhaps the simplest setting in many ways, although there's one caveat. These are combinatorial spaces with a parameter n, which is the number of qubits, and the wave functions will not vanish at the boundaries, so the large n limit essentially doesn't exist as you'd expect in, let's say, traditional quantum mechanics. And we'll use the complex Euclidean space Vn, which is just some n copies of C2. The important point here is that we'll have Hamiltonians, which are Hermitian matrices on 2 to the n by 2 to the n matrices, and we'll use the expected value of an observable. And other than that, we won't require much more quantum mechanics than that. So just a very standard setting for today's talk. And the type of notation that we'll use is we'll define Bn to be the computational basis. The single qubit basis is then 0 and 1, and that corresponds to B1. The linear extension of Bn over C would be canonically isomorphic to Vn in the sense that Bn has a basis which can be identified with a basis choice in Vn, which in turn is equal, as we know, to C2 to the n. The standard sigma matrices are given as follows, and down below the important point here is point number 3. The set of Hermitian matrices on 2 to the n by 2 to the n matrices is equal to the real linear extension of all possible sigma matrices, where AL will select your sigma matrix. And I think this is a well-known fact for people working in quantum information. And so this should be fairly standard. Now, we will use quantum circuits, and just to sort of briefly sketch kind of a definition of what's going on, the quantum circuit is a way to form a tensor contraction, and there's basically 4 different types of notation in quantum computation, which is common. They're all sort of mixed together in many cases. The quantum circuit can be viewed as a contraction of a tensor where you can line up the wires with a tensor indice, and you can line up these with the tensor symbol. You can line up the boxes or squares, etc., with the tensor symbol. Then you can have when two wires are unique between two symbols, that's a contraction which corresponds to a closed wire. We're doing that now for the specific purpose. As we are aware, a p-depth circuit can be written as a sequence of gates quite evidently. You'll take unitaries use of L, they'll act on some initial state, and there'll be p of them. Yet this form can evidently mask the internal structure which is exposed by a tensor network, which is the following circuits. Now, in the beginning of quantum computation, the way that people used to think about this is you're given a quantum algorithm which will factor into a sequence of unitary gates, which then must be embedded into your quantum processor. However, this is not the current way that people think about this. In fact, today, what the experimental teams, the top leading teams around the world, such as IBM and Google, they will create the same circuit structure every single time, and it is up to the quantum programmer to tune and adjust the parameters so as to minimize an objective function. We will get to what an objective function is later, but this has created what's called ansatz quantum circuits. There are a few different families of ansatz. In fact, there's many more than what I've just listed. But the main idea is that you have a fixed structure quantum circuit and you're allowed to tune these gates, and we will minimize an objective function. Why is this a good idea? Well, this is the only thing that that people are focused on right now, essentially, And you can see from this table, there's a number of qubits and there's the depth. And the number of qubits and the depth, there's more results than just this, but this is what I have in the table. And it's quite exciting because you can have 20 qubits, depth 25, 23 qubits, depth 4. So you're able to realize these variational ansatz circuits on an increasing number of qubits with an increasing depth. And the main take-home message is that dozens of gates can now be realized with a negligible accumulated total error. This will not scale up forever, but we're living in kind of a sweet regime where error mitigation techniques allow us to kind of assume the gate model for at least some short-ish circuits. And so this is what everybody, I would say, is very excited about. And this is the kind of idea that we're going to explore today in this talk. And so what is the ground state model of quantum computation? So like anything, we are given we start with a problem statement. So the problem goes like this. You're given a Hermitian matrix. You have a quantum processor that receives a list of numbers, which is given by boldface theta, and there's some p-long list of numbers, for example, and you're able to prepare the state, which will be defined by setting the ansatz circuit by the prescription given in the list of numbers theta, and that will produce the following state. Then you're able to repeat this, and you're able to get an expected value. We, for the purpose of today's talk, that the expected values returned by the machine will essentially be the true mean, not the empirical mean, but both can be bounded, and the statistics of measuring the observable actually behaves quite well. And so the goal is to find a theta that gives the best approximation of the minimal eigenvalue of h. So for example, we're trying to minimize the second equation here, which will give us the arg minimum of this, and the arg min of this is actually going to be the theta, which minimizes this, or the quantum state, depending on how you set things up. And the first point to mention is that the Hamiltonian will be developed to satisfy several constraints. It's not going to just be any Hermitian matrix. We have to sort of bound things so you don't have an exponential number of terms as your problem class scales up in n. And in addition, the true minimum might not be reached by any assignment of theta, and the true minimum is actually given by this here, and this is a lower bound on the second equation here, and that's called the variational principle. So the properties of ground states. The view of using a ground state quantum computer is something that I have taken part in since the time at D-Wave. This was, this at some time long ago, this was a very new idea, a very creative idea. Now it's become more commonplace, but it also became somehow an unattainable idea. D-Wave has been working on a quantum annealer, not a universal quantum computer. When I was working there, I actually proposed some methods to add an extra coupler to the D-Wave quantum computer so that it might do universal quantum computation, but the method was very convoluted and cumbersome. Now, these ideas got started, let's say, in 1982 by Barahona. He proved that basically all the problems in the class, all optimization style problems can be embedded into an Ising model of the form 1, and it can be restricted to some square lattice where the couplings can be vanishing or 1 or -1. And the first thing to notice is that you can check the energy of an Ising model relative to a quantum state, or sorry, relative to a classical assignment in the size of the graph that the Ising model acts on. So you label your edges of the graph, you equate them with you equate this graph with the JLM and then the HIs, which are the local node energies, and you can put in these values for the nodes in equation 2, and that will give you the energy relative to the state. This calculation can be done in polynomial time with the number of J's and the number of H's. It's quite evident. So you can check the answer easily, but minimizing this thing turns out to be NP hard. Well, actually, and in fact, you can turn it into a decision problem and you can make it into a complete problem, but Barahona did not do that, at least at that time, and that's okay. So going further, what we had was, in the modern setting, this is taking place like in the early 2000s, in Kitev's textbook, his famous book, they proved that 5-body qubit Hamiltonians has a ground state energy problem, which to find that ground state is QMA hard. And in fact, what he did was he took the output of a quantum circuit, and if the circuit outputs 1, it will shift the lowest eigenvalue of a Hamiltonian up. And if it outputs, let's say 0, it'll leave the kernel intact. He actually was 2 parameters A and B, but we don't have time. It's equivalent. And so what they're doing is they're saying, okay, decide if this Hamiltonian has a lowest eigenvalue 0, or if all eigenvalues are at least 1, for instance. And that problem turned out to be QMA complete, which is the analog of MA, which is in turn the probabilistic analog of NP. Then going further, finally, at some point, Kempe and then again Kitev and Regev proved the QMA completeness of 2 local Hamiltonian on a sparse graph. Okay, so that's a graph without nearest neighbor interactions. It could just be any graph, essentially. And then Oliveira and Turhal showed QMA completeness on a 2D square lattice. Okay, so it kind of recovered back to what Barahona did. And these constructions also inspired the excellent proof by the famous theoretician Aronoff, Dorit Aronoff, that adiabatic quantum computation can simulate quantum circuits. And around the time in 2006, 2007, the open problem was related to what D-Wave can actually do. And can a reduction of the interactions past general 2-body be given? Or in other words, what is the simplest Hamiltonian that can have a QMA complete ground state? Okay, so then I answered those questions at that time. Now, please ignore the slight typo on this slide. I somehow didn't manage to fix that. There should not be an m comma m plus 1. This is one operator, the sigma. So just cross that one m out. I apologize for that. I gave actually a second talk earlier today in the middle of the night, and I noticed that at that time. So I apologize for that. So this is one of the several problems that we work on in the lab where we're formulating a problem from physics into a way that, let's say, mathematicians can work on it and understand it. I especially like this particular example because it's quite easy to state, but it's very hard to solve, I'd say, in the general case, and we're still working on it. It's been solved in some very general, important cases which have opened up, like, let's say, different fields of physics, such as the parent Hamiltonian problem. Essentially, the QMA complete stuff is all solving this problem in one way or the other. And so the problem goes like this. You are searching for a non-negative Hamiltonian H with a kernel spanned by a given set of vectors. That, in general, is quite easy. You could take a projector onto that set and subtract it from the identity, and that gives you a kernel spanned by that set. Yet that has essentially does not have the right desirable physical properties at all, so that's not a valid solution. The constraints that we want to include, for example, if we included k-locality of interaction terms, it would rule out this projector that I just mentioned. Spatial locality, so you can ask a question, does a quantum state of this type exist in one dimension or not? And then, of course, you can place conditions on the spectral gap, frustration, or integrability, and you can make approximations. So it doesn't quite have a kernel that spans the set you want, but it'll have something very close to that kernel. Inside this context, several no-go theorems have been developed, and those are even, let's say, just as interesting. So going a little bit further, the first step is we can solve this problem, and we'll do this very fast just to motivate. Solve this problem generally in the classical case is sort of a warm-up. The way that we'll do that is we'll use what's called pseudo-Boolean functions. These will transform your Ising spin variables, which are plus or minus 1 variables, into Boolean bits by the affine transformation given here. And this can be noticed by equation 3 sort of summarizes what's happening. On the left-hand side, you take the complex numbers and you do a field extension with the indeterminates. They're not variables because there's no equation. So they're indeterminates, x1, x2, xn, and then you take the modulo space such that all of the x's squared will equal x. So that's some kind of idempotent condition on the x. Then you will arrive exactly at these types of functions, except r will now be c. This will actually be isomorphic to vectors in C2 to the n. And of course, every vector in C2 to the n gives a diagonal matrix over C. And so your Hamiltonians are considered to be diagonal matrices. And this will be kind of the setting where your spin variables are now replaced with binary variables. And so what we'll do now is we'll construct the set omega n to the k, which will be the field extension in indeterminates over R modulo the idempotent condition such that the kth plus 1 term will vanish according to this equation, which means that, for example, in equation 5, you will see that omega n to the 2 means that k plus 1, which would be 2 plus 1, which is 3, will now have this condition that they vanish. So you're basically adding a root to your polynomial, your polynomials, and so that root makes it constrained to two-body interactions. In fact, h omega n to the 2 is exactly your two-body Ising Hamiltonians written in another way, and then ask the following question. Given some subset of bit strings, which are n long, does there exist a non-negative h in omega n to the k such that the kernel of h is spanned by that set S? In general, we found that this to be true, but there are caveats. Firstly, as an example to kind of motivate when we started this problem, before we, let's say, formulated it in this sort of new, more systematic way, we said, okay, can you specifically find an H such that, for example, its ground state is a logic gate spanned by this logic truth table? And that turns out to be true, but we also found out that certain logic gates were not possible. So for example, there does not exist an H in omega 3 to the 2 such that the kernel of H is spanned by X, Y, and Z. Actually, my postdoc mentioned that if you drop the, so Richik Samgupta, actually, he mentioned that if you drop the non-negative condition on H, in fact, you can have a kernel that does span this, yet there is a lower eigenvalue. So he originally proposed that as some kind of counterexample because of this slide that I forgot to mention, hey, you know, this is still non-negative, but all of them from the original problem statement are supposed to be non-negative, and so it's fine there. But it's an interesting counterexample nonetheless. There are many open combinatorial questions with these types of problems, but nonetheless, we have the following construction, and then I'll mention the main theorems. Adding an extra slack bit or some set of slack bits, I can always embed any set into an Ising Hamiltonian, probably no surprise for those that work on it. And doing that, we go to the following. We have basically three theorems. So given this set, we can always find an H in omega 2 to the n plus polynomial in the size of S such that the kernel of this H is spanned by the set. Okay, so essentially we can solve the kernel problem, but we don't know the best embedding for to embed S. At least I don't know that. Next, we can solve the kernel problem specifically for classical circuits. We can perturb the output of the circuit by adding this factor, this projector onto 0. And then we can actually formulate a minimization problem, which will give the input of the circuit such that the output would minimize this. Okay, and in doing so, we can also construct the fact that if we have a family of, if we have some kind of way to generate these H's inside of omega k, and we can decide if this omega n to the k has a non-trivial kernel, this turns out to be NP complete for all 2 is less than or equal to k is less than or equal to n. So this is kind of the summary. The open questions that still remain are really about specific embeddings. You know, how few qubits can you do X and Y and Z? How few qubits does it require to realize certain operators? And in particular, the no-go theorems. There's not very many of them. There should be more. So there's still some open questions here. Now, we don't want to work on the classical problem today. This was maybe interesting, let's say 20 years ago or even longer ago. Some mathematicians worked on this 100 years ago or even 50 years ago and made some progress in kind of a different setting. But what we want to work on is we want to take and instead of embedding a bit string, we would like to embed a quantum circuit into the ground state of a Hamiltonian. So if you see equation 15, we're looking for a Hamiltonian, H, that has a kernel spanned by this quantum circuit. So in other words, minimizing that Hamiltonian would give us the output of the quantum circuit. And here I will stop for any questions. If there are. Okay, so I suppose there's no questions. I will continue. If there are any, it's okay to ask them as we go. And again, the problem is generally solved by constructing this projector onto the ground, onto the space of the circuit, but that won't work for the following reasons, as we will soon see. So the types of tools we used originally we used the following tools to solve this problem. So originally we tried to build this Hamiltonian, and we had to use these gadgets. And I'm showing these because it motivates something that goes on in the talk. So these gadgets are a construction that allows you to create an effective Hamiltonian, such as a YY interaction out of present terms, where this Hamiltonian does not contain YY, but you can create it at the cost of adding a large spectral gap. Likewise, you can do the same thing with number 18. You can do the same thing with a number of different constructions as such, and those give you a way to capture, let's say, 3-body and higher order interactions, just as we did for the Ising case, by using slack bits and a large gap and what's called a perturbative construction. And going further, we have the following thing. Remember that the ZZ and the Z term, which is just the generalized Ising model, this is something that D-Wave can realize. If you add this XX term to it, then you can embed any quantum circuit to its ground state in principle, and this would be useful for universal quantum computation. We also proved this in 2007, then published in 2008, that like let's say this Z times X, it looks a little bit non-physical, but you might be able to do that with 2 orthogonal variables like a capacitive to a flux coupling and a flux qubit. So this was all motivated by the D-Wave work. And at the time, it's kind of an open question. Can you do something with a physical Hamiltonian that would give you universal quantum computation? But the problem is, in both cases, the constructions are quite cumbersome and the gaps are large to be able to do this. So this lets us arrive, however, at the following table, which I believe summarizes the typical view of why most people from, let's say, the physics community especially will believe that quantum computation will be quite advantageous over classical computation. So first of all, on the left, we have problem Hamiltonians. So you can consider these problem Hamiltonians as classes of problems where there's a parameter n that can go up to infinity, and for each n, we can generate these things somehow uniformly at random. The question is, can we find the ground state energy? One body Hamiltonians or one local Hamiltonians, yes, it's easy to do. You can just minimize these one at a time by hand. It's not even a problem, right? You can do this on Mathematica. Next, you have 2 local Ising Hamiltonians. Well, these are NP hard, as we said, and it turns out that classical and quantum, it appears to require, obviously, all the time, exponential time to minimize these. Likewise, the electronic structure will subsume the 2 local Ising Hamiltonian, and furthermore, it goes up, and the rest is just exponential time to minimize those. Now, it doesn't mean that all instances take exponential time. It just means that the worst case scaling behavior of these types of problems generated uniformly with some parameter n will scale exponentially. Then we say calculating the state energy. What does that mean? It says given a bit vector or a quantum state, how do I find the expected value of that state relative to this specific instance of a Hamiltonian? And this is where it gets interesting. So you'll notice that 2 local Ising is polynomial for both classical and quantum. So in other words, if I am given a bit string, I can obviously calculate the energy relative to the 2 local Ising model example. In fact, we did that in one of our slides, if you do remember. And here's where it gets interesting. There is what I like to call the memory scaling conjecture. Okay, this sort of came out from, let's say, Richard Feynman around that time, Seth Lloyd, all of these people said, okay, there exists a quantum state which cannot be stored in any classical memory, yet can be stored in a quantum memory. And to be able to manipulate and to do certain calculations with that state would then be impossible on a classical computer because you can't really store it, and there's not enough structure that we know about to make these types of calculations. So assuming that you can't store your state in memory and there's no technique to, let's say, write down your state in some kind of interesting way where it doesn't blow up in memory, but you can still make these calculations on a classical computer seems to generally be lacking. So it takes exponential time to evaluate an expected value if you cannot store the state and you have no method to do it. Yet it would only take polynomial time on a quantum computer. And so this separation is very, very important. However, let me tell you something about factoring. Factoring numbers actually says kind of this is not a general setting. The memory scaling argument is not the only argument for quantum computers. So to be more powerful. So for example, factoring, if I give somebody two integers and say that they're, if I give somebody two integers and say that their composite is prime, you can check that. Yet finding those two integers appears to be exponential classically and take polynomial time quantum mechanically. These algorithms appear to go through some entangled states, which might be very, very difficult to store classically. So it still might be the same argument. I don't know, at least. But nonetheless, for the case of, let's say, Hamiltonian minimization, the calculation of the expected value is, let's say, easy on a quantum computer, hard on a classical computer. And minimization of these models is still going to be difficult, both quantum mechanically and classically, but every time you calculate an expected value on a quantum computer, it's going to already save some computational time, which could be significant. At least this is the way I like to look at it. I'd be happy to discuss that further at some point, if anyone's interested. Now, over the course of my career in quantum computation, which I've worked on different areas of quantum computation, and I've studied different ways to emulate an effective Hamiltonian on a quantum computer. How would that work? Well, you have control. For example, you could have a method which is control plus a free Hamiltonian evolution, and each one of these methods has a problem. They all have advantages, but they all have a problem. You essentially can't do any of the first three. But the thing that we're going to talk about today is going to be the measure expected values of the variational model. Variational model is highly expressive, but it must be repeated many times. Nonetheless, that repetition has enabled the experiments that I've said today, which are far past the experiments which have been done previously. How many more minutes would I have in this talk?
You can take 15 minutes, no problem, 15 minutes.
Okay, I will be on time. So in 2017, this wonderful paper came out. And I think from that point, people started to really look at the variational model quite seriously, just because of the fact that this experiment is very, very impressive. And here are the ingredients. When I started to work on this, there's some good theoreticians here and a lot of experimentalists. They came up with these ideas and they demonstrated this experimentally, and it was really amazing work. And then from my perspective, looking at this more, let's say, like from a theoretical computer science perspective or a mathematical physics perspective, you're going to want to eventually define everything in some kind of structural way, and you want to determine if this is a model of quantum computation or not. And so the subtle differences in this model between the gate model and this model, they appear to be very small, let's say at first, but they're actually profound. And so here we go. This is the main idea, the main excitement, where everyone says, oh, the field of quantum algorithms is now somehow completely different than what it was, let's say, 4 years ago, right? How did that happen? 5 years ago, 6 years ago? How did that happen? Well, somehow ideas from machine learning started to sort of appear into this theory and kind of merge together. And one of the main ideas of machine learning is you have a feedback loop to train a neural network, but in this case, we train a quantum circuit. Okay, that wasn't the only idea, but that was a powerful idea. And as we know, that was missing from traditional quantum algorithms, which were just viewed differently. And so we prepare a quantum state, we measure expected values, we'll talk more about that, then we compute a cost function based on repeatedly measuring this. So this process right here takes some kind of, there's some kind of extra iterations here to get these expected values out. Then we compute the cost function, and then we run the whole thing again and try to minimize some type of cost function. The measurements are done in terms of polystrings. The cost function will be discussed later. The outer loop optimization tries to find the theta sub star that will minimize the objective function, which we will now define. This is based on the following simplistic trick, which really does help quite a bit. So as you looked at in the prior slides, trying to simulate an H on a quantum computer was difficult. We had the gadget constructions, which required giant gaps. We have the circuit emulation using a Trotter sequence, which requires 1 million gates. But you'll notice the following: 21 on the right-hand side, we have an expected value of a polystring, which is some local measurement, product of local measurements. I can take this part and I can calculate this part on the quantum computer. Then I can merge this with the associated coefficient and I can calculate this objective function given these. And what that does, it makes it so I don't have to store this quantum state on a classical computer. I use this projected memory power of the quantum computer to do that and to calculate this expected value. And so I have to do some number of copies to get the tolerance that I want. But nonetheless, everything scales polynomially. And so this method of calculating the expected value is a fantastic method, which really opened up the door for a lot of things. Then the final thing that they had in their paper was the idea that every calculated expected value will be minimized, will actually have a minimum, which is given by the true minimum, which is over the entire vector space Vn. And this is the variational principle, and that gives a lower bound. And so this is why these algorithms are often called approximate algorithms, because we're not always sure, we can't always guarantee that we actually get the global minimum for realistic problems. And so equation 22 gives us some properties that, or it gives us a property that we can. Now, in the case that when we can construct the Hamiltonian ourselves, we can know that the minimum, for example, is 0 and that this has a non-degenerate kernel. And so in that case, we can make some type of assurance, and we'll look at that case. Now, what I wanted to do is I wanted to study this, and I wanted to prove that it was universal. Okay, and it turned out to be universal. So I defined the variational state space as all possible states, the union over all possible states that you can prepare. Then importantly, operator cardinality. So given a Hamiltonian, the number of terms in the sigma basis is called its cardinality. And those two ingredients, then I have the idea that I can replicate this state in trials. These could be some kind of time series. One could be done prior to the other. And if these evaluate less than some, if the expected value evaluates less than some chosen parameter delta, then we say that the penalty function accepts the state phi. Now we arrive back again at the kernel problem. And in this case, there's an additional constraint on the kernel problem, which will rule out the projector case that we mentioned earlier. And this is the cardinality must be some polynomial in the size of the gate sequence. Okay, but I'm still looking for a kernel that spans the output of the quantum circuit. We did this in two ways. The first way, I believe, is very interesting, yet it does not prove universality because it only allows some logarithmic number. Okay, and you can actually just write this, you could write this slightly differently, but we'll write it this way for today. So the logarithm, you have to have some bounded number, some fixed number, or some at most logarithmic number in the size of your problem, non-Clifford gates. And the reason why is the number of terms, the cardinality in the Hamiltonian depends exponentially on non-Clifford gates, yet is invariant under Clifford gates for some mathematical properties of them. This construction, although not universal, is quite nice because the Hamiltonian acts on n qubits, as does the state. I will not have time to go through the details of it, but it is quite simplistic. You have a projector onto all of the bits, which is local. And then you evolve this in the Heisenberg picture, which is an isospectral transformation, which means that you still have the same spectrum. And the kernel of this will be evidently satisfied. And we also have the eigenvalues as well. And importantly, you'll have the following situation for a Clifford gate. The cardinality right here in this equation, the cardinality is invariant under the Clifford gates for some mathematical properties that are given above. And going further, we want to remove that exponential dependence on the non-Clifford gates. For that, we had to turn to actually the history state, which appeared in Feynman and then later in Kitev's work when he modified this. And what we did is to kind of conclude the talk within the time window, we created a ground state which spanned all the computational steps, which is called the history state. Then we project onto the solution space where the clock register T is greater than some value. That can be applied to the stability lemma, and we can boost this probability by adding some extra number of qubits and some extra number of identity gates at the end. And of course, in the large limit of M, this thing approaches 1 quite well. And the probability of the circuit accepting the Hamiltonian accepting the circuit goes up. Now you'll notice that this Hamiltonian will have bounded cardinality, nice spectral gap properties, and it will act on, let's say, a few qubits. In the adiabatic case, because we don't have the access to the measurements where we can just make these strings easily, you will not have logarithmic qubits. You'll have a linear number. You'll have O to the n, not log n. So it's some exponential reduction in the number of qubits from the adiabatic case, which is interesting. Still, the construction's a bit convoluted. Nonetheless, that is the construction. Now, I will go now a little bit forward because we don't have quite the time for this. I will actually go to this part and I will mention one thing. If I give you a Hamiltonian and I say minimize it to find the output of the quantum circuit, that's an optimization problem. I have to be able to give you the control sequence or the gate sequence that will cause that Hamiltonian to accept. And that is done, and some people say, oh, this is cheating, but it's not practical, but mathematically it's fine. The gate sequence itself defines the Hamiltonian. The gate sequence itself defines the control sequence that's accepted by that Hamiltonian, okay? In practice, I'm not saying that a ansatz circuit of any length can minimize any Hamiltonian. Not at all. This is not true. And what I am saying is that if you have, let's say, no errors and you can do any circuit, then this model, which allows you to measure expected values in the computational basis and does allow you to only prepare an ansatz circuit, can in principle, if the ansatz circuit is long enough, which is some polynomial size depth and the size of the circuit, this is a universal model of quantum computation. With that, I now have finished at the correct time, I believe, and I will take any questions that people might have. And if there's no questions, I suppose that's also possible.
I don't see any questions.
Hi, Prasanta.
Yeah,
Hi, Jacob. Nice to see you.
Nice to see you.
Hey, so you said something about universality of VQA, but I think it was a little fast for me. Can you just broadly repeat the argument that you were trying to make?
Okay, so I proved that VQE was a universal, represented a universal model of quantum computation as follows. Given the description of a quantum circuit, I can find a Hamiltonian which has polynomial number of terms in the size of the quantum circuit such that the Hamiltonian's zero energy, lowest energy, non-degenerate ground space is spanned by the output of that quantum circuit up to some parameter, up to some small parameter that is up to some epsilon. The circuit itself provides a control sequence which minimizes the Hamiltonian. Okay, so in principle, it's universal, but as you can rightfully say, I'm essentially assuming the gate model exists, and in the sense that that I can actually build this circuit. Okay, so what I'm not saying is, given some k depth variational circuit, I can minimize any Hamiltonian, and that's universal. Like, I'm not saying that today's machines are universal. I'm just saying that this VQE put inside of this framework where you sort of define everything and you do the analysis, let's say, for lack of a better word, like correctly, if you do the analysis in some type of appropriate way for our setting, then you can get out this universal model. I believe people would expect it to be universal because everyone knows that minimizing Hamiltonians is QMA hard. Nonetheless, the analysis was lacking, and so I added that. And we've also added, let's say, a number of other things related to specific properties. But I recently gave a talk for the same host, and I gave a talk on the different effects that we discovered. And so this was a different talk, basically, because I figured there'd be some overlap in the audience. So this isn't my, this is like, maybe this talk's a little bit more theoretical than my other talk, actually. So, but yeah, it's a good question. Do you work on VQE at all?
You'll see in about 10 minutes.
Good. I look forward to it.
Very much. Thank you.
Thank you.
Okay, if there are no more questions, let's thank Jacob for a wonderful talk.
Yes, thank you, everyone.
Now, our next speaker is Sai, the person who was asking questions just before. Sai works in IIT Bombay, and he truly needs no introduction. Therefore, I am not going to introduce Sai. Sai, the stage is yours, and he works on very different things. And today he'll be talking about thermodynamics, I suppose. Please go ahead.
I'm actually going to talk about quantum control.
Okay.
Because I found myself to be in a neighborhood of people who are giving talks on algorithms. I thought that like all good children in the playground, I didn't want to be left out. Can I just get a quick check, Prasanta? I'm hovering over a screen which has your video on it. Can you see my screen here? And can you see my?
Yeah, we do see your screen. Yes.
And do you see the cursor moving?
Yes.
Okay. This is just a blank slide which I just snuck a zoom thing in. So thank you everyone. Thank you Subhashish, Narayan, and the other organizers for having us again at this wonderful conference. I think in 2019 I was there physically, and this cartoon essentially expresses that it's just not the same over WebEx. But here we are. We're doing the best we can. And so with that, let me just begin my my talk. So what I'm going to talk to you about is basically at the intersection of quantum control theory and NISQ algorithms. And so this is work that you can find on the archive here. And it's work that I did with a wonderful student, Guru Amsapalicherla. And so the title of the talk is Algorithmic Primitives for Quantum Assisted Quantum Control. So I'll explain every bit of this as we go along. So let me just begin with a little bit of motivation. You'll excuse, the experts will excuse the simplicity of the talk. Basically, I'm trying to make sure that people walk away with something, if not the mathematical details. So the way I would introduce the problem to you is basically I would say, well, let's just think about our kind of first college course on quantum mechanics. Usually what we solve is time-dependent Schrodinger equation. And when we solve time-dependent Schrodinger equation, what we're actually solving is the forward problem, basically. Oh, I forgot to turn on my video. You can see me, no, Prasanta? So you solve the forward problem of the time-dependent Schrodinger equation. And so the way I want you to kind of think about this is that I give you a bunch of control fields. This control field, sometimes I'll call it lambda, sometimes xi, and sometimes u. I'll change the name around. And I apologize for that. The control field basically is given to you, and given the control field, what we're tasked with doing is doing some sort of Dyson series, some sort of time-ordered exponential, and then we're just asked to solve the problem, right? And the various techniques and tricks involved in doing this is a good first course on quantum mechanics in college. So what I want to draw your attention to is basically the reverse problem of this, the inverse problem, which basically is the problem of quantum control, where basically instead of giving you basically the controls, which are now called xi of t, what I do is the following. I give you the initial state. I give you a target state, which is a special star. This is just a cartoon of Hilbert space, the special star, and I want you to go from here to here. Now, if you make a particular choice of control field, let's say you just want to switch on a static field and and that does this. Well, maybe if you switch on a sinusoidal field, it does this. There are some choices better than others, and to find the better choice is basically the task of the control field. And so let me just already claim to you that this is local optimality is all that I will ever claim in this entire talk, because otherwise you are getting into kind of complexity shenanigans, basically. Okay. So here is an example of a kind of control problem that that I've worked on so already a decade ago now. And so the problem is the following. So it's a very physical problem. So I have a mechanical resonator. So this is, for instance, a trapped ion. And there are the internal levels of the trapped ion, the electronic levels of the trapped ion, which are high frequency levels. So the red levels are much closer spaced in comparison to the blue. And the temperature scale, which is indicated here with this pink dotted line, is such that there is good thermal occupancy in the mechanical resonator. right? These are the conditions. It just happens to naturally be the case for trapped ions. Now, what I do is I couple these two quantum systems, the electronic levels and the mechanical levels. I couple them actually at the difference frequency with a flip-flop Hamiltonian. And what happens is that the excitations are driven from the mechanical resonator to the electronic resonator, and the electronic resonator is actually strongly damped. So it immediately gets rid of the excitations, and that's a way of cooling the system in steady state. Now, the point I want to draw your attention to is that this number G is actually very small, and it's kept small so that the rotating wave approximation can be applied to arrive at this flip-flop Hamiltonian. So and what that basically means is that this is actually a fairly slow process. The extraction of entropy from the thermal reservoir, the thermal state here is actually a fairly slow process. Now, what we proposed was basically a transient cooling method that actually bypasses this completely. And because this is all Gaussian states and thermal at some finite temperature T, basically you can just write the covariance matrix down, and the covariance matrix equation of motion is given here, and then we just applied a control theory solution to it. And what I just want you to see is that as time progresses, the control theory solution seems to do nothing, and then suddenly the population plummets. So this is the expectation value of eta gray is simply the average number of thermal excitations in this reservoir here. And what you can see is basically that the control sequence also looks pretty, pretty difficult to kind of guess. So this is not something that you could have simply guessed analytically. This is something that I just want to mention. Another example of kind of a control solution that I want to show off is basically another work that I did a couple of years ago with friends and colleagues, which is basically the exact opposite problem almost, which is I want to thermalize a qubit. So I have a quantum thermal machine. I'm running 4 strokes, let's say, of an Otto engine or a Carnot engine or whatever. And then in the middle of this, I basically just want to make sure that I thermalize, but I don't want to wait for the asymptotic thermalization. Thermalization is another of these very hard problems from a computer science perspective. So thermalization, exact thermalization takes an infinite amount of time, but epsilon thermalization actually takes a finite amount of time. If you just want to get into the epsilon ball of a thermal state, it takes a finite amount of time. So this is the epsilon thermalization optimal solution, finite time optimal solution for it. And you can see that the optimal field basically almost looks sinusoidal, but if you Fourier transform, there are kind of weird components here, which are these high frequency components here. And so again, the emphasis I want to place is that this is a whole methodology of finding optimal solutions, which is a little bit beyond just kind of intuitive guessing that we are very fond of in physics. Okay. So let me formalize control theory because I need this and I need some results and ideas from from the NISQ algorithms universe to kind of combine the two. So what I want to do is I want to bring up basically the notion of a control theory by formalizing this cartoon that I've just drawn in the previous slide. So what I again have is I have for some choice I have a suboptimal path and I have perhaps an optimal path. If I could, if I was clairvoyant, I would tell you that this is an optimal path. I could actually make it more formal by simply saying that, look, I want to minimize the distance to the target state. So I turn this into an optimization problem explicitly because I've been using the word already. And so I say, well, given a control field psi of t, which evolves the quantum state from the initial state to some final state, please minimize the distance to the target state. And that's a good enough place to start the story. All I want to add to this discussion is basically that experimentalists actually have not just the constraints that they want to optimize to the target state, but they also have other constraints attached to this. So alongside basically this condition that I expressed in the previous slide, that the final states overlap with the target state, which I've written as a target operator Q. So this is just a projector onto the target state. So if you see the bra or ket tau, it simply refers to the target state. T is for target. Basically this projector, I want to maximize the expectation value of this projector. It's the same thing as saying fidelity to the target state. Alongside this, there are other experimental considerations that also typically go into a control theory. So for instance, experimentalists wish to typically minimize fluence, which is the total amount of power that you're pumping into your whole experiment. And the reason that you want to minimize fluence is because when you just pump basically an NMR system, for instance, not only does do you do basically a pi over 2 rotation, a pi rotation, whatever on the NMR, you also heat up the environment. And so the heating up of the environment is a deleterious effect that you don't want. And if you just do unconstrained optimization, basically, then your sample heats up too much and your experiment becomes useless, basically. And so fluence minimization is essential to keep us on the quantum side of things. And likewise, bandwidth constraints are placed typically to kind of reflect the fact that experimental systems have constrained bandwidths, so on and so forth. This is not the only two, but these are the two major ones that one considers typically. And so instead of just writing the expectation value of the fidelity, instead of just writing the expectation value of the target operator, which is the same as the fidelity, what I will write is basically a complicated cost functional, basically J. I'll always call it J. And J simply refers to basically a cost functional that incorporates all of these different constraints. And I want to maximize this thing while minimizing a bunch of other things. Right? Again, let me show you a very practical example. So this is from a very famous paper by Zhu and Herschel Rabbits, from many, many years ago. What they were doing was they were considering basically the OH molecule in a Morse potential, and they wanted to raise the particle expectation value from a point x naught to basically a point x. So they have an operator x, which basically peaks at a value x, at a value x prime, sorry, and they want to basically optimize the overlap to that operator x. So this simply you achieve this if you basically if you think of the center of mass of the atom being co-located at x prime, and they want to do this. So this this represents basically maximizing fidelity, and at the same time they want to minimize fluence, which is the thing that I just told you before. So as power, basically it's given by the square of the control field, because the square of the field typically goes into the power calculation. So you want to maximize the fidelity while minimizing fluence, so you put a minus sign there, and this is a Lagrange multiplier that simply tells you the relative strength of the two constraints. If alpha is 0, alpha naught is 0, then you don't care about fluence at all. This is not a problem that heats up, and only worry about fidelity. If alpha naught is fairly large, then you care a lot about fluence, and so it has to be kind of optimized alongside fidelity. It has to be negotiated alongside fidelity. So that's the way to understand this cost function. Okay, so how do you basically go about setting up these control solutions? So let me show you three important examples. In fact, I won't tell you the third one, but I just write it here to say that this is also something that we've considered. So the first is basically variation algorithms, and this is in fact what I'll spend some amount of time talking to you about, and also gradient algorithm, which I won't talk to you much about, but it's actually in the paper, and non-gradient algorithms, which are also in the paper. So the reason I bring up non-gradient algorithms is basically for those of us who are, for those in the audience who are experts on VQAs and NISQ algorithms, there are these barren plateau, so on and so forth issues, which basically you can bypass by going into this universe. So I just say that to pique your interest. Okay, so just again, I apologize to everyone here basically, but I'm reminding myself as to how I do variation principles to begin with. So the first thing I write down is a Lagrangian. So, I'm just going back to classical mechanics 101. And then what the crucial thing I just want to remind everyone is that you can incorporate, certain kinds of constraints by basically a Lagrange multiplier technique. So you simply, if you have equality constraints, fi of q comma t is equal to 0, so semi-holonomic constraints, for instance, in classical mechanics, you can incorporate them into basically the paradigm of the Euler-Lagrange equations and Hamilton's variation principle by simply multiplying f with an undetermined Lagrange multiplier chi, and chi times f basically enters the modified Lagrangian basically. So L plus chi times phi is now the new Lagrangian, and now what you do is you write the action as basically the integral over the new Lagrangian, and you set delta s equals 0, and you get the Euler-Lagrange equations. And the Euler-Lagrange equations you get not only for the coordinates q, but also basically for these undetermined Euler-Lagrange, these undetermined Lagrange multipliers chi. So you have n coordinates q, and you have m additional Lagrange multipliers, and you get n plus m equations, which basically when you solve together, this is the same thing as solving the constrained Lagrangian problem, right? So this is basically in Goldstein and other places. So this exact spirit is exactly what we're going to borrow as well in the control theory solution that I'm going to talk about. So what I do here is basically I write formally my cost function j. This is the same thing as writing the action, which is basically the fidelity at the final time. So this is the target state tau. I remind everyone. So that's that little star on that cartoon that I showed you. This is the final state to some, if I made some arbitrary choice of control, that's my final state. And then what I have to do is I have to enforce Schrodinger equation. I can't just be anywhere in state space. I have to be in state space at a point which is consistent with the fact that I evolved with the Schrodinger equation. So how do I enforce the equality constraint? So this is basically I psi dot is h psi, or this operator del t plus ih is basically should be a zero of this. Acting on psi should be zero. Because it's a zero, I can incorporate it by a Lagrange multiplier, right? So this Lagrange multiplier, which is a scalar function chi, becomes a bra chi. I use the same letter chi just so that I give you that little familiarity. So this chi is basically what is called a co-state or Lagrange multiplier. It's the same phrase used in the control theory literature as well. So this expectation value, this transition amplitude basically is always zero if Schrodinger equation is obeyed, right? So that's the way to think about it. So over time, at all times it has to be true. So I integrate over time, and then I remove the fluence term as well that I want to minimize. So these three terms basically are just the representation of the thing that I want to minimize. And again, what I do is I do first order variation of the action to be equal to zero, but the action now depends on three functions. So it depends on the quantum state psi. It depends on the co-state chi, which is just the Lagrange multiplier, and it also depends on the control field that I'm trying to find, which is this psi, right? So these three equations, basically equal to zero equalities, produce three equations, and these are the three equations that I'm just showing you. So the first one is actually just Schrodinger's equation. I psi dot is h psi. I've just written this out. Ignore the k just for the moment. I'll get back to it in a second. And the initial condition is psi at time zero is the psi zero that you gave me, right? You have to give me, remember, in a control theory solution, you have to give me the initial state and you have to give me the target state. So the Lagrange multiplier equation actually is I chi dot is h chi. Again, this looks exactly the same as Schrodinger equation, with one crucial difference, which is that the Lagrange multiplier equation, the co-state equation, is actually specified not at the initial time, but it's specified at the final time. It's specified at capital T, right, at the final time of the constant time control that I'm trying to perform. So this Schrodinger equation is actually traveling backwards in time. So you have a Schrodinger equation traveling forwards in time, which is this first equation, and a Schrodinger equation traveling backwards in time for the co-state, for two different quantum states here, right? And they meet at time t basically with this overlap equation, which is in this yellow box here. And this overlap equation is the update to the control solution. Chi is the control that it's the thing that I desire to find. And so this control solution is basically just the imaginary part of some overlap. So the only thing I want you to take away from it is that there is the quantum state psi up to time t, there is the co-state chi up to some time t, and then there is the operator mu, which is the control operator. So my control theory is given by h0 plus magnetic field times dipole moment operator or something like that, right? So mu is the operator that I'm interested in, and pi is the control field. So the control field is simply given by the expectation of the overlap of basically the state and the co-state in this operator mu. Okay, so now let me explain to you what this variable k is. Just like in Hartree-Fock theory, this is a self-consistent solution. So the solution depends on the problem, which depends on the solution. So you can see that psi depends on the Hamiltonian, but the Hamiltonian itself has the quantum state, has the magnetic field psi in it, but psi itself has the quantum state psi in it. So psi depends on itself non-linearly. And so the way you solve it in Hartree-Fock theory is you make a guess, and you feed that guess in, and you just iterate over and over again. And every time you iterate, you get a better and better solution. Same as in Ritz variational principle. You feed a solution and you iterate over and over again, and you just get a better and better solution. So in exactly the same way, all that I've done is some of these I've called k, and some of these I've called k minus 1. And what this does is it allows you to start somewhere and simply iterate the whole problem over and over again and solve the problem. So if I was to put this in a box, like I was doing a programming course, so this is the way I would write it. I won't talk about this, but I just want you to see the two crucial things that I want you to take away from this is that there is a forward and a backward evolution, always in Krotov, and there is an update of the field term that you have to do, which is basically this overlap that you have to compute. This is actually very generic of variational principles. Variational principles always end up having a forward step and a backward step. And so this is something that I just want to emphasize. Okay. So with this, let me actually introduce you to another very famous algorithm, which is a gradient ascent pulse engineering algorithm, which was tailor-made for NMR and then became very famous everywhere else by Naveen, who's actually at IIT Bombay. So this basically works as follows. So what Naveen and his co-workers did was they said, well, let's just directly optimize the thing that we're interested in, which is the fidelity, right? So this is the fidelity to the final state. Let's just optimize this. This is the cost function J, right? And so their controls are typically called U, and just to kind of keep with their notation, I've just used U here as well. So what they do is they say, well, look, what is the evolution equation? Is I psi dot is H psi, and so H is just some linear sum of Hamiltonian terms. Okay. So what are the steps of grape, which basically I again want to just bring up just to kind of emphasize one point. The steps of grape are basically that you just write the final state down as basically the initial state times a piecewise constant Hamiltonian. So I take my Hamiltonian controls and I apply them as piecewise constant terms, and then I multiply from the right to left, and that's my unitary evolution operator, and I apply the unitary evolution operator on psi naught, and that's psi of t. So what that means is that the overlap with the final state is that quantity. And most importantly, I can break this product K going from 1 to K max up to some K1. So K to K1 and K1 to K max. So I've done nothing here. I've just split it into two. One I've written in light yellow and one I've written in turmeric, basically color. Now what I can think of is I can think of this turmeric color as actually a backward propagating solution up to time t. And this is a forward propagating solution up to time t. Why would I up to time k in this discrete index? Why would I do this? The reason I would do this is because if I was to basically take an analytical gradient of this, right? If I was to actually try and compute the gradient and the Hessian to try and compute a grape walk, which is what they do, they just do gradient descent. Then dH by duk is basically just because my Hamiltonian is of the form xi times mu, it just produces one static operator. It just produces a time independent operator. And so one operator comes and sits here, and you have a forward evolving quantum state up to time k1, a backward evolving state up to time k1, and an operator sitting here that you have to take the overlap with. So it's the exact same as Krotov. This is the only thing I want you to take away. So the exact same thing that appears in Krotov, a forward evolved state appears here, a backward evolved state appears here. The difference is that that was for Lagrange multiplier, this is for the target, and an operator expectation value appears here. There it was for the static operator, and here it is for whatever the time dependent operator is that you choose, basically the kth operator that you choose. So that's what's said here. And so what I want to basically point out is exactly what I just say in this slide, which is please note the universality in both of these algorithms, and essentially this is what I will build off of, which is that there is always a forward and a backward evolving set. And then there are two things that I have to compute. I have to compute state overlaps, and I have to compute transition amplitudes. So if I take this operator, which is in light yellow here, if I take this to be the identity operator, then what I'm computing is basically the overlap between two quantum states, arbitrary quantum states. If I take this to be a non-identity operator, I'm computing a transition amplitude. If I have these three steps, if I can forward evolve, backward evolve, and do this, I can do all optimization, right? This is the whole story. Now, let me bring in basically the thing that is of interest to many of us in the recent times, which is the fact that many body quantum systems exist and NISQ devices are noisy. So the point is, the question that you can ask is basically you can say, look, these simulations become harder and harder to do. Basically, if I'm in a many body context, tomographic measurements are impractical. They're very, very costly. Can I replace some of this stuff with NISQ simulations, basically, right? Can I do this? And if I can do this, maybe I get away with kind of a lot. And what I hope to show you is some answer towards that. We think that indeed the answer is yes. Okay, so let me just also show you the real kind of true context in which I think you should think of this problem. it's not just kind of trying to, let's say, cool a nanomechanical oscillator to the ground state. It's not just thermalizing 1 or 2 qubits. It's problems like this. So this is one of my favorite papers. It's a very, very nice paper by Luis Santos's group. What they did was they considered the Bose-Hubbard model, which is basically bosons hopping in an optical lattice like this. And these bosons can basically exist in one of two phases, typically. One of these phases is what's called the Mott insulator phase, where you have one egg per eggshell, per carton, per hole, and they're basically in an insulating phase, which means they can't move. And the other is basically the superfluid phase, where they basically can just hop around and they're bosons, so multiple ones can occupy a given basically hole. So the superfluid to Mott insulator transition is kind of a famous problem in condensed matter theory. It's studied in many textbooks. And what you see is a phase diagram with respect to the parameters J, the Coulomb repulsion U, and basically the chemical potential mu. You'll see basically phase diagrams like this telling you that there is a Mott insulator to superfluid transition, basically. Okay, so far so good. Now, what Luis Santos did was he basically promoted this U to a U of T, a time-dependent Coulomb repulsion term. And they can do this because they can take these optical lattices and they can jiggle them basically up and down. And so they can promote basically one of these things to a time-dependent term, and then they can transform it or look like it's a time-dependent term on something else, blah, blah. Some technical details here. But just imagine that you can experimentally do this. Now, what Luis Santos did was he actually proposed, the paper did was they actually proposed a very specific form of U of T. They said U of T is U0 plus sum over L, UL cosine L omega T, and UL has some specific form attached to it. And what this does is it simply turns it into a time-dependent Schrodinger equation problem. It's a forward problem because you've already told me what the control you're applying. All you want me to do is solve this problem, and because cos L omega T is periodic, it's actually amenable to a Floquet theory solution, and so they solve it using Floquet theory. And they point out that there is an effective Hamiltonian underneath, the Floquet Hamiltonian underneath, which actually produces not just the Mott insulator and superfluid phase, but also a pair superfluidity phase. And the pair superfluidity phase is characterized by the expectation value of A square being non-zero. So it's like a squeeze state for quantum optics, for those of us who are familiar with that language. And so what they showed was that by driving an optical lattice, you can actually drive a Bose-Hubbard model into something that's the many-body analog of a squeeze state. And that's very exciting. But if Luis Santos wasn't around to tell us that this is exactly the solution that will get the job done, if I only gave you the target and the Hamiltonian, if I told you, you can do whatever you want with this Hamiltonian, but please produce for me a pair superfluid, it's near impossible for you to produce for me a pair superfluid. It's a very, very hard problem to solve. And so what we're hoping to do is basically provide a solution which goes towards addressing that issue. Okay? And what's the big issue here? The big issue is basically Hilbert space dimensionality. Hilbert space dimensionality being a big issue means that simulations are a big issue. Classical simulations are a big issue. And if you want to replace them with quantum simulations, measurements are a big issue because you still have to measure a tomographically large number of components. Okay. From this perspective, let me show you a previous approach. So this is a hybrid grape algorithm. So I showed you the whole grape machinery. You take the fidelity and then you make derivatives, and there is a state overlap, and then you have to a transition amplitude estimate, transition amplitude that you have to estimate, and then you optimize around it. So what these folks did, Lee and their co-workers, what they basically did was they said, look, what is the fidelity that we're interested in? The fidelity is the expectation value. It's the overlap between the density matrix at the final time and the target density matrix, which they call rho bar. And the target density matrix, they insisted, should be basically writable as a sum of a sparse number of operators, sparse set of operators. So x times xs times ps, where xs are some numbers and ps are a sparse set of operators. And if xs times ps, if ps is a sparse set of operators, then what they basically insist is that you just tomographically reconstruct the target state, and once you have the target state, you can compute everything. The final state. And once you have the final state, you can basically just reconstruct this fidelity estimation, because it's just the trace of RF rho f times PS. So take these measurements, right? So measure the density matrix, the final density matrix in the PS basis, and then reconstruct the fidelity measure and run it that way. What this basically means is that this is only run for a small sparse set of matrices, which is classically simulable. So it, in fact, I think begs the question, why would I want to do this on a quantum computer, right? And so the truly dense problem, the problem that's actually difficult to do is exceedingly difficult. It's essentially order 4 to the n measurements. And so, you have a little bit of a tension there between what is solvable on a classical computer and hence unnecessary, and what is necessary but truly difficult. Okay, so you're already seeing that I'm kind of slowly making my way towards ideas that are related to NISQ algorithms, to variational quantum algorithms, so on and so forth. And this is not by accident. Indeed, what I just want to point out is that NISQ algorithms are just the other side of this coin, right? And so you can see this very nice PRX quantum by Herschel Rabbits and their co-workers, where they basically point out this thing that that was evident to me for several years now, which is basically that quantum optimal control and variational quantum algorithms are basically two sides of the same coin. So you can think of quantum optimal control as a pulse level design of basically of a quantum circuit, whereas basically you can think of variational quantum algorithms as basically a circuit level design of the same circuit. And so to create an experiment, you can approach the problem either way. And so what I'm hoping, what I've been doing recently is basically trying to learn from the VQA literature and the community that is coming up, the kind of essential problems that they have, and trying to bring the optimal control theory and its ideas to it, And so the rest of the talk will be about that. Okay, so let me just make one or two comments about variational quantum algorithms in case some of our colleagues here are unfamiliar with it, and students, of course, which is basically, it's based, just like Jacob just mentioned, it's based off of the Ritz variational principle. So, you've studied this in your quantum mechanics course, which is basically that the ground state estimation can be done by using this estimator. This is the cost function in my language. And what you do is you simply minimize. So this psi lambda is a parameterized quantum state. So you just write a psi with some parameters lambda. I'll show you how in a second. And then you demand the expectation value in the Hamiltonian, and you basically minimize this. And this minimization program is always upper bounded, basically lower bounded by the true energy, which is basically the variation principle. Okay, the Ritz variation principle. Now, usually, what I want to emphasize is that usually we just do it on paper. The helium atom, for instance, we just do it by hand, or we do it on a classical computer for slightly more complicated problems. We just do the numerical minimization, right? And this produces fantastically good results for small physical systems. So the idea is basically to replace this estimation part basically with a genuine quantum computer. So get a quantum computer to spit out this number, and then by the way of an experiment, and then once you've dealt with this red line, you have a classical post-processing step which basically optimizes the problem and returns basically the newly optimized. So once you've optimized it, you've changed the variables a little, and you return the newly the new variables, and that's the way you've updated basically psi lambda, and you can go through one more cycle if you feel like it. Exactly like it's variational, you just give it one more iteration, it gets better. Yeah. Now, how do you parameterize psi lambda, right? So for instance, what you can do is you can write psi lambda as a product over some algebra OK times lambda k. So for instance, if you're just preparing SU2 states, sigma x, sigma y, sigma z with some parameters lambda 1, lambda 2, lambda 3. And that's a parameterized quantum state, psi parameterized by lambda. And now you can take this entire thing up to on some initial state, and you can feed it into one such algorithm, right? So a key step to many of these algorithms is, number one, to prepare this quantum state. Number two, to measure the desired result, right? Because the expectation value of the energy must be something that you can easily measure, because otherwise then you're stuck. You're back to square one, basically. And let me just say, there are basically in the update part of the program, there are basically many ideas and new techniques that have come up. So there is gradient versus non-gradient methods, and this I emphasize only to kind of point at a particular subsection of our paper. And key NISQ issues which have come up in the recent past, basically things like barren plateau, which are cousins of local minimization problems and flatness problems that have existed in classical control as well. Expressibility versus trainability, so on and so forth, all have kind of cousins in this universe. So some of them have cousins in this universe, which also have to be discussed. Not only that, there are, I think, opportunities as well. So Jacob also pointed this out. This hardware efficient ansatz. So ansatz, which basically have have been driven basically by what is experimentally possible, I think are also kind of very good ideas that have not traveled in the opposite direction to quantum optimal control, or are rather only traveling now to quantum optimal control. And so I think that direction is also kind of a very interesting direction to take. Okay, so I need one more idea from this whole NIST literature. So I borrow it and I show you the idea just for completeness. And this is due to Andrew Childs and Nathan Weed. And the idea is basically that most operators that you're interested in writing, the expectation value, transition amplitude, doesn't matter. Most operators can be expressed as the sum of basically some scalar coefficients times polystrings. And polystrings are basically unitary operators. You can implement them on a quantum computer. If I have, let's say, sigma x tensor identity, that's implementable on a quantum computer. Sigma x tensor, sigma y tensor, sigma z, that's implementable on a quantum computer. So you can break this x into x, x sub k times sigma sub k, and you can then use it to basically you just push the sum outside, and you can measure. You can take up psi lambda. You can rotate it with sigma x on the first qubit, sigma y on the second qubit, so on and so forth, and then you can just measure the overlap with psi again, and this number will just be known to you, and you can reconstruct via LCU basically this operator expectation value. So operator expectation values, at least for kind of LCUs which have a small compact description, are experimentally kind of achievable. Basically, this is the whole point I just want to make. Okay, so I apologize. There's a lot that I'm throwing at you, and so I just want to summarize. I kind of just want to pause for a second and summarize the key things that I want you to take away. The key things are the following. Number one, quantum control basically produces equations like this. I don't expect you to remember them. The only thing I want you to remember is that there are two crucial varieties of things that that we end up with. One is basically you have to end up with state overlaps, and you can see these are two Schrodinger equations. But if you look at this, this is Q is, remember, it's a projector onto the target state. So I need the projector onto the target state acting on a quantum state, which involves an expectation value. So I need state overlaps for running equations like this. I need to be able to run them. I can run the quantum simulation on a quantum computer. This is, I just assume this for the moment. The second variety of beasts that I'm interested in is transition amplitudes, which are also basically things of this sort. So I have a backward evolved state, a forward evolved state, and then I need to basically just have an operator in the middle that I basically take the sandwich of. So our solution, so let me just flash our solution to you in the form of a kind of written up algorithm. Our solution is to propose two algorithmic primitives. We call them primitives because they themselves are not the Krotov algorithm or the Grape algorithm or the Crab algorithm. They are used to build these algorithms. They're primitives for the algorithms, right? So just as the quantum Fourier transform is the primitive basically to construct the Shor's algorithm, these are primitives that once you use them, you can construct bigger algorithms out of them. So algorithms sit on top of these things. So the first one of these is called an overlap estimation algorithm, and the second one is called a transition amplitude estimation algorithm. They're written up formally here, but I will just explain them to you in more physicsy terms as we go along. But what I want to basically tell you is kind of give you a broad overview of what is the structure of our algorithm, of our algorithmic primitive. Our algorithmic primitive can be broken up into three boxes. The first box is that we require a bunch of quantum resources. So we need actually the target state that we're trying to optimize to, right? And you can say, what does that sentence mean, basically? So remember that when I basically demand that you produce an optimal solution for me, it does not mean that no solution exists whatsoever. It simply means that I'm trying to speed up the process for whatever reason. So if you give me a bunch of offline resources, which are basically the target states, then I can make you a much, much better, much more efficient target state preparation machine. So I need the target state as one of the quantum resources. I also need the Hamiltonian encoded as basically either an LCU or a block encoding or a thermal encoding, whatever you want. And we discuss all of these in the paper. And we need the initial state, of course. So these are three quantum resources that are required. And their input into a quantum processing machinery, which involves two things. One is just a standard evolution using a digital quantum simulator. So there is trotterization and measurements here, and trotterization steps here. And then there is a measurement step, basically, which I will discuss in a future slide. And this measurement step, what it does is it computes the overlap or the transition amplitude. And it returns the overlap or the transition amplitude for a classical post-processing step. So it looks very, very similar to a variational quantum algorithm, for instance. But with the key difference being that we're not trying to optimize over states, we're trying to optimize over whole paths. We're trying to actually get optimal control solutions, basically. Okay. The thing that I wanted to say, again, as a side note and as a cautionary tale, is basically that the fact that we need offline resources is a good thing. It somehow keeps us honest with respect to complexity theory. So if there are difficult to produce ground states, if there are Hamiltonian ground states that are difficult to reach, blah, 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 then we die, basically, because we're not able to do better than basically what is allowed from a complexity theory point of view. And this is a good thing. Otherwise, you absolutely should not trust anything we're doing. Likewise, what I will say is that there are also opportunities here. So there are 1D and 2D tensor networks are basically things that we can handle on classical computers. 3D tensor networks are actually simulable on linear optical quantum circuits, basically. So Martin Plenio's group actually has a very nice paper on this. So what that means is that nested interferometers can generate 3D tensor networks, which are outside the classical set of simulable quantum states. And so what this means is that we also, in the near term, might have opportunities where we could have very, very interesting target state optimizations that we can do on linear optical circuits that we then transfer over to a trapped ion, or we transfer over to a superconducting device. And so we can share basically quantum resources across physical systems. And this is something that this system allows, because what it does is the optimal control solution is the same if the Hamiltonians underneath are the same. So once you're able to normalize to some basic Hamiltonian that you can implement on any of a couple of different physical systems, you can transfer solutions over to those other systems. And we're hoping that this will have applications in gate compilation techniques. So one of the ways in which I think this will be interesting is that it can be used to basically find compiled Grover search algorithms and so on and so forth. So there is kind of some very nice ideas here, which I think very nice ideas here. Okay. And the very last kind of apology for this paper that I will give you is basically a kind of a paradigmatic statement. So another way of kind of stating what we are saying is basically I point you to this very, very nice paper by a bunch of people, including Michel Lucan, about basically designing quantum circuits. And basically what they say is the following. They say a full quantum computer stack basically has several of these layers. It has a qubit technology, control engineering, which is perhaps part of today's talk here, quantum software and algorithms. And what they basically say is that there are two big challenges. The first challenge is basically that entanglement and kind of delicate quantum systems can produce very nice results. But the full set of applications that can exploit entangled superpositions, it's not clear what they are, and it will be nice to find them kind of. The second is quantum computers are notoriously difficult to build, and extreme isolation is required, blah, blah, blah. So what they basically propose is basically what they call a co-design paradigm. And the co-design paradigm is you take both of these into consideration. So you design computers to respond to problems, and you design problems to respond to, to take into account the available hardware resources. So in that exact spirit, I basically want to say that our solution that I'm going to show you in a couple of slides from now calls for basically adding two things to the control and the hardware. On the control side, I'm going to show you basically a nice little trick, which basically uses a limited swap gate and control swap gate, and is able to basically construct the overlap of unknown quantum states. Unknown will become interesting and important for a reason now. And the second is basically I'm going to propose basically redesigning the swap test implementation. So adding arbitrary controls, basically, there is a very nice solution by Tim Ralph, which involves increasing the internal Hilbert space of quantum systems. And by increasing the internal Hilbert space of quantum systems to go from qubits to qubits, basically, you can actually add controls with polynomial depth, basically, and in fact, linear depth. And so these two solutions combined together, we think, are a co-design approach basically to the problem, and would perhaps this or its cousins would basically be useful ways basically to do to custom engineer quantum control machinery, which basically can then optimize modular quantum computers. Okay, so let me explain the solution now that I've advertised it in several different ways. So what I will show you is optimal, so overlap estimation algorithm. So this is one of the two algorithms that I promised you. Overlap estimation algorithm via basically Hadamard testing. And so the way I'll do is I will just assume Hadamard testing. I'll just work my way down this thing. And then every problem that comes up, I'll just keep solving it. So I'll show you all of the solution, including the Hadamard test, but just bear with me for the moment. So if I have a quantum state X, which is basically 0 times psi plus 1 times chi, then basically I can find the overlap between psi and chi. This is easy to do. And overlap between psi and chi, for arbitrary psi and arbitrary chi, would just solve the overlap estimation problem completely. So I can imagine psi to be basically some unitary u acting on psi 0, and chi to be some unitary v acting on chi 0. Of course, we know that u and v are the forward evolved part of the control solution, the backward evolved part, but forget about all of that for now. We come back and plug those in as special cases of the solution, right? And so I imagine basically u and v to be basically some digital quantum simulation representation. So the big problem is the following, which is I don't know u. I can't write u and v down because they're actually on a quantum computer. They're just pulse sequences that I've given on basically tons of operators that don't commute and so on and so forth. So multiplying these matrices out is the big problem. I don't want to do it. So how do I superpose two unknown unitaries acting on two known states? Basically, this is the question. Because I know psi 0 and I know chi 0, but I don't know psi of t and I don't know chi of t. Now, how do I deal with this problem? So the way to do this is actually something that came up for completely different NMR-related reasons by Osmaniak, Horodetsky, so on and so forth, and was implemented by a Rayleigh-Flams group in this paper. So these two papers are the references for that, and basically it's just algebra. So I'll run through this. Prasanta, so I have 15 more minutes total, right? 5 plus 10.
Yeah.
Okay, so I'll try and finish up quickly. So the idea is basically that if you give me a quantum state phi 1 and phi 2, and I want to produce a known superposition alpha phi 1 plus beta phi 2, then what I need to know is I need to feed this quantum state alpha 0 plus beta 1 into a control line here. So alpha and beta are part of the things that I demand. They're here in red. Phi 1, phi 2 are also here, so they're here. Now, what I need to do is I need to choose these two operators, p mu and p zeta, which are the two projectors. I project this quantum state here, and I project this quantum state, and conditioned on those two projectors clicking, I basically have my quantum state here. And all that these authors point out is how to design a mu and zeta to be such that this thing works. So the way that this thing works is let me just quickly just tell you what the trick is. You can just work basically p zeta here, and once you work out p zeta, what happens is basically that you have zeta acting on one Hilbert space and basically mu acting on another Hilbert space, right? So mu acting on another Hilbert space, and what you can do is you have these degrees of freedom, mu and zeta. You can choose such that mu expectation value on 0. Mu overlap with 0 is the same as zeta overlap with phi 1, and mu overlap with 1 is the same as zeta overlap with phi 2. So you can choose these two. So all you need is some partial information, which is you need to know the overlap of this zeta on phi 1 and phi 2. If you know the overlap between these three operators, then you can just do the whole thing. This is the whole story, basically. And then what happens, you can just work out that it just drops out and you get the thing that you're interested in, right? So it's a very simple solution. So what we've done is we've basically incorporated that whole machinery in here. So this is a controlled swap test along with p zeta and p mu, and my quantum state psi and target state tau are sitting here. But on top of it, I've also incorporated ancilla lines 1 and 0 and 1, which I've indicated in red. And what the 0 and 1 do is they basically either run control on 0 or control on 1. And when I swap, basically what happens is I swap 1 tau to here and 0 1 psi naught to here. So when I swap, this control gets activated. So when it's 1, tau is acted upon by V. When it's 0, psi naught is acted upon by U, right? That's the way to read this. And then there are some spurious phases that you have to correct for in the overlap estimation, which is this theta sitting here. So once you do all of that, if you project onto the correct basis, then basically once you project these three projectors out, you basically get the exact quantums, the overlap estimation that you're interested in, basically. So this is exactly the solution that I just want to point out to you. So the second solution is basically is an engineering solution. It's a hardware solution. And the hardware solution was in a very nice paper by Tim Ralph's group almost 10 years ago again now, which is basically that if you have, if you're interested in doing a control operator O, a control unitary O on many lines, this is of course VQA tries to avoid this at all costs. NISC algorithms try to avoid this at all costs because it's actually very costly to implement on just a universal quantum computer. Our solution is don't do it that way. Actually do it by just at least for the control, designing control protocols, custom design your qubits. And I'll show you how you actually don't need to do any work per se. Well, you don't need to do any hardware work per se. The idea is the following. So you propose an internal swap gate XA, and what the internal swap gate does is if you have a qubit level, 4-level atom, which has the energy level 0, 1, 2, and 3, what it does is it simply swaps out the 0, 1 level for the 2, 3 level, right? So, and the 2, 3 level for the 0, 1. So it just, I have a 4-level atom like this, and it just simply swaps them out like this internally inside a physical system. Now, let me just remind everyone that important physical architectures for quantum computing, like superconducting devices, are already anharmonic oscillators. So we can actually address multiple levels. They're not just stuck with 2 levels, and the multiple levels are natively available. You don't have to do any work basically. All you need to do is build the microwave, control sequences to address the next 2 levels, incorporate the next 2 levels into the whole story. As opposed to just leaving them out right now. And so if you do this, then what Tim Ralph's analysis proposes to you is basically that by simply adding just a linear number of lines here. So if let's say I have 3 qubits that I want to basically perform the control on, then I simply add 3 lines here and 3 lines here. So twice the number. By just adding a linear number of internal swap gates, I can actually implement an arbitrary uncontrolled unitary. I can concatenate with basically these internal swap, and that's the same as doing this. Circuit diagram A is the same as circuit diagram B. So what we did was we combined all of these ideas together and basically made a proposal for this kind of a device, which basically what it does is this part of the circuit, which is the dotted blue line. Basically, what it does is it prepares the superposition of the unknown quantum states. This U, V, mu, this mu L is basically the linear combination of unitaries. So if you add this line, you can actually even do transition amplitude estimation, because now the transition amplitude simply comes as one Hamiltonian that whose linear terms that are sitting here. So we also have this thing that it should be expressible in a small number of terms. And then by basically performing just ground state measurements, you can completely bypass tomography, and you can simply collect all of the data that you need to actually run the quantum computer, the quantum control solution, just out of binary numbers, basically. So you don't need any tomographic data. You don't need, essentially the bottom line is basically we only need transition amplitude, one transition amplitude specifically time series, and one state overlap time series. We don't need the full tomogram of the problem, and so we just bypass the tomogram by basically just designing our way to it, basically, by doing a combined software hardware design to it. Okay, so how does our machine look? So our quantum assisted Krotov algorithm, for instance, first has to evolve basically a psi dot is minus I each side. So the way we do it is by using a digital quantum simulator, and so we replace the true unitaries U with the trotterized unitaries WI. Now they come with additional indices JK, because there's actually the jth, the kth run and the jth time. So there is a time index sitting here on the bottom. And then basically we compute the overlap and the transition amplitude by using the techniques that I've explained before. And then we are able to kind of just do feedback on this, basically. So this is the way this whole thing runs. Okay. So let me just make 1 or 2 more quick statements, and then I stop to take a few questions. So let me remind you that basically I've replaced U and B with trotterized versions, and so I need to discuss errors. Let me just do it offline. So the errors come in two varieties, well, two that we considered. One is totalization errors, and the other is the fact that you have a finite number of measurements. You don't have an infinite number of measurements. And so the way we incorporated totalized errors is by following an analysis from the late David Poulin and Rolando Somma, Verstrate, basically, and it simply points out that that the ratio of the total volume of a d-dimensional Hilbert space to the epsilon ball in the d-dimensional Hilbert space is exponential, basically. So this ratio being exponential can be leveraged to basically construct a number of gates that are required for any given totalization up to some finite error. And so we use that and back calculated, basically incorporated this analysis. So what is the norm between the unitary and the totalized unitary? Basically, what is the difference in these two unitaries? If this is set to some epsilon, how many gates do you need? So this whole analysis we followed. And let me just tell you qualitatively what happens. My cost function basically in Krotov, I didn't mention this to you, but this is true, is actually what is known as uniform convergent, which means that every time that you run Krotov on a classical computer, the Krotov algorithm actually either keeps the cost function the same or it increases the cost function. So it just keeps climbing up like this or saturates and climbs up a little bit more. There is a band which represents this yellow band, which basically represents the fact that I have finite errors. And these errors creep into the controls, and the controls creep into the quantum states, and the states creep into the overlaps. And all of this this error keeps creeping in, basically producing a band. And this band basically will tell you where the optimal number of times you can run this algorithm. So K max is basically this x-axis, and it's the point where you're going to get cut off by, so you climb, and every time you climb the delta JK, the climb is large enough that you basically are outside this band every time. And then at some point you hit the band, basically, which is your next overlap is in the band and you can't say anymore because you're not uniform convergent anymore. And this analysis we've actually worked out in the paper as well. But let me end by just showing you a numerical example. So what we did was we took a single qubit optimization to go from the state 0 to the state 0 plus 1 divided by square root of 2. And what we did was for 0 error, you can see that you have basically perfect overlap here. And then as we increase error, basically, you can still see basically that the algorithm does fairly well for increasing noise levels. So it doesn't do very well for very, very large amounts of noise, but this is the analytical analysis of this is essentially in the paper, and the corresponding noise fields. You can see actually that this is the kind of worst. I mean, it has no relationship to this. It's so noisy that you have no. And we did the same for 2 qubits as well. I mean, the whole point about Minsky things is that you can't really simulate large numbers. But we did this for 2 qubits as well. And likewise, basically, if you take an optimal control and you add actually a fair amount of 1% noise to it, basically, our algorithm is still fine. It goes from something 10 to the minus 4 to something 10 to the minus 4. You can barely notice it, basically. And so if we dump it by a factor of 10, then you start noticing some decrease in the cost function, basically. But noisy gates are basically, I think, at 0.05% errors, and so this is okay. Okay, so let me just conclude by basically saying that what this is it's trying to bring quantum control solutions and kind of techniques and technology that exists in the NISQ universe together with some things that we've learned from kind of quantum optics and stuff. So what we are proposing is essentially a hardware redesign of the swap test in a way that basically allows us to proceed forward towards basically optimal control of NISQ algorithms optimal control of large quantum systems on NISQ devices. And so we think that this will have some applications in kind of modular gate optimization and quantum assisted chemistry and things of that sort. Okay, thanks a lot. I'll stop so that I can take questions for the next 5 minutes.
Sai, have you tried on some real systems, like for example, for some molecules or estimating energy levels?
No, yeah, because we were just the theory part of it was fairly hard to work out. So we've just finished. So this is, yeah, definitely this is in the future, Prasanta. Because the point is basically that this is in principle supposed to run on a kind of universal quantum computer with traumatization error. So this is the kind of model that we just chose for ourselves instead of kind of trying to emulate kind of real NISQI devices. And so, yeah, I mean, so we really have to run this for like some large enough size and see, yeah.
The one which you are telling that quantum assisted chemistry, that would be the best thing to check it out.
Perhaps, yes. It would be the most exciting thing to check out, I agree.
Yes. If there are no other questions, let's thanks, Sai. Any questions? Any more questions? Okay, so thanks, Sai. A very nice
Okay,
talk.
my pleasure
Very exciting
entirely.
talk.
My pleasure entirely. Thank you, everyone.
Diksha, are you around?
Yes, sir. So
So
Dr. Harrow is not here. So we just
okay.
mail him. And he must be logging in.
Okay. We can. So there is no break. No, I did not see the time. So we'll finish this one right now, continuously, right?
Yes, sir.
Okay.
No.
So then we'll wait. We'll wait for Dr. Harrow. Not a problem.
Yes, he's here.
Okay. Dr. Harrow, hi. Yeah, it's a pleasure to have Dr. Harrow here. For some of you who are familiar with quantum algorithms, you would realize that Dr. Harrow was involved in the development of this program of solving linear systems of equations. That was a major breakthrough after these algorithms of 90s, and that attracted a lot of attention. And it has found use in, basically machine learning, quantum machine learning, and many other applications. So, and in addition, if you take his interest, he runs, for example, a blog for Quantum Pontiff. Many times I have looked at that blog. So, Dr. Harrow, please go ahead. It's 40 plus 10, 40 minutes for talk, 10 minutes for questions.
Great. Thanks for the invitation. Thanks everyone for coming to attend this. Here, let me start sharing my screen. Good. Do you see my slides?
Yeah, we are able to see your slides.
Good.
Yes.
Great. So, so I'm going to talk today about some thoughts of mine about how quantum and classical algorithms can work together. Sorry, quantum and classical computers can work together to solve problems that could not be easily solved by one or the other. As well as some of my other thoughts about, yeah, I have one specific idea as well as some broader ideas about how these two can work together. And part of the motivation for this is trying to understand, starting with my algorithm for linear system solvers, looking at the big picture of quantum algorithms, there's a phenomenon where people propose quantum algorithms in many different models and many different input models, and you end up getting very different things based on these different input models. So, for example, the standard model. By the way, do people? Let me make a laser pointer here. People see a laser pointer moving around? Hopefully you see a red dot over where it says standard. The standard model of quantum algorithms is one where the input is just a bit string, like a tape on a Turing machine, or just some bits on a hard drive, the output is also a classical bit or bit string. For example, this is the model of factoring or combinatorial optimization problems like 3-SAT, where the input is just a short string and the output is also a short string. This is a kind of the conventional model of most, on a classical computer, for example, you would imagine that this is the input model. However, on quantum computers, we often think of broader ones. So on actually quantum or classical computers, we often think of the oracle model as well, where the input is not given explicitly as a bit string written on a hard drive, but via the truth table of some function. So this is called the oracle model. You imagine you have some efficiently computable function O, or some subroutine O that you can perform. You give it I, the index that you want to query, and it returns to you the ith bit of some large string. So you never have to write down the entire string. You could say you have implicit access to it as the truth table of some function. And this is the model behind the Grover speedup, as well as other more complicated speedups, including some exponential ones like the hidden subgroup problem. And this is an attractive model because often we do have access to some function, but it's hard to extract the structure of it. And it facilitates fair comparison between quantum and classical. But because we have a quantum computer, we also have uniquely quantum models as well. So there's the quantum data model and the quantum oracle model are two other models that make sense. In the quantum data model, your input is given as the amplitudes of a quantum state. This is the model that my linear systems algorithm works in. It's also used by things like the quantum Fourier transform. And there's the, finally, you can combine these with the quantum oracle model where you have a black box unitary. And all of these are used in some way. So, and in fact, Shor's algorithm makes use of all of them in some way. He uses the quantum oracle model to do phase estimation, making use of the quantum Fourier transform to solve the hidden subgroup problem, which finally is used to solve factoring. But the problem with these categories 2 through 4 is that you always in some way want to ultimately turn them back into a question about the standard model, because that's really, in the end, we get classical data and we want to return classical data. And so the ultimate challenge for quantum algorithms, if you have something in rows 2, 3, or 4, is how do you turn it back into the standard model in a useful way? So one thing that I always that has long puzzled me is, what about quantum search? The Grover algorithm. How can you use this for a hard optimization problem? So what the quantum search says is, the original title was a little confusing in that it said it was a database search, which it very much is not. What it is an algorithm that says if I have the ability to compute a function, f of I, such that f of I will say is x sub I. So this truth table is x1, x2 through xn. You want to find a string, an input I star that sends that f sends to 1. Classically, of course, you need order n time. Quantumly, Grover famously showed that you can do it in square root of n time on a quantum computer. And since then, the ideas behind this algorithm have been used for many unstructured or semi-structured search problems, like maximizing a function, approximately counting the number of ones, finding collisions, triangles in a graph, even speeding up things like rapidly mixing markup chains. And so it's been a very successful idea, but it uses this oracle model, right? So you have an oracle that you use to extract the ith bit of your input. And this very much does not look like the usual way that people access data. So if you ask, what does a data center look like? It looks, here's a picture. It's not something that you can send a superposition of input of queries to. You can't, query it at a superposition of 2 different locations. It's a classical, these are classical hard drives. It'll decohere your it'll effectively just measure which bit you want to query and send you back one of the answers. Also, this wouldn't be the right way to search the database, even if you could make superposition queries. If you wanted to find one record in this data center that matched some criteria, you shouldn't anyway be doing it sequentially. You should send the query to all of the hard drive controllers, right? Even if it's mostly storage, there's still going to be some processing units, some CPUs attached to each one of them. And if you have some simple queries due on each bit of storage, you should do it in a distributed way. So you should do it in, you can always parallelize the query. Some people have proposed something called quantum RAM that can be queried in superposition, which would give, which would let you do this. But this is not easy to build. Quantum RAM would let you run Grover over real data, but it's an additional hardware requirement. And since as a theorist, I'm aware that my time is much cheaper than the experimentalist time, and that the experimentalists are already sweating pretty hard to build the standard model of quantum computers, I really want to see what can they do with those before we get to, before I make even more demands and ask them to build additional hardware. So how can you do an oracle in the conventional quantum computing model, standard model? So you have x1 through xn living on a hard drive. How can you map it to a quantum oracle that will give you superposition access to these to the string? And one quantum circuit for doing this is the following. In the top register, you have I. In the bottom register, you have where you want to put the answer. And you just do n sequential gates. And each one of them looks at the first register, checks if it's equal to either 1 or 2 or 3, whatever, and adds the corresponding bit or bit string, could be a bit string, to the second register. And this does the job. It's a unitary transform. It does not require any unusual hardware. If you want to think about what does the hardware look like here, you should think about maybe you have a laptop connected to a big hard drive, and the laptop is also connected to maybe an FPGA, which talks to the pulse generator that sends in the pulses to the quantum hardware. And so you can read one record from the hard drive, construct the corresponding pulses, send those to the quantum computer, and iterate. And there's no sense in which the quantum computer needs, is getting any superposition access to anything or any kind of special access to the hard drive. We're really just controlling the quantum computer in the usual way, by just doing a sequence of easy to compute 1 and 2 qubit gates. So the only difference is that we're doing it informed by access to a large hard drive, but that's a very reasonable capability for a classical computer. But the problem with this proposal is that it takes overhead order n to make one query. You have to sweep through the entire classical data set. So that is really quite bad. It really wipes out all of the oracle speedup that we would like. So what do you do about that? As I mentioned, one solution is to posit better hardware. QRAM would be a hardware solution to this, and has its advantages, but it's quite a lot to ask for additional hardware, and there are arguments why this might be almost as hard as just building a large quantum computer. And the other solution, the one that Peter Shor came up with, is to come up with a clever function that encodes where the truth table of that function lets you do something interesting. So first, there was an oracle speedup for period finding, which means finding the period of a black box function. And then Shor realized that if the function you used was f of I is a to the I mod n, then extracting that period will help you factor n. So that was a brilliant insight. But in the 27 years since this algorithm, we have not been able to repeat it many times. And if you're just doing some random machine learning problem where there's a bunch of data you have from the internet, there's no reason to expect that such a function even exists, right? Like, let alone could you find it, but in general, a lot of optimization problems do not apply to functions of this form. So instead, I want to propose to find problems where we can reduce the size of the data set and still get a meaningful analysis. And that way the quantum computer can help us by doing a sophisticated analysis of that gets sped up by a quantum computer over a smaller data set. And I'm going to focus on realistic problems like clustering, Bayesian inference, and saddle point optimization, problems where they're not contrived problems that people actually want to solve in optimization and machine learning. So let me be a little more concrete. Let me talk about the types of problems that we want to solve. So these are new problems. I want to talk about statistical problems that involve large data sets, too large for a quantum computer to directly access, but still I want to know, is there a way they can meaningfully improve it? So one example of such a problem is maximum likelihood estimation. If I have a set of models Y and a data set X, I want to find the model that best fits the data. I'm assuming I have some distribution P of X given Y of seeing data point X given model Y. That's my likelihood. F of XY is the log of that, is my log likelihood. If I add that up over the whole data set, I get the log of the probability of seeing the whole data set, assuming these are like IID points, given I have the model little y. So that's the thing that I want to maximize. Plus, I have this other term, R of y, that you can think of like a regularizer or a prior. It tells me that even in the absence of data, I prefer some models over others, either because I have prior information or I'm just assuming that the simpler model is more likely or whatever. Okay, so this is a calculation that people often want to do. And you can ask, can we get a Grover speedup for it? And mathematically, the roles of X and Y are pretty similar. So Y I'm maximizing over, X I'm summing over, but at some crude level, both max and sum are both amenable to a Grover speedup. So I might hope to get a quadratic speedup for both. However, the type of data is very different. X is a real data set. It lives on a hard drive where I do not, as I discussed, do not have Oracle access or cannot make superposition queries to it. Whereas Y is a synthetic data set. It's you can think of it like the truth table of a function. For example, it could be the weight and centers of clusters. So maybe I have many options for Y, but I don't need to ever write them all down explicitly. I have implicit access to them. I can, if someone gives me an index, I can just tell you what the ith choice of clustering is. I don't need to enumerate through all the ones beforehand to get to it. So here I can make superposition queries. And so what that means is that my ability to run Grover is very different for X and Y. I can do a Grover search over Y, but not over X. So in this model, sort of what I would argue is the standard model of a classical computer that controls a quantum computer, I can run Grover. The outer loop is going to have square root of Y evaluations of this sum here. But for the inner loop, when I sum over X, I have no savings. I'm doomed to just iterate through the whole data set one at a time. So this really erodes a lot of the quantum advantage, right? If I get to speed up the Y part, but everything involving this big data set is not sped up at all, that is going to hurt a lot. That's going to make it a lot harder to find a meaningful quantum speedup. So the key question here is, can we reduce this dependence on X? Can we, if we could reduce or eliminate this term, then we'd be able to get much more of, whatever the advertised quantum speedup is. So this is an issue, by the way, beyond Grover. If I were to have an optimization algorithm, people are looking for these that get better than a Grover speedup. Of course, it's not possible in general, but maybe my problem has some structure that makes this amenable to it. Then I might have an even better function of Y, and it would be even more important to get rid of the other term so it doesn't wipe out the savings. Any questions so far about the problem that we're trying to solve, or anything else? I know there'll be questions at the end, but I would pause for a second. Okay, so my approach is going to be find a way to reduce the data set, to approximate a big data set by a smaller one. So if you have some data set X, imagine it's like a clustering problem and you got a bunch of points like this. If I reduce the data set to this smaller one, X prime, and I try to cluster X prime, that's still going to give me an okay clustering for the original data set. And more formally, what we say is that X prime is a core set for X if for all possible models Y, the true log likelihood of X is pretty close to the approximate log likelihood that you get for X prime. And here you see there's some weights here, W of X. Those weights are necessary partly because there are many fewer terms on the right-hand side, right? So just for this to add up to roughly the same order of magnitude, you'd expect some kind of weighting on the right-hand side, but also it's often important for the weights to be unequal. In this case, for example, we have big clusters and little clusters, and the best core set takes a constant number of points from each cluster. And so that means that the little clusters, I have a high chance of taking points from, and the big clusters, I have low chance of taking points from. And the weights need to be put there to compensate for that. So that means even though I'm on each point from the big cluster, I make much less likely. When I do take it, I put it in there with a big weight to reflect the fact that it came from a big cluster. So in order to make this unbiased, I need some kind of weighting. And this is the idea behind importance sampling. I don't want to go into too much detail because it's a machine learning technique that I'm just making use of this, not a contribution of mine. But that's the rough reason why the weights here are important. So what does that look like in terms of an overall hybrid algorithm? You have a data set X, goes into the classical computer, it crunches it down to some core set X prime, and then the quantum computer uses that to carry out its optimization and output some value Y. In a little more detail, how does the classical computer come up with this core set? One approach that works for clustering is to find a crude estimate of Y prime. So maybe use an approximate clustering algorithm that gives you maybe too many clusters and not necessarily the optimal ones. But those can still be used to construct the important sampling weights. Because remember what I said, you want to sample from the big clusters at a different rate than from the smaller clusters. Well, how do you know which ones are the big or small cluster? That seems circular. You have to solve the problem in the first place. And the key here is that an approximate solution will do. If you have an approximate solution, the quality won't affect the final quality of your answer. It'll just affect the size of your core set. So you do an approximate solution, the quality of which will impact how big your core set is. You use that to get important sampling weights, and then you draw X prime with important sampling, meaning that there's some distribution over which you sample from, and you put in the weights to compensate. Then, using X prime, the quantum computer can use Grover or whatever your favorite optimization algorithm is. The cost of the inner loop is no longer the size of X, now it's the size of X prime, which is much, much less. And the total cost of Grover is much close to the best you could have hoped for, right? The best you could have hoped for is to search over the size of Y with a trivial inner loop. Now, if X prime is pretty small, the size of the inner loop scales like the size of X prime. Now you're doing much closer to realizing the full Grover speedup. Or, again, replace Grover with some other algorithm if you like. And so for clustering, this is an example where this gives a provable advantage relative to the best known classical algorithm. Okay, so we don't have a proof of how long, provable lower bound. All we can say is the best classical algorithm that we can prove is to do a core set procedure and then brute force over all clusterings of the core set. And so in this setting, the quantum algorithm can do the same thing, but the search over clusterings of the core set now is quadratically better. And this is where most of the runtime is. So I think this is nice that it's a, previously Grover looked like something that was really for combinatorial optimization problems, like you could Grover over three-sat the solutions to a three-sat formula. But it seemed harder to use it for things with data. But using core sets, that lets you extend it really to a broad class of problems that have big data sets. And next, as a quantum algorithm designer, so if I'm just agnostic to if I'm using classical or quantum, this is, I think, a good way to solve a problem. But the role of the quantum computer, you could argue, is not very big. And maybe what was going on here is that the problem just wasn't as hard as we thought. Like, it didn't actually need this big data set. And from the quantum computer's point of view, by the time you even turn on the quantum computer, the classical computer has already dramatically reduced the size of the data set. So, that's the sense in which we maybe didn't need most of it. But there are other cases where we can have algorithms that are sensitive to the entire data set in important ways that use the quantum computer interactively. So maybe there's a series of messages back and forth between the quantum and classical computer before you get the answer. And so this will bring me to my second algorithm. And for this, I want to consider a slightly different problem, the problem not of maximum likelihood estimation, but Bayesian inference. So I have the same setup of a log, f being the log likelihood, but now pi naught is my prior over models y, and then given that I've observed the data set, pi is going to be my posterior, the posterior probability of y. And I'd like to sample from this. The most likely point will be my maximum likelihood, or sometimes my maximum a posteriori estimate. But samples have the benefit of also giving me a sense of what is the uncertainty interval around it. And okay, how can a quantum computer help with this? In general, if you have a core set of size t, the classical computer can send this to the quantum computer. The quantum computer can sample from the corresponding distribution. So where the true log likelihood is approximated by the one from the core set. And then the classical computer can use this to construct the next point in the core set. This can be done in a way that where basically it's sort of the most informative point, given that this is everything that you've seen already. And there are a number of proposals for doing this. I'm going to, again, some of these involve going into the classical machine learning literature, which is not where I want to focus. I just want to tell you the broad, this is the broad outline of the algorithm, how a core set can be built up iteratively in a way that uses the quantum computer at each step. And the advantage here is that because of you've already seen a bunch of models from the quantum computer, you can figure out which point is not well fit by the models and be sure to add that one so that the models can correct themselves to fit whatever points are hard to fit. Not just a random point from the set, but sort of the hardest to fit point. One other advantage of this algorithm is that we have a Grover style speedup for sampling, but the Grover speedup for search is kind of like a square root speedup over brute force search. But the Grover speedup for sampling is a square root speedup relative to simulated annealing. So it's already a fairly sophisticated classical algorithm. Sometimes the best, not always the best, but sometimes already the best classical algorithm simulated annealing. And so being able to quadratically speed that up is a lot more appealing than quadratically speeding up brute force search. So that's my second algorithm. For the third one, I'm going to be a little more concrete and talk about a hybrid quantum classical algorithm that I can describe fully. And so for this third problem, I'm going to talk about saddle point optimization. And this is a little bit more specialized than the previous two, but still quite general. The idea is that you have, again, a data set, x1 through xn, but now I'm going to define capital X not to be the set of all of those, but to be their convex hull, meaning that the smallest convex set that contains them, like in this picture. And y, I'm going to define to be the set of probability distributions over m items. So instead of having, let's say, m models, I'm going to allow all convex combinations of those models, all mixtures of the models. If you're familiar with boosting, this is a little bit the situation there, where you have basic classifiers, but also you can output mixtures of those classifiers. And then the objective function f is going to be linear in x and y. So when I do this convex mixing, then f linearly interpolates between the points. And the minimax problem I want to solve is I want to maximize y, max over y, the minimum over x of f of x, y. So think of that as the best model for the worst point in x. And because of my assumptions, von Neumann's minimax theorem says I can exchange the order of these two and get the same answer. I can minimize over x and then maximize over y. I get the same thing. So what does this correspond to? Well, the way I've set it up, it looks a lot like a zero-sum game between an x player and a y player, where y wants to maximize and x wants to minimize. Here, it's important, though, that, again, the x strategies are enumerated by some kind of data set, and the y strategies are something that we have implicit access to. So you can think of x as some kind of, maybe some database of transactions, some of which might be, or of fraudulent transactions, and y might be strategies for catching fraudulent transactions. And you want a portfolio of fraud detection strategies that really work in the worst case, because if there's one fraud strategy that you're missing, then there's people who have an incentive just to put more resources into that strategy. So something like that, where there's a database of strategies for x and an implicit list of them for y. The family also includes linear programming. So let's say that y corresponds to the simplex, and every point in x is some linear constraint, some half plane, there's half space that cuts down y. Then if you think of these as f of x, y is telling you it's basically greater than or equal to 0 if the constraint is satisfied, or negative if it's unsatisfied. And so if this maximum is greater than or equal to 0, then that means that the linear program is feasible. And if it's less than 0, that means it's infeasible. So evaluating this corresponds to solving the LP. It also looks a lot like the original maximum likelihood estimation problem we looked at, except there's a minimum over x instead of a sum over x. So sometimes this is a good approximation for the sum, or sometimes maybe you just want to do a clustering where you care about the worst case rather than the average case performance. Like maybe you want to, provide coverage to many people, many customers, and you really don't want to leave anybody out. Or if you're familiar with SVM, this is a lot like SVM in the L1 norm, which I described a little more in the paper. Okay, so let me describe to you the algorithm for this, and you'll see how it works well in the hybrid setting. And I'll explain this for as though this is a zero-sum game, because I think it's most intuitive there. And here we're following an algorithm by Grigoriadis and Kachian from 25 years ago. And I'll illustrate it for the game of rock, paper, scissors. So here's the payoff matrix of rock, paper, scissors. You see it's positive, it's y gets the payoff and x gets minus the payoff. So +1 means that y wins, -1 means that x wins. And one naive way to play this game to try to converge to an equilibrium is one player picks a strategy and the other player does the best response, and so on. But for rock, paper, scissors, that will cycle. So let's start off doing that. X will choose x1 arbitrarily, let's say rock, which induces these payoffs. Now, if y chooses the best response, that'll be paper. And then if x chooses the best response, that'll be scissors. And you can see that's just going to cycle forever. But if you add a little bit of randomness, it converges quickly. So instead of choosing the best response, y will choose a response that's biased towards the better responses. So the probability of y1 will be proportional to e to the epsilon times the payoff. So that biases it towards larger payoffs, but it's not deterministic. Now, let's say that y happens to choose the best payoff, which is paper. Then we go back to x and we do the same thing. That induces these payoffs for x. And we sample x from the same distribution, except now it's biased towards low values because x wants the smallest possible value. And so the best would be scissors, but sometimes x will choose something else like paper because it's random. Now we go back to y, and y responds to the sum of everything that x has done so far. So just add up these two rows, and that induces, that's the vector that x is that y is responding to. So you see in the beginning, the players are kind of bouncing around at random, but quickly the bad strategies become exponentially less likely, and this will start to converge, it turns out, to a Nash equilibrium. This is what Gregoriadis and Kachian find, that the error is less than epsilon times the maximum payoff. After a number of rounds, it goes like the log of the total number of strategies divided by epsilon squared. So this is very good scaling with the number of strategies. It works well for extremely large strategy sets. The scaling with epsilon is not so good. So this is a useful algorithm in a setting where you want a very crude approximation to a very, very large problem, which is often the case for quantum optimization algorithms. So this will run on a hybrid classical quantum computer very naturally. Their number of rounds of alternation is t, which, if epsilon is not too small, t is hopefully not that big. In each round, what do? The classical computer has to sweep through the whole data set, and the quantum computer has to grover or otherwise search over its entire space of strategies. And the inner loop in each case, what the classical computer has to do for each item in the data set, and what does the quantum computer have to do for its inner loop of grover, the time is order t. And so if t is small, this is close to the best you ever could have hoped for, right? Like the best you ever could have hoped for is to run grover once with a trivial inner loop. If t is small, you're running grover t times with order t effort in the inner loop. And that's not too much worse than the best you ever could have hoped for. So it's so this is I think quite a natural algorithm for this hybrid setting because as I said, if it's reasonable that t wouldn't be too large, in which case the quantum computer is really not paying too much for the data. That cost has really been successfully pushed onto the classical computer. And so it's a method of doing hybrid computing that uses really the strengths of both platforms, the quantum computer for searching, the classical computer for accessing a large data set. Now, I think I want to, I don't have time to go into this in great detail. I'll just talk about this briefly. When people talk about hybrid algorithms, they often mean variational algorithms, and this is often also what people mean by NISQ algorithms. And the idea is that you have some variational ansatz, which corresponds to you start with some state and you do a bunch of pulses, and then you try to minimize some objective function. And this can be used for combinatorial optimization. If the pulses maybe alternate, applying some the phases corresponding to your objective function, and then all the sigma x's. Or it could be the variational quantum eigensolver, like maybe where you break up a Hamiltonian to maybe kinetic and potential energy terms, and you alternate between those. And the idea is that the classical, there's a classical outer loop where you search over T1 over the parameters of this and use the quantum computer to estimate the objective function. And this is appealing because you can always get started with a small quantum computer. For small p, you can always do this. And if p gets big enough, sometimes exponentially big, so don't get, it's not always that great, but certainly if p gets big enough, this will eventually converge to the right answer. So you know that in principle, it's a reasonable algorithm to pursue. So one piece of work I think I don't have time to talk about is my work with John Knapp my former student, where we looked at what happens if the quantum computer doesn't evaluate that function, but it evaluates the gradient. You can even go to second order where it evaluates the second derivative. And we found basically methods for evaluating the gradient, which I think I'll skip, and some performance guarantees, and some proofs that in some cases these gradient methods beat the zeroth order ones where we just estimate the function. The other work I want to very briefly talk about is the more recent work that my students have been doing. So John Knapp has been working on this barren plateau problem, something that was started by Patrick Coles, Jared McLean, and others, where they argued that when you do these variational circuits, it does not work well if you initialize them randomly. You really need to have some insight into how you initialize them. And they found that if you run in the circuit for long enough, then if you initialize to be a long random circuit, all the gradients will be exponentially small. And what Knapp found, and this paper will hopefully be out soon, is that the gradients actually vanish exponentially in the depth of the circuit. So even before they get to a 2 design, which requires quite a lot of time, the gradients are already exponentially vanishing. This is called the barren plateau problem, because you can imagine your solution landscape just looks super flat in every direction. And then my other student, Eric Anschwitz, actually I wrote in preparation, but he's actually just recently posted this paper, said if you zoom in on the landscape, it actually has exponentially many teeny little bumps. And here's a numerics from the transverse field Ising model that give you the idea. And they're exponentially local minima with values that are very close to just what you'd get by just choosing at random. And so both of these are not killers for variational algorithms, but they do point out that random initialization is not the way to go. And so this, yeah, actually I forgot to bridge these two talks. What variational algorithms do, they're also making use of the strength of both classical and quantum computers. The difference is that they are making use of the coherence time, whereas what I talked about in most of the talk is making use of as well their ability to access large storage. So I think what this points to is the need to continue working on these variational algorithms, but with maybe more insight into how to initialize them, because just striking out blindly will not work well. There's a way of linking the two, of variational algorithms, to what I was talking about in the first part of the talk, but maybe I'll skip that unless there are questions. One brief thing I'll say is that there's a broader scope also for hybrid algorithms for things like quantum simulation as well. So if your goal is to simulate a quantum system on a quantum computer, we have many classical simulations of quantum systems as well. And this is work I'm just starting to think about, is how can those two work together? And I think here there's a lot of scope for improvement. And let me wrap up by saying that quantum computers are coming, we hope, and they're going to be doing effective things, but classical computers are not going anywhere. And so we should really design our algorithms with this hybrid model in mind. And one example of hybrid computation that I like was one that Kasparov popularized after he lost to a computer in, I think, 1997, is the idea of centaur chess, where there's a human and a computer playing together. For a while, the top chess ratings were these hybrid teams. They were significantly better than the best computer players. And unfortunately, now humans don't improve the value of computers when playing chess, apart from programming them. But there was a period when a grandmaster paired with a computer could do better. And so for quantum and classical computers also, I think there'll be a long period in which using the two together will be more effective than either one alone. Okay, I'll stop here, and thanks again, everyone, for your attention.
Now we are open for questions. Maybe I can ask a question to start with.
Sure.
What are the, quantum chemistry or other kind of practical problems where these kind of hybrid algorithm are being used?
So I guess what I had in mind was for problems in analyzing big data, and for quantum chemistry, what I meant, all I was proposing were basically ideas for how to do the, things that one might do that I haven't done yet. This is kind of like future work. So yeah, I can talk a little bit more in detail about what I was thinking. So with some of my students, we've worked on extrapolation. So you want to estimate the partition function. And so, can you estimate it in a region where, let's say you're able to sample the Gibbs state in some region, can you extrapolate beyond that into some other region to estimate the partition function, even into a region where it's difficult to do the quantum simulation. So we have classical algorithms for estimating partition functions. Those I think might benefit from being combined with quantum simulation to further extend the range where they could do it. Another thing that I think is promising is important sampling for Hamiltonian simulation. So if you simulate a Hamiltonian, let's say it's this sum over alpha, h sub alpha, it's got a ton of terms. The Trotter expansion would just be to say do each term sequentially. Earl Campbell had this great idea called Q-drift, where you just sample from those terms. Like maybe it's a quantum chemistry problem. The number of terms goes like the number of orbitals to the fourth. So that's really a huge number of terms. Maybe you don't really need all of those. So Campbell's idea was just sample from those and you get a good approximation. But then the question is, whenever you're sampling, with what weights are you sampling? And I think by doing an adaptive algorithm, you might be able to sample from the basically Campbell was sampling based just on the norm of the term, but some terms might be more or less important depending on the state that you're acting on. So I think there's room for further savings there. But for that, you'll need a hybrid algorithm where to figure out what is even the state that you're acting on and how important the term is for that one, you have to run the quantum computer. And finally, one purely classical algorithm, like my colleagues that do lattice QCD simulations do, is quantum Monte Carlo. And that's basically like a, you turn the entire thing into a giant classical sum over, an enormous space, and then you sample from that. But you can think of that as summing over many, many variables. But what if summing over some of those variables looked like a tensor contraction? A tensor contraction is also a way of summing over many variables. In some cases, this is more efficient on a quantum computer, especially if there's a sign problem. And I've been discussing with them ways of dividing up the problem into one where you do Monte Carlo over some degrees of freedom and tensor contraction over others. But anyway, none of these are finished. These are all just ideas I've started thinking about.
Thank you.
You're welcome.
I have a question.
Yeah.
Is there any good way to check from where to initialize the parameters?
Say that again about, is there a good way to check what about the parameters?
Means we for the algorithm initialize some of the parameters. So is
Right.
there any way to check from where to initialize them? How to initialize?
You mean in like the context of these variational algorithms?
Yes.
Yeah, yes.
Yeah, something like that. Yes.
Right. Yeah. So it's yeah, it's a big problem. So there's no canonical answer to it. One thing that does not seem to work very well is doing it layer by layer. So you might say, let me solve it for p equals 1, optimize it, and then increase p to 2, and then and so on. And each time use what I've done before as a prefix for the next one. That seems to not work very well. One thing that works okay is to say, well, let me approximate an adiabatic schedule. I know the adiabatic algorithm will converge if I take long enough. Maybe I could start with something that looks kind of adiabatic and then optimize from there. So use the adiabatic algorithm as a start. That's one approach that works okay. Another one is if you can solve it for small values of p, instead of using that as the prefix for a larger value of p, you can basically fit a curve to those values of t. Like often the values of t will not be jumping around like crazy, but they'll have some kind of pattern to them. Almost like adiabatic, but maybe something more refined than that. Like adiabatic would be a linear trend, but maybe there's some other simple curve that you can fit. Then if you have that curve, that lets you extrapolate also to higher values of p. So Misha Lukin's group has been experimenting with this on their neutral atom system. But there is not any one answer to the question. There are many things that people try. They work in some settings, and maybe not work in other settings. Yeah, what you're asking is a big important question that people are still very much grappling with.
Thank you.
Yeah.
Okay, so if there are no more questions, let's thank Arom and all the speakers, Jacob and Sai also.
Thanks, everyone.
Yeah. Now I hand it over to Diksha.
Yes, sir. Thank you, Professor Panigiri, for your time and chairing this session, and the speakers also for their interesting talks. We will see you all after tea break at 7:20 hours IST.
Okay, thank you. Yeah.
All right.
Hello, can you hear me?
Yeah, yes. You can now. You can try your.
Okay, and how is the sound and the picture? Is it okay?
Okay, good.
Okay, super. I'm a little bit afraid that the connection is not too good. In the last talk, which I listened to, it was breaking off sometimes. Then I have to switch to the to my other modem, and I hope it goes better. So just bear with me. Sorry, I wanted to share. So let me share. No, I don't want to share the screen. I actually want to share my keynotes. But it doesn't show here. Why not? Let me clean a little bit up. Maybe then it works better. Just 1 second. So I delete everything. Okay. Do this. Yeah. Now where's my? Just give me 1 second. Okay, so now hopefully I can share it. Share keynote. Yeah, there it is. Can you see this?
Yes, yes, sir.
Super. Can you also see my mouse? Wait a moment. Here's my mouse. Can you see my mouse as well?
Yes, sir. Yes.
Ah, how nice is that? That's wonderful. And you are hearing me.
Can you meditate full screen?
Say again?
Full screen.
Full screen?
Yeah.
Do you see my mouse still?
Yes, sir. We can see.
Good. Okay, let me switch a little bit around. Can you see this? Does it change?
Yes, sir. Yes, sir.
Okay. Good. So then maybe we can make it, hopefully. Let me try my movie, okay?
Okay.
Okay, so we have to maybe I go out and then switch to the page. I'm not totally sure where it is. I think here. Okay, so now there should be a movie starting. Now nothing happens. Now, can you see this this movie?
Yeah, yes, sir. We can see.
Okay, super. All right, I think then I'm set. So everything fine, and yeah, let's hope it works later as well. One never knows. I'm sorry that I'm so pessimistic, but with the internet and these distances, I'd rather be in Jodhpur. Can you hear me?
Yes, sir.
Okay, was I breaking off?
Sorry. Once again.
So you are audible,
Yeah,
you are audible very
see.
well. No problem. 100.
Hello, yes.
You are audible.
I'm audible. Okay.
You
I
are
hope it works. Yeah. Otherwise, if you suddenly lose me, how can you can you somehow show it? Do you have a kind of chat that I can see here? Because I don't see it.
There is a chat. Message will appear for you.
Okay, where do I see it?
Bottom right, sir. Bottom right.
Bottom right. Now you are.
Next to the button on for participants.
You know, at the moment, I just see in front of me my keynote slides, and I see in front also my picture, and then I see the names, active speaker and thumbnail video. Then it says active speaker, grid view. Maybe what's that now? That doesn't help. So
Sir, I pinged
now
you
I have
at the
more. Say that again.
I sent you a message in the chat.
Oh, you sent me a message in the chat. Yeah,
Yes,
I
sir.
think now I have it. Okay, wonderful. Yeah, Yoti, thank you very much. Thank you. I got it.
You're welcome, sir.
Okay, super. So in principle, I should see the chat if I just leave it open. Let me start my my screen. Yeah. Okay. If you write something in the chat and tell me that it doesn't work, then I stop
Sure,
or
sir.
I try to change the modem. Okay, I got it.
Arul here. Hello.
Hello.
Hi, Thomas. Arul here.
Hey.
Hi.
Arul, yeah.
I think I'm the. You can see me too, I guess. Oops.
Are you my chairman?
Yes, yes. I'm supposed to chair the
Oh,
next
wonderful.
session. Hi. How are you?
Hello.
Yes.
Good to see you. Yeah.
See you. Yes, indeed. From Chennai to South Africa via Jodhpur.
Yeah. Oh God. Yeah.
With a strange connection going on. I think we met Mohali last time. Before all this stuff, of course.
Yeah. Yeah. That's true. Yeah. Look, I hope we can travel soon again. I want to come to Chennai and I will visit you if you don't mind.
Yes.
I mean, I want to come but it's so difficult, you know, with this I don't know, with these internet connections and not really being there, you know. I mean, I now give my talk, but afterwards we don't have a chance to chat, you know. I mean, it's like
Yeah, it's kind of, we are giving a blind talk, basically. We can't see much.
blind, yeah, totally blind. Yeah, everything might crash and I don't notice.
But actually, this is a very brave conference by Subhashish. It's one of the, I think, the bigger ones that I'm seeing online.
Yes.
Yeah.
True.
Yeah. But your thing seems perfect so far. So touch wood.
Oh, wonderful.
Yeah.
I hope I'm not the first one where it doesn't work. I was surprised by this new system. You know, I didn't use it before. This what is WebEx or something?
Oh, this WebEx, yeah. We do use it here in our institute. Maybe there is, it's more of a
Oh, really?
Cisco. Yeah. It's okay. It's quite reliable.
Okay. Good. Okay.
So
super.
I think we're fine, and you can see the chat, but I think you should be fine.
Yeah. Okay. I can see the chat. Yes.
On the chat, so we could see the chat.
Mm-hmm. Okay, but
other speakers in the session are Tabish. Hi, Tabish. Tabish was there. Hi, how are you?
I'm here.
So Tabish, and the third speaker. Is the third speaker here? Any of the organizers?
He's not here. He will be joined.
Okay, he'll be. Hi, Thomas. Yes.
Hello.
He will be joining. He's joining from where? Oh, it's Canada, right? Yeah. So, Thomas, good to see some chaotic potential going on. Look forward to it.
Yeah, chaotic potential, hen and hails. Yeah, thank you. But I'm going to stop share now, but I don't know how to stop sharing. Here, stop sharing.
Yeah.
Stop sharing so that others can try.
Want to check your thing?
Yeah, I think I will check my sharing.
Because the third speaker is not here anyway. It's probably very early morning for the speaker. It's probably the first thing that he's doing is getting up and talking, unless he's.
So can you see my screen now?
Yeah.
Yeah, wonderful.
Yeah. Can you make it? Yeah, perfect.
Yeah, full screen.
Just change it. Change your screen. Yeah, it's fine. It's all good. So, how is the situation in South Africa vis-a-vis the pandemic?
The pandemic, yeah, it's okay. I mean, we don't have a high infection rates, but people are not really vaccinated. I mean, I think we have 40% vaccinated.
40% doubly vaccinated.
Yes.
That's.
But I'm not sure whether we get anywhere. I mean, so it might be that we never reach 60%. So I don't know what that means, you know, whether it goes on forever or it will stop. But
they're saying
how is it in Chennai?
You know, in Chennai, it's around. Well, the Indian number, I think now, Tabish, correct me, is probably around 10,000 a day. Is that right, Tabish, or maybe slightly more? South was affected a little bit more. Chennai is okay. It's pretty much opened up as far as business is concerned. Our institute is still functioning online. We have a few students, senior students around. But even next semester, we not anticipating direct classes. But otherwise, the city, people are trying to forget or have forgotten.
Yeah, I think I have not been following because I think situation is improving in all the cities now.
Nice.
Yes, but if you see the news from Europe, it's pretty disturbing. There seems to be an upward trend there, and you know they opened up pretty dramatically, Europe, and so I don't know. If it goes on in this way, I think we should be fine. But what is in fact, today was celebrating 1 billion or something like that. There was 1 billion vaccinations in India.
1 billion? Wow.
Fact is, it's still not doubly vaccinated, right? I mean, I think the doubly vaccinated percentage is not more than 30, I think. Tabish, is that correct?
No, I don't know about the percentage. Yeah, but yeah, fully vaccinated percentage is quite low.
Yeah. So that's still going on.
And have you been traveling, Arul, anywhere?
Not really.
I mean,
I have avoided. You know, there was no. I didn't. Just within Tamil Nadu, I just went some 200 kilometers away. But not since the pandemic started. I haven't really gone. But I have colleagues who have traveled to Europe and come back. So just recently, and a few more are traveling. And next semester we are having more visitors. So it's going on, and I believe. See, in India, we had two major vaccines. One, which is AstraZeneca Covishield, which is, and the other was a Covaxin, which was more an Indian production. And so the Covaxin did not get WHO clearance so far. So I think it would have been very difficult. I got that, for instance. I think it would have been very difficult for me to head out. Although I do know a person who got that and has traveled to the United States. But I think we made an exception, and you know there was So they are making exceptions, and people are traveling. They're starting to travel. And
Yeah.
yeah, I mean, if things
Look for me. Yeah.
yeah, exactly. I mean, if things, I think if things hold up as of now, I think it should be fine next semester or next year, early next year.
I also think so. I hope,
Did you
you
also?
know, how long was this now? 2 years?
Yeah.
2 years, maximal 3, then it should be over. That is, I mean, that it wasn't at the time before, 100 years before, when they had this, after the First World War, they had this Spanish flu. Did that not also last like 2 or 3 years, and then it was over?
So yeah, so hopefully that.
Let's hope.
Yeah.
Let's hope. Okay.
All right.
Yeah. If you ever want to come to South Africa, speak to me.
Yes, of
I'm
course.
happy to invite you.
Thank you.
You know,
Yeah, I would love to. Yeah, sure.
it's very nice here. Yeah, I mean, usually.
Yeah, I
But
heard.
of course, yeah.
I mean, actually, one of our students was with French.
Francesco Petroccione, okay.
Now he is with Carol's group in Krakow, or maybe in a slightly different group. Yeah, he's gone there as a postdoc. Yeah, so
I see.
he was there for 5 years with Francis.
Oh, yes.
Francesco. Yeah, so he had a really good time. He told me that.
I think I know whom you mean. He was very, very knowledgeable person.
Yeah, he worked
Yeah,
on
very
open
good
systems.
person.
Yeah, it was a bit of. Yeah.
Good, good.
When are we supposed to start? We have another 15 minutes.
15 minutes, okay.
Yeah, I think
Okay, maybe I go and.
Yeah,
5:20.
or something. Yeah, maybe I will also do that. All right, see you in a short while.
Okay, I see you later. Okay, thank you.
Right, Tabish, maybe you can share your talk.
Yeah.
Welcome back, everyone. The second session of day 5th will be chaired by Professor Arul Lakshminarayan. Professor Lakshminarayan, please take over.
Thank you very much. Yeah. So welcome everyone to this session of this conference, this afternoon session, the second session today. We have 3 speakers and 3 very interesting talks. So I hope you'll stay with us. The first is by Professor Tabish Qureshi from the Center for Theoretical Physics, Jamia Millia Islamia. And I'm going to give a small introduction to Tabish. The organizers have done a fantastic job of actually giving us these nice write-ups. So Tabish did his PhD in 1993 from Jawaharlal Nehru University, New Delhi. After working as a postdoctoral fellow at the Institute of Mathematical Sciences, Chennai, where I am, incidentally, he joined Jamia Millia Islamia as a faculty. He's a theoretical physicist who started out as a condensed matter physicist, but is now interested mostly in foundational aspects of quantum mechanics, involving quantum measurement, entanglement, wave-particle duality, and the coherence. Today, Tabish is going to talk about coherence, interference, and visibility. Please go ahead, Tabish. Maybe I will alert you around 6 o'clock. That would be about 10 minutes before.
Yeah. Thanks.
Please go ahead.
Okay, thank you, Arul, for this introduction, and I'll also take this opportunity to thank Subhashish and these other team members who are working very hard to organize this meeting. And it's nice that even during this pandemic time, we have this opportunity to discuss our work with each other. So, let me discuss this very well-known phenomenon of two-slit interference. So you have 2 slits, and there is a source of light, and then see interference on the screen. So how do we treat this thing classically? You have classical light. So basically, you assume that there are fields emanating, say, E1 from this slit and E2 from this slit, and they arrive at a point X on the screen. And suppose tau is the time difference between the arrival from these 2 points. So then you can write the intensity of the screen as follows, as an average of this quantity, and this represents the real part. So you can use this translation operator to represent this in terms of the fields, not at the screen, but at the slits. So this E1 is the field at the slit, and E2 is the field at the other slit. So you can write a coherence function as follows. I1 and I2 are the intensities at the 2 slits. So fringe visibility in optics is conventionally defined as this I max minus I min divided by I max plus I min, minimum intensity maximum intensity minus minimum intensity divided by the maximum intensity plus minimum intensity. So for if both the slits are equally illuminated, then the visibility can be shown to be just equal to the mod of this coherence function. So the interesting thing is that fringe visibility is a measure of this coherence of light. If the light is completely incoherent, then the visibility of interference will be 0, and it will be maximum when this coherence is maximum. So this is what happens in classical optics. Now, how do we treat this problem quantum mechanically? So quantum mechanically, let me pose the problem that you have a source of maybe light or particles, which is throwing particles, or let me call them quantums, one at a time, and there are two slits, and there is some kind of a path detector here. I am not specifying what kind of path detector it is, but you just assume that it could be a small camera or something else. But something very, I am going to treat it in a very generic way. So the way I write the state is this psi1 and psi2 are the states coming from slit 1 and slit 2, and this d1 and d2 are the two quantum states of the path detector. So without specifying the nature of the path detector, I'm just assuming that these d1 and d2 are the states of the path detector. They are normalized states, d1 and d2, but they may or may not be orthogonal. Okay, so if they are orthogonal, then of course you can know perfectly which slit the particle has gone through. So one can, using this state, you can write the density operator, and then you can write the reduced density operator for the quantum by tracing over the states of the path detector. So then one can show that fringe visibility is still defined as Imax minus Imin divided by Imax plus Imin is just equal to, maybe there was a factor of 2, mod of rho 1 2. Rho 1 2 is the off diagonal element of this density matrix. Now you see that in this space of psi1 and psi2, it is just a system with a two-dimensional Hilbert space. So this density operator, density matrix is a 2 by 2 density matrix, and this rho 1 2, rho 2 1 are the off-diagonal density elements. So visibility is just equal to this. So we know in quantum mechanics, off-diagonal density matrix are considered to be a measure of coherence. They seem to represent coherence generally. I mean, in quantum optics also, it is well known that if a density matrix is completely diagonal, then coherence. So in quantum treatment also, the fringe visibility is a measure of coherence. So coherence can be measured using interference. So that is a basic idea. Whether you are treating a classical system or a quantum system, if you see interference, then you just measure visibility, and you will get an idea of the coherence of the light or the particles, whatever the case may be. So now, if you want to study wave particle duality, I can briefly just mention what I mean by wave particle duality. Basically, this Bohr's principle of complementarity. That at one point, at one time, you can either see wave nature or you can see the particle nature, never both at a time. But if you want to look at both aspects at a time, then what you can do is you can look at it in a quantitative way, like this much of wave nature and this much of particle nature. So that quantitative wave particle duality for two-slit interference is given by this duality relation. So this was first derived by Englert in 1996. So this D is what we call the path distinguishability. It is a measure of how well you can distinguish whether the particle has come from path 1, slit 1 or slit 2. So let me not go into the detail how this is defined. And visibility, this V is the visibility of the interference, which is simply defined as in conventional optics, basically the contrast of interference. So with these two definitions, you can just show that d square plus v square is less than or equal to 1. If the state is pure, there is path detector and quantum state is pure, then you will see an equality here, not an inequality. So now suppose one wants to go beyond these two states, suppose to 3-state or 4-state interference. So first of all, one thing is we need is that this distinguishability needs to be generalized to n states. And the other thing is that you have to worry about visibility, how to define visibility for n states. Of course, you may want to use the same definition, but if you have seen how a 3-state or 4-state interference looks like, there are some primary maxima and secondary maxima and so on. So this may not be a very convenient quantity for n states. But anyway, we'll come back to this point later. So suppose we look at this 3-state interference in quantum mechanics. So a quantum emerging from a triple slit, the state can be written as this psi1 plus psi2 plus psi3, and it may or may not be equal superposition. So there are these factors P1, P2, P3, and this D1, D2, D3 are the 3 states of the path detector. So I have represented this path detector by a blue line without specifying what it is. Just assume that it has 3 states. So for example, if these were orthogonal states, and if you were to measure an operator for which D1, D2, D3 are the eigenstates, then you know that if you get the eigenvalue corresponding to this D2, then you know that the particle went through the slit 2, not from slit 1 or slit 3. Okay, so for 3 slits, it is more convenient to define a distinguishability in the following way. So this was done using what is called this unambiguous quantum state discrimination. Like if you are given a state and which could be one of these, say D1, D2, D3, where D1, D2, D3 are not orthogonal, then this unambiguous quantum state discrimination is a method in which you can distinguish it without any error. Of course, the downside is that sometimes your method fails, but when it fails, you know, and when it succeeds, you know. But when it succeeds, then you know for sure, without any error, which of these 3 states you have. So this distinguishability can be defined in terms of this, and visibility still we use the same old definition, and then we get this duality relation EQ plus 2v divided by 3 minus v is less than or equal to 1. So you can see that this is a good enough duality relation, but you can see that it doesn't have an elegant form as the one which we had for 2 slits. So
Tabish, if I may interrupt, what is now the visibility defined as in terms of the density matrix?
Yeah. Just come again.
I mean, in the earlier case, you just had the off diagonal matrix element as the visibility. Is this visibility the coherence or something of the density matrix of the quantum?
So now this one is not. So this one will depend on this thing, the off-diagonal elements, but in a more complicated way.
Okay. So how exactly, sorry about this Imin and Imax, how is it defined from the state itself?
Yeah, I'm sorry, I have not gone into the detail of this. Maybe when I discuss this and slit this, maybe it will come out. So you have to write you have to evolve this state from here to the slit. And at a point, you have to see what is the state. So state will again consist of 3 parts. Then you take a mod square of that. That will give you the intensity at a point.
Okay, so it's
then you look at where the intensity is maximum, where the intensity is minimum. You have to look at the whole interference
pattern.
You
have to do the evolution and then.
Using that, then you calculate this using this Imax minus.
Thank you.
Okay, so if we go to n-path interference in the presence of a path detector, again you will see a complicated interference pattern, and you have this. So again, since Bohr's complementarity principle has been discussed in terms of to begin with in terms of two-slit experiment, but since you have n-slit or three-slit interference, it should continue to hold there. So a consequence of complementarity principle is that if you acquire past knowledge about which slit the particle went through, that should actually degrade interference visibility. That is what quantitative wave particle duality would mean. So we are extending this definition of or the idea of wave particle duality from two slits to n-slit interference. So this is one of the requirements very intuitively of the Bohr's complementarity principle, that any increase in the path knowledge should degrade the visibility of interference. Okay, so let me tell you about this experiment which was done in 2001. So what they were able to show is they considered interference, some 4 paths and 5 paths and so on interference. So they had a sort of more complicated setup in which they changed the phase of one of the paths. So one of the phase was changed by pi, and then they applied decoherence on only one path. Okay, so this method is a bit roundabout, I mean more complicated than conventional interference, but again our Bohr's complementarity principle should continue to hold there. But what they were able to show experimentally, that if you apply decoherence only on one path, it leads to an increase of interference visibility. Controlled decoherence can also be treated like getting path knowledge. So sometimes this is saying that you are increasing the path knowledge and still it leads to an increase of interference visibility. So this was a very startling result. Seems to go against the idea of complementarity or wave particle duality. So first we decided to look at how this thing is happening, that what special is happening in this kind of setup. So we look at a 4-path interference. So the phase in one path has an additional phase difference of pi. So this blue curve represents the interference when no path information is obtained. So you can see this blue curve, and this red curve is the one in the presence of a path detector. This is what we saw, that if you introduce a path detector, so you can see that now this intensity has actually increased here. So you can see that clearly the contrast seems to be more now when you are actually detecting the path. So seems to go against this thing, idea of complementarity. So to give you an intuitive idea why this thing is happening, is that even if you have a 4-path interference, it is actually built up of various 2-path interferences, like quantum coming from slit 1 and slit 2, it will give you some kind of a 2-path interference. Coming from slit 1 and slit 3, it will give you another 2-path interference. Slit 1 and slit 4, again it will give you a different 2-path interference. So all these interferences are adding to give you a net interference pattern, which is a 4-slit interference pattern. So now when you are actually flipping the phase of only one path, what is happening is that when you just change the put an additional phase pi, the 2-slit interference from say slit 1 and 2 may get cancelled with the two-slit interference from say 3 and 4. So this is what is happening by putting an additional phase. So one two-slit interference from slit 1 and 2 is getting cancelled from two-slit interference from slit 3 and 4. So that is why you see in this blue curve, you see this weird kind of pattern. There is a dip here where you don't expect a dip. Normally you see tall primary interference intensities, but this is not what you see here. So naturally, when you are introducing decoherence or path information, then what is happening is that cancellation is getting cancelled. So two interference patterns which were getting cancelled, now they do not get cancelled if you introduce decoherence or you put some path detector in between. That is why you see an increase in intensity. So that is the basic understanding we got from analyzing this, that is a mechanism which is at work in this experiment which we have done. So this experiment generated naturally a lot of controversy, and there were various papers on that. So like this one, so what they are saying is that visibility is incompatible with any intuitive idea of complementarity. So people sort of there seem to be a consensus that interference visibility is not a good measure of good measure of wave nature of the particles. Another paper here we show that for multipath quantum interference, the visibility of interference and the which path information are not always complementary. So now you are in a fix. You are in a multi-slit scenario, and how do you quantify wave nature? This is the problem. All you have in interference, all you have is the interference pattern. From the interference pattern, how do you get a quantitative measure of the wave nature? We see that interference visibility is not a good measure. So how to go about it? So that is a problem I am going to address now. So let me recall the present audience. I think everybody is familiar with this paper, which was a seminal paper by Plenius group. So they have defined a measure of coherence, which is basically the mod of sum of the mod of off-diagonal elements of the density matrix. So these are density matrix, and these are the elements. So J not equal to K, you are summing over all the off-diagonal elements. So this has been shown to be a good measure of coherence. So one thing you will see that this thing is not normalized, whereas our visibility was normalized. So we can easily introduce a normalized coherence if you just have a finite Hilbert space n. Then if you divide it by n-1, you will get a normalized system. So this is what we introduced, a measure of coherence. So in an interference pattern, so this let me specify that this measure of coherence is dependent on the basis. But in the interference pattern, our basis is sort of fixed by the slits. The particle coming from passing through one slit, slit 1, slit 2, slit 3, these states, they are actually orthogonal. So they actually give you a natural basis. So you can use that basis and write evaluate this coherence that basis. So this we have shown that for n-slit interference also you can get a very nice duality relation, very simple. This dq again defined in terms of unambiguous quantum state discrimination. This is for n-slits, and this coherence defined in the way which I have shown here. So this one can show that it follows a very tight duality relation. For the pure case, this will give an equality. If you are looking for a quadratic form, like just Englert's result for two-slit, this also has been shown that you can have another measure of distinguishability. So you get d square plus t square less than equal to 1. So to give you an idea what DQ is a maximum probability with which one can unambiguously distinguish between the n paths. So now the thing is that in two-slit experiment or an n-slit experiment, visibility can be measured easily in an experiment. But the problem is that this gives you a nice duality relation, but can this coherence be measured in an interference experiment? That is a problem. That all you have is interference is an interference pattern. How to get this coherence from that? So conventionally, I told you this visibility is defined as Imax minus Imin. So you can see that this is a typical three-slit interference pattern, which I have shown here. So this blue dotted line is how you measure visibility. This is the maximum intensity and this is the minimum intensity close to that. So you subtract these two and divide it by the sum of these two. So this gives you the visibility. So now what we propose is that you don't measure visibility this way, you measure visibility in a different way. That you take the maximum intensity and then you take the intensity if the light were incoherent, then all this interference fringes would disappear and you will get this blue curve. So if light is incoherent, this you will get a blue curve. So at the same point where you have this maximum intensity, if this light is incoherent, then this would be the intensity. So let me call this I incoherent. So if you write this I maximum, you take subtract I incoherent from I maximum, divide by I incoherent, divide by n minus 1, then lo and behold, you actually get coherence. This coherence which we have just defined here. So this looks very neat that by defining your visibility in a different way, you can actually get coherence for n-slit interference. So this idea has also been tested very recently, this year only, by this Chinese group in this multi-slit interference experiment. But the sad part is that in this scenario of the experiment which I was talking about, this thing doesn't work in that scenario because this derivation is actually based on this conventional interference which you get for a n-slit interference. If you flip the phase of one or do something more complicated so that the interference pattern, instead of getting degraded, it gets distorted. So if it gets distorted, then this formula will not work. This will work for a conventional interference. So although this method of measuring visibility gives you coherence, but still it will not work in this scenario given by this in this experiment. So now what to do? So now let me just go into a bit more details of this, how we get the interference pattern. So for an n-slit experiment, now let me write the state which is coming out of the n-slit as psi1 plus psi2 plus psi3 to psi n, and multiplied with that, correlated with that are these different states of the path detector. Again, remember this d1, d2, d3, etc. They may or may not be orthogonal. So we can write the density operator for this interfering quantum as this and take a trace over this path detector states. So you will get this. So let me point out here itself that if all these are orthogonal to each other, then you see that off-diagonal elements will all disappear. Only diagonal elements will be present. So suppose we do the following. Suppose we, from this n-slit interference, we open only one pair of slits at a time. Choose any two slits and close rest of the slits. Then the density operator for only a pair of slits at a time is given by this. So I am assuming that only IS and JS slits are open. Then you can write the density operator as this. So for now, this is a conventional two-slit interference. Two-slit interference. I can write very easily the interference visibility for this also. It is twice of rho ij divided by rho ii plus rho jj and multiplied by this inner product of di dj. And same way, because now I have only two paths, I can write a path distinguishability also the same way using unambiguous quantum state discrimination, and it is given by this 1 minus 2 times this factor and inner product of dj and di. So for these two slits, we can get a very simple duality relation, is dq is dq plus visibility. This is a conventional visibility less than or equal to 1. So equality holds again for pure quantum state. So this is a tight duality. So now what we do is we choose different I and j. I mean, close these slits and open another pair. So now what you do, if you do the same process for all pairs of slits, then you can average over all slit pairs and you get the following. So you are summing over this distinguishability for each pair, for all pairs, and basically this is dividing by the total number of pairs which you have. Same thing you do for interference visibility. So then you get a very nice duality relation, that this thing plus this thing, this is a measure of particle nature, this is a measure of wave nature, you get less than or equal to 1. So this is a new duality relation for multipath interference, which you can actually do because you are dealing with only two slits at a time. Now you see that this is all fine, but it looks very trivial because after all, when you are closing all slits except other than the two, you just have a two-slit interference. What has it got to do with n-slit interference? Is it anyway related to n-slit interference? So the interesting thing you can show is that, so the question is that, is this related to n-path distinguishability in any way? And this average visibility, average two-path visibility, is it related to n-path interference in any way? So this one can show that this is actually true, that if you average over the two paths visibility, you actually get coherence, the same one which was given by Plenius group. So that's very cool and very elegant. Same thing happens for distinguishability, that if you take this two paths distinguishability and average over all pairs of paths, then you get the n-path distinguishability. There is a separate definition for n-path distinguishability, but this turns out to be same as this. So then this distinguishability, this duality relation, which looks a bit more complicated, turns out to be the same as this distinguishability, this duality relation, which I showed for n-slit interference, same as the earlier result. So very good. So now the thing is that you have this duality relation, but now you know how to measure this coherence. You have to measure this coherence simply by measuring visibility for one pair at a time and then averaging over all pairs. Very easy to do. So this thing has also been experimentally tested out. So this is an experiment in which they do this for slit interference. They have closed the middle slit and slits are open, and then you can do it one at a time, different pairs at a time. Then you can calculate this coherence. So coherence can be calculated. And you can see that this thing works. So one can show that this thing works even when you have this complicated scenario in this experiment of May and White's, where they have flipped the phase of one of the paths and so on. So no problem with that. This method will work in that scenario also. So summary, measuring standard visibility for pairs of paths ultimately leads to n-path coherence. And measuring two-part distinguishability for pair of paths leads to real n-path distinguishability. And unlike n-path visibility, which increases in May and White's experiment with increasing decoherence, the average visibility from path pairs is always decreases. So the sort of unintuitive feature or feature which went against Bode's complementarity principle, that is no longer appears here. So conventional n-path visibility, where it fails, this average visibility from path pairs, this actually succeeds in that situation. So this can be treated as a method of quantifying interference in the n-path interference. So this new duality relation is always. So suppose we do this similar method classically. Because classically this n-path experiment has not been studied so well. So classically, if you do that, if you measure this visibility in the same way that maximum visibility divided and you subtract from it not the minimum visibility, minimum intensity, but the incoherent intensity, then you can show that this visibility is related to this coherence function, and this coherence function is what? This is just a sum of mutual coherence function for pairs of states. Okay, so you remember my first slide where I showed you that this thing visibility of interference was equal to the coherence function for two slits. Now it is just equal to the average of the coherence function for different pairs of slits. This is what we get from this. And from this, we also get an idea that maybe you can define an endpoint degree of optical coherence. So in optics, till now, people have not explored, people only talk of 2-point coherence functions. So an endpoint coherence function can be defined as this. So this is something which, whether it is useful or not for other purposes, so this has to be explored. Okay, so I think I am well before time. So let me just summarize this. So coherence now can be used as a new visibility in n-path interference. But the visibility has to be measured in a different way in order to extract coherence from it, and not simply as Imax minus Imin divided by Imax plus Imin. So you can use one of the two methods. Either you use this method that you take maximum intensity and subtract from it the incoherent intensity, or you can do the following, that you can open only pairs of paths depending on what is experimentally convenient to you. You can open only pairs of paths, then average over the visibilities which you get from these pairs of paths. And that is what will give you. Okay, so for further details, you can look at these references. So I think I'm done. Thank you for your attention.
Thank you very much, Tabish, for a very interesting talk. Now I invite questions. Please unmute yourself, or there's a chat box too.
Cool. Can I ask a question? This is Thomas.
Please, Thomas. Yeah, please go ahead.
Yes,
please.
Thank you very much. Thank you very much for the nice talk. Very inspiring. Does it mean, so if you can find the coherence in terms of the two-path coherence, so the average two-path coherence, does that mean that only two-path interference plays a role in this? So that we can forget about three-path.
Yeah, it seems so. That as far as coherence is concerned, only two paths at a time plays a role.
That's amazing.
Yeah.
Yeah. Is it? Can you say why?
Okay, why? That I don't know. Maybe it is related to this Bond's rule. I'm not very sure.
Sorry, to which rule? I didn't understand.
Bond's rule, because ultimately you take mod square of the wave function to get the intensity. So maybe it is related to Bond's rule.
Yeah. May I ask, could it be that, okay, it's not really multi-particle interference, right? I mean, if we had multi-particle interference, then that three particles come together is very the probability is probably very small. But this is not. This is one particle going through three slits,
Yeah,
so it's different.
one particle.
Sorry. Yeah. So this is not the reason. Okay. Thank you.
Yeah.
Thanks, Thomas. Any other questions for Tavish? Maybe I will ask you, take this opportunity, Tavish, for some clarification. So one is, in an experimental context, what actually determines the set of states D?
States D for the path detector.
Yeah.
Yeah, that has to be, that depends on the experimental setup. Yeah, so you have, in the experiment, you have to see that which states of the path detector get correlated with the different paths of the particle. Those will be the states.
Because, I mean, you have a vast amount of difference if suppose they are orthogonal or not. So can the experimenter have a control on this?
Yeah, so that depends on the experimenter, that he has to design the experiment in such a way. So sometimes you have a control, sometimes you don't have a control. So normally you would think that you have a control, because you ideally, if you want to find out which path the particle has taken, you want these states to be orthogonal to each other.
Right.
For example, in two-slit experiments, I can give you an example that if you can manipulate the polarization so that the polarizations of the particle going from the upper slit and the lower slit are orthogonal to each other. So this now polarization can act as a path detecting entity.
And you had, in your initial, the first inequality you had was C square plus D square smaller than or equal to 1. And then you had other things which were like C plus D smaller than 1. So yeah. What is the, I mean, is one stronger than the other or something like that?
No, for two slits, actually the difference is that, so for example, this one which was derived by Englert, so this is of quadratic form.
Yeah.
But So this one has a linear form. But here the difference is that this is defined in a different way. So Engler's distinguishability was defined in a different way.
Okay.
But you can have a similar form. So these two are quite equivalent. So now this has a similar form as Engler's. So that is not a problem.
And if I may ask one more, but maybe before that, I would ask if there are some further comments or questions. Others?
Can I ask one more?
Yeah, please go ahead.
Yeah, I just wanted to know, Tabish, whether you know the distinguishability is somehow has something to do with entanglement. I guess.
Yeah, very much.
Yeah,
it has to do
very
with
much.
entanglement. It is not possible at all.
Yeah, but also in the classical case, if you have a two-slit experiment and you just put a polarizer, a vertical polarizer and a horizontal polarizer on the two slits, then you would also lose the visibility.
Yeah.
And it's a similar thing.
Right.
Because yeah. But my question is, can you somehow say something about entanglement between two parties? You know, I mean, I'm not sure whether this is a reasonable question, but you know, in a multi-particle scenario, in a multipartite scenario, you know, multipartite scenario, one would have, you know, one can distinguish between the entanglement between always pairs or maybe three particles and so forth. And in your thing, it's more like we don't have entanglement between particles, different particles, but rather between different degrees of freedom.
Right.
And my question is it possible that I can measure with your distinguishability or with the coherence? I don't know which. Can I measure this two-partite entanglement? Can I measure this?
Yes, actually it can be done. So there's a work of mine which I can point to. This was published in Optics Letters, I think last year. So this, I think the title is Predictability, Distinguishability, and Entanglement. So there actually, what we have discussed is that using this distinguishability and coherence, you can actually experimentally know what the degree of entanglement. So yeah, so that is correct. What your guess is.
I find that very fascinating, if I may say, because you have such an easy way to measure it.
Right.
You know, with your maximum and the incoherent intensity. So this is the first entanglement measure that I think is like easy to
do. Right. So this actually I have proposed.
I want to see that. Yeah. Nice. Thank you.
Thank you, Thomas. Are there any other questions or comments? Maybe I will ask one final question, Tabish, about in a general scenario of diffraction or interference, how do these things carry over? Is there some more general study of that?
General study in the sense?
I mean, this looks like to me like a few slits, and it's like a multi-dimensional scattering or something of that kind, interference. Would that make any difference, and how does it?
Well, I thought n-slit interference was general enough. If you are, how more general are you imagining?
I mean, one can have all kinds of diffraction. This looks like more to me like usual diffraction grating, right?
Right.
And the interference from that. So my question is, if it was a much more general scattering of, so would that? I don't know how that would.
Yeah, I think the problem will become more complex, but these, I think, ideas can be carried over, because the take-home message is that if you want some kind of a path information, then you have to have, as this thing Thomas pointed out, that you have to have entanglement with some other degrees of freedom, which will give you some information about different paths. And generically, getting path information should affect interference or diffraction. So if there is whatever phenomena of diffraction is there, I think that should get affected by this getting path information.
Okay, if there are no further questions, last opportunity to ask. I want to thank Tabish for a very interesting talk and for allowing for time for discussions. Thank you, Tabish.
Okay, thanks.
Thank you very much. Yeah, our next speaker is Professor Thomas Conrad from University of KwaZulu-Natal, Durban. Thomas, can you share your slides? So Professor Conrad studied physics in Tübingen, London, and Constance. He is with the School of Chemistry and Physics in Durban, South Africa. His research is focused on quantum measurement and control, especially with optical systems. He is interested in the interplay between science and arts and likes to visit India for work and vacations. We're very sorry that you're not here in person, Thomas. Shortly, we hope to have you. So today, Thomas will be talking about quantum control with coherent or measurement-based feedback. Thomas, I'll alert you after about 40 minutes. Yeah?
Thank you very much, Harul.
Thank you.
Thank you very much for the nice announcement. And thank you to the organizers, to Subhashish for thinking of me. And indeed, I'm very sad that I'm not there, that I can't be there and that we can't talk afterwards and find new ideas or just drink a coffee together. Hello to all the viewers. And yes, I am very, very happy that I can be there, and thank you again for inviting me. I would like today to talk about quantum control, namely either with coherent feedback or with measurement-based feedback. And this is work done, some of it over the years, together with Herman Aes, who used to be in Stellenbosch in South Africa, but he was a professor there, but then IonQ, this is this American quantum computing startup, bought him out, and he is now in Maryland. Amy Rouillard is a master student of mine. Michael Kastner also used to be at the University of Stellenbosch. Then Subhashish Ghosh, who is at the IMSC, I'm sure you know him, and Sandeep Goyal, who is at ISA Mohali. Okay, so this is a picture of the Durban beachfront, and it is always compared to Florida because...
Sorry, Thomas, the slide has not changed.
Yes, the slide has not changed. That's not so good. Can you see the slide?
No, it's still on the
first
slide. It's still on the first title slide.
Okay.
At least for me.
And now?
I hope it's, can someone, yes, now we can see some beautiful beach there. Yeah, Thomas, please go ahead.
Oh, I see there is a lot of delay because I have already the third slide in front of me.
Oh, I see.
So
okay. Now I can see content. Okay.
Yeah, I'm sorry. There is a lot of delay. I think this is the reason, but at least it works. So what you saw before was a picture of the Durban beachfront. It's compared to Florida often because we have a lot of buildings that are Art Deco, like in Florida, and we have a long beachfront. And then you hopefully see now my table of content. Do you?
Yes, please go. Yeah.
Okay. The table of content is I want to start with an example of quantum control, and then introduce you to measurement and measurement-based feedback control. But I do that by first talking about how we can actually monitor the state over time. And then I go to how can we control the state over time. And afterwards, I try to introduce a method of coherent feedback control. That means we just look at the interaction of systems, and we totally stay in the quantum realm. There is no more measurement, no more information coming out of the system. But by bringing the systems together and designing the interaction in a certain way, we hope to control one of the systems so that we can drive it into target states or even target dynamics. Okay, and then I shortly, if I have time, I will talk about optical application. So I want to wait until Arul tells me that the new slide is visible.
Yes, we can see.
It's visible.
Yeah.
Okay, so this is an experiment, a very nice experiment, a very complicated experiment, a challenging experiment by the Harosh group, and Harosh got together with Wineland the Nobel Prize, as you might recall, because he is so good in controlling photons in a cavity. This is a microwave cavity, and it is, of course, a lossy cavity, so it will lose after 60 milliseconds photons. I mean, that's the decay rate. And in order to control this, he first measures the number of photons by sending in atoms that you see here, like these round circles. That's like Rydberg atoms. They have a very high orbital angular momentum, L equal to 50. So the electron is far out, and as we know from the principle of large quantum numbers, it looks classical. The electron has practically a classical orbit, but that's not the point here. The point is that they are very stable, and they interact with the photons in this cavity, in this microwave cavity, and they interact in such a way that they get a AC Stark shift in one of their levels. So let's say we consider here two levels, like I think L equal to 50, and then maybe there is a M equal to 50 and M equal to 49. And we consider these two levels, and one of them gets a stronger shift, is strongly shifted in the electric field, in the AC electric field inside here. And this shift in the phase of the atoms can be detected using an interference experiment. This is a Ramsey interference, a Ramsey interferometer that can translate the phase shift into a probability amplitude to detect the atoms here, either in one of the two states. Okay, so by making measurements here, you'll find something out about this phase shift, and the phase shift depends on the number of photons in the cavity. So this is, of course, unsharp measurement of the photon number. I will explain later exactly what I mean by that. But just in fuzzy terms, it doesn't allow you to, from a single measurement here, I cannot detect, I cannot say what is the number of photons here. I can just maybe give an updated probability distribution. I can say, yeah, with this probability, it will be this number of photons, and with the other probability, the other number, and so forth. And if you want to really know the number, you have to send a lot of atoms through, and then you get the number. So let me go to the next slide. And again, I wait until you give me the signal that you can see it. Sorry for this, but
yes,
I'm afraid.
you seem to have gone back.
Okay.
Yeah.
No, this
okay.
is a new one.
Yeah,
I hope this is a new one.
I can see the difference. Please go ahead.
Okay, good. So now you see a feedback mechanism. So this was really an experiment that was done in 2013, where the Harosh group measured the average number of photons in here, and as soon as the average number decreased by 1, they put a photon back in here. So this is a feedback mechanism that is based on the measurement results and based on calculating the state of the electromagnetic field here, or more precisely, the number of photons, the average number of photons, and then comparing it to a set point, like always in closed loop control, the usual classical closed loop control. You compare to a set point, and then you give feedback in order to reach the set point in case you're not yet there. So in other words, if a photon went out of this cavity, they try to put it back in. What they sent in was a coherent state with a certain phase and a certain amplitude, and then there was some scattering, and some of the photons would really land in the cavity. But the problem was to actually calculate whether the set point was reached or not, because this had to be done in real time. So the velocity of these atoms here is 250 meters per second, and this is maybe of the orders of millimeters long, I think. Maybe I'm wrong. Centimeters is I think centimeters better, but still you get something like microseconds, a few microseconds where the thing is in here, and so you have to be quite fast with your calculation in order to always give the feedback. But I have to say, I think a lot of atoms passed through, and then it was kind of in groups given, calculated and then sent in. But in their paper here, which you see here, they point out that it was difficult to get the calculation done in the time. So here's the results, and the results look like this. I hope you can see it.
Yes.
There is, or maybe it comes in a moment. There is here some detection of E and G. These are the two levels that you can detect the atom in. And then there was some calculation of the difference to the set point, the photon number. Here is the amplitude that is now derived from this. And then you see the average photon number, which was also calculated looking at the actually at the results from the atoms, and you see that more or less it stays around 1 photon in this case, and around like 4 photons in this case. So they were able to actually keep the photon number constant in a decaying cavity. But one has to say that this was not easy. Okay, this is not an easy experiment, of course not, but also because because of this actuator, you have to actuate, you have to react with your feedback mechanism on timescales that are quite small. So what I want to say is, what can we learn from this, and how can we make things better? And maybe one thing one can learn from this is that if you want to measure dynamics, then it is good that you use a sequence of measurements in order to know what's going on. You know, you cannot just make one measurement or no measurement. If this is like a dynamical process, you have to measure the system in a sequence of measurements. This was done here. Then an additional comment is you can use weak interactions if you want to avoid shelving in terms of the Zeno effect. So this was also a weak measurement. And then the question is, of course, can we get around this this kind of control here? I call it PID control, stands for proportional, integral, and differential control. So that's a way of modeling the present, the past, and the future of your system. But it is difficult with quantum systems. So because of the time scales, and also because of the measurement process and so forth. And here comes the last question: can we, instead of using this classical information that we get from a measurement, can we get away from this? Because this is what makes it slow, maybe. So I want to shortly talk about unsharp measurements, and then tell you what one can do with monitoring as a quantum system. So here is a two-level system, and if you start in this on the x-axis, and you make a measurement of sigma z, which is the z component maybe of the spin of a two-level system, or you know, the E and G component of these atoms that we had before. And then in a projection measurement, you project onto one of the eigenstates of this observable. But in an unsharp measurement that is mostly given by such an indirect measurement, so where you couple to your system with some probe system, and then you make a measurement of the probe system, it's not necessarily a projective measurement. It might just drive the system state in direction of one of the eigenstates, so either to here or to here, depending on so-called measurement. I mean, this is like, they are called effects. And these effects allow you to calculate the probability given the state the system is in before the measurement. They sum to 1, and then you have measurement operators, or sometimes also called Krauss operators. I mean, Krauss operators may be more general. In this case of the measurement, one would call them measurement operators, and they make this movement here, and you see it's proportional to the square root of EI in case that you have a minimal disturbance, but you can also have more disturbance, and in general any operator can be written in this polar decomposition. That means as a unitary part times a positive part, and the unitary part can incorporate feedback, and that's where I want to go in a moment. I want to point out that in an unsharp measurement of an observable O, you need that all effects are commuting and are commuting with that observable, and then you can estimate the expectation value from the measurement results, just as Harosh did in his measurement. His effects are commuting with the number operator that is the observable of the electromagnetic system. Maybe I forgot. Now it's going all higher. Sorry, I have to. I'm sorry. I have to put a small break in. I pressed the wrong button. I wanted to say that the difference between the eigenvalues here tells you something about the measurement strength. If the difference is 1, then you have a projection measurement, very strong. If the difference is 0, then you have no measurement at all, infinitely weak measurement, if you want. So state monitoring, works like this. If you have, I mean, in the way we do it. Okay, so this is the way that was developed by Lajos Diósi and Jürgen Aurich and others and myself, but I'm not saying that we are the only ones that use it. But in our idea of state monitoring, we always use pure states instead of mixed states. So you could say If you don't know the state of system, use a mixed state. But no, we then just use an estimate of the state that is a pure state, and then we update it using the measurement operators. Okay, and this is just a normalization constant, because these are just entities that are on the paper. They are not the real states. And in a sequence of measurements, here you see unitary evolution, and then one of the measurements, either you get the result plus or minus, and then unitary again, and so forth. In such a sequence, you can start to get perfect state information. However, not about the initial state, but only about the state as it evolves. And here is a limit, which I want to call the Bacchielli limit, although it's written wrong here. Here delta P should go to 0, not to infinity. So if you go to a limit where the period between the measurements becomes arbitrarily small, and the measurements become arbitrarily unsharp, so very unsharp, then you can describe the whole system in terms of continuous measurements, and you can write down these differential equations, stochastic differential equations, which contain this Wiener increment, and yeah, you can describe the system as well as the estimate in this, and the system and the estimates equations are coupled, because in the signal here, this is the increment in the signal, there is always the expectation value with respect to the state of the system, even if you write the equation for the estimate, because it depends on the system what happens, not on what you write on your piece of paper. So the estimate is coupled to the system, and then it is pulled towards the system in some sense. I will show you in a moment. Here are some time scales, and the time scale of 1 over this gamma, which I can see as the measurement strength of the continuous measurement, is like the time that you need to resolve 2 levels. I'm here looking at a measurement, continuous measurement of a 2-level system. And if that is very much smaller than the time that it takes to measure, the time scale of the evolution of the system. So here's a Hamiltonian, which is the natural evolution of the system. Then you end up in the Zeno effect, because you hammer the system into a particular state. And in the opposite regime, where the level resolution time is much bigger than the period. I mean, I call it here the Rabi period, because I'm thinking of Rabi oscillations, but it could be any. Yeah, I mean, for 2-level systems, I guess there is not much more than these oscillations. So if this is much smaller than the level resolution time, that means you never really see the level resolution, and then you don't disturb the state much, but you still get information out of it, and that can be used to monitor the state. And I can show you here an example. So usually, if you have a harmonic oscillator under some noise, then the actual state deviates from the desired state, and you don't know where you are. But if you do these unsharp measurements, then you have here the actual state is the black one, and the red is the state estimate, and you propagate both with the same, according to the measurement results, with the same measurement operators, then you find that you always know where the system is. Okay, and you even in the presence of noise, you see with a high fidelity, you have a high estimation fidelity of what the system does. And here I want to show you a graph of a system that is subjected to a chaotic potential. So it's a quantum system. If I take just the expectation value of the naturally moving system, then I get something chaotic like this. But if I measure it, then the following happens. Here's a small movie. You see the red thing.
At least for
Yes.
me, there is a bit of a time lag. So now it's fine. I mean, now you're in the simulation.
Okay, super. Thank you very much. Yeah. This is important. While we are talking, how much time do I still have?
You have about half an hour more, I think.
Okay, wonderful. I don't need more. Okay, so maybe tell me if 15 minutes are left so that I get to the end. Okay, so here is two wave functions. I mean the modular square of the wave functions actually, and the one is the blue one that's of the real particle that is moving around in this Hennen-Hales potential, and then the red one is the estimate. And both are moving, and we do a continuous measurement. This is a simulation, of course. And then we update both according to the measurement results using our, we could think of cross operators, but we can also do it continuously in the simulation. And then you see how they dance around each. Oh, this was wrong. Sorry, I have to go back. Now we have the delay again. I hope at some point you see the stance of the wave functions. Can you see it?
Yes.
Okay, and you see the fidelity here. There is a fidelity bar. So as time goes on, the fidelity becomes higher and gets higher and higher. And now to add some drama, I have a particle that collides in 1 second with the real particle. And then, of course, the fidelity goes back to 0. And the red one chases behind the real one. So the estimate chases behind the real wave function. And look at all these chaotic peaks there. But the fidelity starts to grow. And in the end, they are perfectly together so that you have really a way to monitor the wave functions using these unsharp measurements, the sequence of unsharp measurements. And it goes back to, yes.
Yeah, it looks pretty cool, but let me just ask whether the fidelity, I mean, there are clearly interference patterns and there are these sharp peaks that are coming up.
Yes.
So is the fidelity larger when you have these almost coherent kind of states, or it's also when you have a very complex state, it's able to catch that?
Yes. So look, this is a very complex. This is not just a Gaussian, right?
Yeah.
And before also you saw all these peaks, and the fidelity is that high. And what that means is that not only because we were only measuring here the position. Actually, I should have explained that. We were measuring the position of the particle.
Yeah.
And not only do we get information about the position, so about the wave function itself. I mean the modular square of the wave function, as the picture shows, but the fidelity is really the overlap. So the phases are in there as well.
And also,
okay.
you must
So
be
this is
doing a coarse graining of the space because you're having a continuous space. So
sure.
Yeah.
Of course, I have to. I mean, this is still, there is some numerical uncertainties in there. I mean, or it's not perfect, but within what we want to know on these scales here, micrometers, this is quite fine. I don't know how many we did. I think 10,000 or 10,000 small fields here, right? You can look it up in a paper that came out in 2000 and I think, let me just think, about 2010 or 11 with Lajos Diósi. And yeah, so this is this. And I just want to understand or tell you what I think the mechanism is behind this. I mean, why is this so, right? And you all know that if you have a channel, a trace preserving channel, then there is the monotonicity. So this is a channel, you can always write it in terms of cross operators. And then there is a monotonicity of the fidelity. That means if you start with two wave functions, rho and sigma, and you look at the wave functions later. I mean, here I'm actually using, because we are dealing here with mixtures, I'm using density operators. And you look at the density operators after the channel, then they are closer together than before the channel, before the action of the channel. That's always like this. But the reason for this is that you basically shake the system in some incoherent way, and then it looks always the same. So if you think of starting with pure states, let's say you have two level systems. You start on the surface of the Bloch sphere, then you wander inside the Bloch sphere. And of course, if you come from different sides, from different states, with different pure states you start, afterwards, if they go inside the Bloch sphere, if they get mixed, yeah, they look similar. They come closer. So this is not really that you know more about the system. In fact, you know less about the system. You just take the system, you shake it a lot, and then it looks, all systems look the same if you shake long enough. Now, what I want to talk about is another monotonicity, and that is for probabilistic operations. So if I take a pure state and I
sorry, Thomas.
Yes.
What is your definition of fidelity?
What is my definition of fidelity? Well, for mixed states, it's the one with the with the trace of the square root, and then you take square root of rho times sigma times square root of rho.
So that is the Beer's metric fidelity.
Sorry?
This is just the Beer's distance which we take for fidelity, right?
I didn't understand the word.
B-U-R-E-S, Beer's.
Beer's, yeah.
Yes.
Maybe, I don't know. To be honest, I don't know. But I mean, you probably know, Subhashish, you know this, you know the monotonicity for trace preserving channels, right?
I know that, but my question was whether this will depend upon the form of the fidelity that you take.
No, this is, I think, I think this is always the case. I mean, this is, for me, this is natural that, you know, if you wander in the inside, if you get more mixed, of course you get, you know, you get closer to each other. Maybe, you know, I have a too simplified picture with my two-level systems, but one can prove this for the usual fidelity. I forgot the name of the fidelity. There is another name that always comes up with fidelity.
Okay.
But you know what I mean. I can tell you later again. It's the usual, the trace and then square root rho.
Okay.
I mean, you know, the square root of rho up to the power half times sigma.
Yeah, then sigma, then rho up to the power half. Yes.
And then you have to square it, I think. Or sometimes people square it, sometimes not. But that doesn't matter. So here in this scenario, I'm just looking at pure states. So I say, look, let me take one state and let me make a probabilistic process where I so it's not trace preserving. I just map it to with some cross operator onto another state. Here's a normalization constant, and then I compare the fidelity of two states that underwent the same process with the same cross operator, the same probabilistic process, and I compare the fidelity after the process with the fidelity before the process. And if I have different processes that can happen, namely I equal to 1 from 1 to n, then this fidelity here, this average fidelity here will be greater than this fidelity. So this is a different picture. Now, if you think of the Bloch sphere, this is like you really you keep the purity of these things, and you can even think of if you started in the middle of the Bloch sphere with two states, and you would undergo such a process, then you would move, you would become purer. You would move towards the surface of the sphere, and this is what happens in these measurements. You move towards the surface of the sphere, but you move closer to each other. and this can be shown by this thing. On average, you move closer, and this is what we saw. The wave functions on the wave functions. If you continue long enough, the wave functions in the sequence of measurements, they become purer, and they become closer. You can think of this like a filtering process. Okay, if you run two systems to the same filters, then of course they will come. You select always something out of them. They will become purer and they will become closer. Will get closer. So this is the idea here. And now I just want to point out a mechanism. I mean, we can put this mechanism just like this, that we say, okay, if you start with two states, let's say with this state and with this state, and I have the same measurement result, and I end in one case I end here, the other case I end here, and I look now at the angle afterwards and the angle before, you see that the angle is smaller, and that is because this is a point where they converge towards, right? But the same thing happens even if you have dynamics. Then the dynamics is kind of rotating the sphere, but still the same process happens. So I want now to use this to convince you that one can do something with feedback that is based on the measurement result, which is much simpler than calculating the difference to the set point and using PID or something. And the way this is done, this is a special control scheme that was developed by Hermann Eis and others a few years ago, and it works like this. So if you think of, you make a measurement, an unsharp measurement, and you start in your target state. Let's say this is your target state. You want any state to end in this state in the end. But your real state is actually this state. And now you make a measurement, and the measurement will transform the real state into here, into this state. And your target state, if you just look what would happen if the system were already in the target state, it will move to here. So now, in the next step, we apply a unitary feedback that rotates the state that we would have gotten if we had started in the target state back to the target state, because we want the target state not to move. And if we do that, then the real state, which actually went to here, will now come down to here. And if you compare these two angles now, you see the first angle, that is after the measurement part, and then the angle after the feedback part, they really become closer. So this angle is much smaller than before. And if I repeat that, then on average, I will end here. So this is the scheme, and we called it self-fulfilling prophecy because we searched for a nice name, of course. But it is because if you assume that your system is already in the target state and you just protect it, I mean, you measure and protect it by moving it back, then it will finally end in that state. Okay, so this is the self-fulfilling prophecy scheme, and one can now do nice things with it by looking. We started with a state orthogonal. This is for two-level system, orthogonal to the target state, and then we do these sequences of measurements with feedback. And after some number, okay, this is quite high still. A high number of things, we end in the target state for the orthogonal state, but actually we end always in the target state, which I will show you later. And you can get much faster there if you increase the measurement strength. Okay, so you can also use that to go into target dynamics. So I can, if I have a certain, I have a certain Rabi frequency. So this is the frequency, the frequency pattern. I mean the frequency spectrum, Let's say I have even some noise in that frequency spectrum. No, let's not say I have noise. Let's say this was the original peak, which is peaked at some frequency 1. Now I can use my feedback scheme by making the target time-dependent function to accelerate the system, the rotation in the system. So afterwards, it's here. And the other thing I want to show you is that if you have, if noise is present, so this is with noise, so without SFP scheme and in the presence of noise, I have a Fourier spectrum like this. And now I can protect the system against noise by putting the target state time dependent and then make the measurements and act accordingly on the system, and then I get this black curve which has less noise, as you can see. So the red fizzle around here is gone, and we can also produce states that are kind of so we can produce exotic dynamics here on the surface, 8 on the surface. There is a state that came from here and joined here. Then there is another state that joined here at the North Pole, and third state, this state joined here, but then they all go together around. So this can all be done, but I want to show you still another scheme to do these things, and I don't know how much time do I still have.
You have about 15 minutes, Thomas.
15 minutes, okay. Then let me try to only do 5 minutes here. I'm not sure whether I can do it, but let me try. Okay, so now I want to go to coherent feedback control, which is you have a 2-level atom and you have other 2-level systems that scatter of this 2-level atom, and then there is an interaction. Let's say it's in a sequence, and in the end, I want to have this system in a target state. This is the idea, and let me try to explain it at a simple example. So, by the way, these two schemes, this scheme that I now tell you, this coherent feedback scheme, is related, of course, to the first, to the measurement-based feedback scheme. In fact, it is just the unitary version of the first one. And let me show you how this works. So from this, we just want to have unitary coupling between the controller, which is now a quantum system, and the system itself. Okay, so let's assume I start in this superposition of 2 states. I have here 2-level system, and this is also starting in some superposition. And in fact, this one is the target state that I want to reach, but now encoded in the controller, and I want to transfer to this to the system, the target state. So what I do is I first take a rotation that rotates the controller into one of 2 orthogonal states, namely either 0y or 1y, depending on the component that comes here from the system, so that you can think of like I'm marking the basis states of the system in the first step, and then in the second step, I now rotate the system conditioned on the pointer. So this is like a pointer state, and now I take this pointer state. Let's say I'm in 0y, then I say, okay, if you are in 0y, then please rotate this thing about the y-axis about an angle of 90 degrees on the Bloch sphere, let's say, and then you go from 0 to 0x here. And if you are together with the marker 1y, so here I am, you know, I mean, this is the state that came out of the first step. I'm now in the second step. If you're together with this state, then rotate, please, the system in the opposite direction. So you can think this was the North Pole, and you rotated it into the equator onto the x-axis. And if you are at the South Pole, then you make the opposite rotation also about the y-axis, and you also end up on the x-axis of the Bloch sphere. So in both cases, you ended up on the x-axis. You are now in a product state, and you reach your target. That means in one step, you made it actually from any initial state into the target state. Okay, and this can be done by using these unitaries here, and we can put them together because they actually commute. The generators here commute, and then I get a unitary like this, and there is a coupling constant. So in this particular case, I had a certain value of the coupling constant, but I can use any lambda value, and then I get to the target state. So let me show you this on the Bloch sphere. So what I did here is I cut the Bloch sphere into two hemispheres. So here I just have the southern hemisphere, and then I look at each point. This is my target state at each point, and each point is kind of moving. Now this point is moving here into the Bloch sphere. So this is now a mixed state, and this point is moving here, and that point moves there, so that you can see that the whole of the Bloch sphere, the surface of the Bloch sphere is now lying within, after the first step, within the Bloch sphere. And then it moves inside here, and in the end, it moves to this point. So I contract the whole Bloch sphere onto this, which shows that all the states are going there, and I used here a certain value of lambda that corresponds to weak coupling, but I can make it even weaker. And I will always end here. And this is my point. So I can give you unitaries, and this is not the only example. I can give you many unitaries. This is a page. I cannot say much to it. It just means we have the same structure as before, namely unsharp measurement and then some rotation. This was what we had in the measurement-based feedback as well. I have now to be fast. There is a theorem. Okay, maybe I want to go back. No, I don't want to go back. So there is a theorem, or we've proven a theorem, and it's on the archive. You can see that if we have a fixed point condition, namely this condition here, that means that the target state will always stay the target state under any of the cross operators that you get from this unitary interaction. So this is now the channel. Sorry, I'm probably going too fast. But I want to say I write down the channel by tracing over the controller, and then I get these cross operators. And the cross operators must be such that they treat the target state as a fixed point. And then on top of it, you have a different condition. A different condition, and that is that makes sure that there is only one fixed point. Then you can show that the corresponding channel, if you apply it enough times, will always lead to the target state. In short, you can think of Banner's fixed point theorem, and then you have it. Okay, so that's the point. And now I go and tell you nothing else. I mean, there are other schemes that you can read up in our paper, and we can also talk about entangling systems by having this interaction on one side and on the other side, and then between these atoms, so that they get entangled. Then these atoms will end in an entangled state, and it is resilient against noise. If you ask me later, I can tell you how. And here is the last thing, namely we can use it for the preparation of light modes. This is a new work together with Amy, Tanita Permol, another student of mine, Sandeep Goyal. And Sandeep has a very nice scheme how to, how to actually implement any unitary for a two-partite system, and we used it here for optical systems where the two parties are different degrees of freedom of the light. And then in the one party, namely the party that we consider as our system, let's say it's the light mode, so the spatial mode of the system, and the other system is under degree of freedom is the polarization. In the light mode, we act with these M0 and M1, and here's two other things that are not so interesting for the moment. And then we can really, due to Sandeep's way of decomposing such a unitary in controlled schemes. So this is like the 1 degree of freedom conditioned on that my controller is in this degree of freedom. This operation will happen on to the system, and then I have here like a beam splitter. So this is like a quarter wave plate where from one polarization I get into a superposition of polarizations, and then there is another conditioned operation, and again a kind of quarter wave plate. And so this gives an interferometer with some conditioned operations on it, and we can implement everything in one beam. So here is a beam, it goes in here. Depending on the polarization, there will be a change in the mode because it gets either reflected here or it goes straight through. Then there are some wave plates, another of these conditional operations, and so forth. And this thing here is exactly implementing what we saw in the beginning in the simple example. So there is an easy way to prepare a photon or even a classical beam in a certain mode without actually losing any intensity. And with this, I want to close because I think I'm far over time. I'm very sorry for this, but it always happens. Maybe I shouldn't try to talk to present so much. Thank you very much.
Thomas, you're perfectly well on time. In fact,
I hope we have time for questions.
For questions too, yeah. So, questions, comments, please.
Can I ask something?
Yes.
Yeah, sure.
Yeah. So this in thermodynamics also we talk about the thermalization process where every initial state will thermalize, right? It will go to a fixed point, right? It will go to a particular target state, right?
That's right.
And there are several ways of achieving that. One can use, for example, this GKSL type master equation. One can use some non-Markovian process also. So, so I would like to know this scheme that you described here. What sort of, I mean, in terms of Markovianity, non-Markovianity, what sort of process is it?
Yes. Okay. So it's Markovian, and because we have the sequence of interactions. So you take always the system, and okay. Look, it depends on what you look at. Whether you want to look at the whole system, which is basically the system that you want to control and the controller. In that case, it's Markovian. Okay. If you forget about the controller and you just look at the system, then it's also Markovian because it's just the application of a channel. It just depends on the state of the system before the interaction, what happens afterwards. So maybe we have it somewhere. Let me see. So if you look at this is one application of the channel, right? And you start with some state rho with the system, and then you you get another state that only depends on the state before. But Subhashish, I must say, I'm not super sure. I never thought about the question. So it might be, no, I'm sure. I'm sure. I tell you why. Sorry that I'm waving here. So look, the system after, this system only interacts once with the, so the controller, this controller only interacts once with the system. Then it's gone and we trace over it. We are not interested in it. Okay. And then the next system comes and interacts. So I think this is it doesn't depend on the history of this.
So this is like, this collisional model of Markovian process where your bath is, bunch of, qubits, each of which are in a thermal state, and then your system qubit interacts with the first bath of the qubit, then you get, cut off the interaction, then the system interacts with the second bath, and so on and so forth.
Yeah, you must be careful. It's not a bath because I assume here temperature 0.
Yeah.
Okay, so it's not like they are in pure states.
Yeah, that's okay. I mean, this is, not just thermalization. You can call it homogenization for any state of the bath.
Okay.
And actually, just to add to that, Subhashish, right? I mean, the partial swap plays a crucial role there as well.
Exactly. Yeah. In fact, that is the only operation through which you can achieve homogenization.
Yeah. Okay, but that's not. I know this result. Okay, but I don't want to have a homogenization of everything. I mean, I think you're talking about the paper of Juzin, right?
Yes.
And he talks about he wants to put this thing basically also in the bar. So everything should be at the same, should have the same state.
Yeah, to begin with the same state. Yes.
Yeah, but that's not what I want. I mean, that's correct. In that case, you need a partial swap. But I'm happy if you produce a different state here than these things have.
Okay.
So let me explain. I'm not interested in homogenization. I'm just interested in reaching a target state. I even want to reach target dynamics. And it is true that if I use partial swaps, that then I reach a homogenization, and this has advantages because in these partial swaps I can, without actually knowing what the state is here, reach a target state. So I can, the state of these things could be the result of some quantum computation, and then I have here a system that's like autonomous. It doesn't depend on what I want to produce. It can regulate itself. But I want to point out that there is a big class of channels and a big class of unitaries that all fall into this class of unitaries that can reach a target state. That produce here a target state. So it's just that they have to have a fixed point, and it must be unique fixed point. And there are many, not only the partial swap, many. And you can use them, right? So this is my answer. Is that answering your question?
Fine. Okay, thank you.
Thank you so much. Other questions or comments? So Thomas, from my side, can I ask about two things? One is the rate always exponential? And two, is there something special about qubits that you have used, and how does it extend beyond?
Okay, is the rate always exponential? Let me just go through I mean, here I'm using these partial swaps. Sequence of partial swaps gives a full swap. So here you have such an exponential increase, but it's not really exponential. I mean, yeah, how can I say this?
Yeah, so this gamma, if it is equal to 1, that would make that.
That would mean we start already in so after the first one.
So sorry, gamma
if
equals
gamma
zero.
is equal to
Gamma
1,
equals 0 is the case when the exponential would break.
gamma equal to 0 is the case where the exponential breaks. Correct.
Yeah.
This is correct. But you know, I always thought, you know, it's not. Does it mean that you need only logarithmic number of steps? Because I have the feeling it's not true. I mean, it looks. I agree. It looks like exponential. Yeah. Okay. Maybe I'm confused. It is exponential.
Yeah.
Yeah. No, for this kind of, for the weak swap, it is exponential. And for the other example we had before, it was also exponential.
Okay.
Same thing. I don't know for others.
Okay.
And then the second question, you can do it for higher dimension. It's not a problem. So with the weak swap, you can do it in any dimension.
Okay.
You know, this is look, this is I and J. This can be anything.
Yeah. Thank you very much.
Thank you. Thank you for your question.
Questions? Final opportunity. If not, let's thank Thomas for a very interesting talk.
Thank you.
Thank you, Thomas.
Thank you, Subhashish, for asking.
Thank you
for coming.
We move on to the third talk of the session. Dr. Christian Boudreau.
Hello.
Hi. Hi, Christian.
Hi, how are you?
Good, thanks. And must be rather early where you are.
It's almost 10 in the morning now.
Oh, okay, good. That's so. Welcome, and can you please share your screen meanwhile?
Yes.
So we're very happy to have with us Dr. Christian Boudreau. He is the Department of, he's at the Royal Military College, Saint Jean, Canada. And today he will be talking to us about universal, well, here there's a slightly different title. So he's talking about using symmetric qubit clusters to protect quantum computation. Christian, I will warn you maybe after about 40 minutes or so. Yeah.
All right. Thank you.
Please go
ahead. So yes, I will talk about using symmetric qubit clusters to protect quantum computation. This is work done in collaboration with Hisham Iluk, Michael Hilke, and Richard McKenzie. So it's fairly common knowledge that quantum computers need to protect their states and operations. And it's also known that there are possible advantages of using higher alphabets in secure communications. So we will consider 4-level systems with an additional symmetry as our basic computational units. We'll call these 4-level systems clusters. A cluster will be 2-qubit universal or 1-q-quart universal. The symmetry that we have studied, that we have used, seems to protect operations against anisotropic noise. I will discuss that in a moment. And somewhat contrary to intuition, the symmetry that we use allows enhanced freedom for physical implementation. So intuitively, asking for strict symmetry is something difficult in practice, but I will show that the symmetry that we use, because it corresponds to a highly connected Hamiltonian, actually might allow enhanced freedom in the implementation. So let me discuss what the cluster is. For definiteness, I'll think of the cluster as two coupled qubits with an additional symmetry. So the cluster is a 4-level system able to take two distinct forms. Here on the left, we have the passive off form, where the states will always correspond to the states of the logical basis, and the Hamiltonian is almost diagonal in the passive off form. So in this form, the cluster is doing nothing. It's just waiting, or maybe it's interacting with other clusters, as I will discuss later on. And the cluster can also take an active computational form, as seen on the right, where now it is not a diagonal anymore. It is actually performing a calculation on its qubits, and it has a symmetry. And the symmetry that we have used is a slight generalization of rotation invariance, where the Hamiltonian would be a circulant matrix. Now our Hamiltonian is what we have called an omega circulant matrix in the logical basis. I will define what that means in a moment. Let me just go back quickly to the off form, where the cluster is waiting or maybe performing interactions with other clusters. The Hamiltonian in this form has self-energies which have large energy offsets, so large compared to the transition amplitudes Kmn, and this effectively suppresses transitions in this form. I will come back to the off form later on in the talk, but for now, let's move on to the active form. So the first form that we considered for the active form, the first symmetry that we considered was a rotational invariance. So you look here at the transition amplitudes, you see that the system is completely invariant under rotation by 90 degrees. And the corresponding Hamiltonian is a circulant matrix. So a circulant matrix is defined by its first row, and then you get the other rows by simply shifting each row by 1 unit to the right. So in particular, all the self-energies are equal. All the nearest neighbor couplings are equal. Second nearest couplings are equal. And if we ask, in addition to circularity, that the Hamiltonian be Hermitian, then of course self-energies are real. Second nearest neighbor couplings are real. Nearest neighbor couplings can be complex, however. So nearest neighbor couplings are given by two real parameters, alpha and beta. Epsilon and gamma are real. So the Hamiltonian is described or parameterized by this collective parameter G, which is a point in R4. Circulant matrices have nice features. They're diagonalized by the discrete Fourier transform. So they all share the same eigenbasis. Their eigenenergies are in one-to-one correspondence with the points in R4. In fact, they are given by linear combinations of these parameters, Gj, so these epsilon, alpha, beta, and gamma. Circulant matrices form a commutative algebra with exponentials. So they all commute with one another. They all have the same eigenbasis. Sums, products, and exponentials of circulant matrices are circulant as well. And that implies that circulant matrices are not enough because they are not universal. They can't possibly be universal because most 4x4 unitaries are not close to any 4x4 circulant matrix. But starting from a circulant Hamiltonian will produce only circulant unitaries. So that's not enough for universality. Circulant matrices have nice features, but they must be augmented by something else. And we do that as follows. We move from circulant matrices to omega circulant matrices, which are polynomials of this matrix J omega, where J omega is defined here. It's a modified shift matrix. So you see that when omega is 1, it's just a standard shift 1, 1, 1, and 1. So a matrix which is a polynomial of J1 of the regular shift matrix is nothing but a circulant matrix. But omega can be any fourth root of unity. And with the other values, other than 1, we get a new class of matrices. we can also think of circulant matrices in terms of generalized Pauli matrices. The generalized Z is this phase shift matrix. The generalized X is just the regular phase shift, which we have called J1, J omega when omega is equal to 1. And the combination ZX is the generalized Y Pauli matrix, and it corresponds to J omega when omega is e to the I pi over 2. So circulant matrices are polynomials in X. Omega circulant matrices are polynomials in these combinations of these matrices, X, Z, and Y. So circulant matrices, again, form what we call the symmetry class X. They are polynomials of this matrix X, which is just the regular shift matrix corresponding to omega equals 1. This is what the general Hermitian circulant matrix looks like. The 4 complex parameters are not independent because of hermiticity. In fact, they depend on 4 real parameters, the collective parameters G that I talked about earlier, epsilon, alpha, beta, and gamma. Again, eigenenergies are in one-to-one correspondence with the points in R4. Circulant matrices constitute a commutative algebra with exponentials. So they're good, they have nice properties, but not enough for universal calculation. They must be augmented by something else, and we do that by considering symmetry class Y. Symmetry class Y corresponds to polynomials in this matrix Y, which is what I have defined before. So it's this shift matrix when omega is the root of the imaginary unit I. So we can consider polynomials in this modified shift matrix, and asking that they be Hermitian again leaves only 4 real parameters, and the most general Hermitian Y class Hamiltonian looks like this. It has pretty much the same form as circulant matrices. I have used exactly the same parameters, so we see that self-energies are equal in real. The taus can be complex. The only difference with a circulant matrix is that we have additional factors in front of the tau. So I to the 0, I to the 1, I squared, I cubed. And similarly for second nearest neighbor couplings, gamma has to be real, but there is this additional phase in front that was not there in circulant matrices. And symmetry class Y has all the properties, all the nice properties of circulant matrices. It's diagonalized by a generalized version of discrete Fourier transform. So all the Hamiltonians in class Y have the same eigenbasis. Their eigenenergies are in one-to-one correspondence with the points in R4. They are again given by linear combinations of the parameters, epsilon, alpha, beta, and gamma, and they form a commutative algebra with exponentials. So again, alone, they cannot be universal, because if you start with a Hamiltonian of class Y and you exponentiate, you get a unitary of class Y as well. And since most unitaries, generic unitaries, are not close to a unitary of class Y, it's not enough to have universality alone. But if we use this class Y together with class X, we do get universality. So a 2-qubit cluster that can realize both classes is universal on 2 qubits. In fact, we have this stronger statement that if I define Hamiltonian Hx in class X, as written here in equation 6, and the Hamiltonian Hy in class Y, as written here, and I define the corresponding unitaries VW, then this set VW is strictly universal on U4. Any element of U4 can be approached to arbitrary accuracy by a finite sequence of V's and W's. We have we have a lot of freedom in the choice of hx and hy. Of course, if I pick, well, it's not true that any Hamiltonian from class X together with
Sorry,
any
Christian,
Hamiltonian from...
I just have a quick clarification. What is x0, x1, x2?
Oh, it's power 0 of...
Oh, I see. It's powers. Okay.
Yes, power. So power 0 of...
x and x squared. Okay.
Exactly. The identity x and x squared. Yes. So, for instance, if I take the identity, which is in class X, and the identity, which is in class Y, of course, it doesn't produce a universal set. So, but we do have a lot of freedom in the choice of a Hamiltonian from class X and a Hamiltonian from class Y that will produce a universal set. And that freedom allowed us to pick hx and hy non-degenerate in this case. This is a desirable feature to prevent untimely transitions due to couplings with the environment. We have tested our universal set VW against noise. So we tested its fidelity against the following error set, the Pauli error set, where we have 15 errors, 15 unitaries, because A, B range can have values, well, stand for X, Y, and Z. So we have 15 combinations generated by the 15 Pauli tensors, which, in addition to the identity, constitute a basis for 4x4 Hamiltonians. So we have tested our universal set against this error set, where the couplings that we have used were normally distributed. And we have compared the performance of our set with two other universal sets, the Slater-Weinfurter set, where A is some entangling version of C0. Swap is the swapping gate, of course, and the Kitaev set, which has the Hadamard on the first qubit, the controlled phase, and the swapping gate, which allows the operations to be performed on the other qubit as well. These two sets are finite. We chose them for ease of numerical implementation, and we compared their performance with our set. And what we find is, well, is particular. We were not. It was somewhat counterintuitive. What we found that V and W constitute a set which is particularly resilient to XZ errors. So errors generated by X and Z Pauli rotations, Pauli matrices. On the other hand, Y rotations are particularly disruptive for this set. This is, so I represent that in the following graphs. On the left, we have a comparison between the three sets where all errors have equal probability, but X and Z rotations, errors containing an X or Z Pauli matrix, are more biased than errors containing a Y rotation. And we see that our set is at a clear advantage. The blue set is VW, the green set is Kitaev set, and the orange one is the Slater-Weinfurter. And on the right, we do the same calculation for average fidelity, but now all couplings are equally distributed. They have no bias, an average of 0. They have the same variance, but X and Z errors are more probable than Y. We pick errors randomly in the sequence of calculations, and X and Z will occur with higher probability than Y in the noisy sequence. And again, we find that our set fares better than Kitaev and Slater-Weinfurter. And we were kind of surprised because it's not at all obvious why this would be the case, why X and Z errors would not be particularly disruptive with the omega circulant symmetry that we are using. we still have to determine whether it's true for it's true only for the set VW or whether it's really an effective symmetry. But what I want to say now is that if one is willing to break omega circulant symmetry, but by preserving what I will now describe as a flux structure for V and W, then these results will remain true. But for a vast number of Hamiltonians, a manifold, continuous manifold of Hamiltonians having the same flux structure, but no more omega circulant symmetry. That's what I will discuss now, the flux structure of X and Y classes. So we can look at an omega circulant Hamiltonian as a U1, as having a U1 gauge potential. So here I represent the system, so the 4 logical states or the 4 levels of the system together with their couplings. Notice that the system is completely connected. Any level is connected with any other level. And the transition amplitudes, the components of the Hamiltonian HJK, can be written in general as a magnitude and phase. And these phases, theta jk, can be considered as a path integral over this gauge potential A. And this defines a gauge invariant structure, mod 2 pi, of fluxes through the triangular plaquettes. Because of hermiticity, one can check immediately that the sum of the fluxes is 0. And because the sum of the fluxes is 0, this leaves only 3 independent fluxes. So out of the 6 possible theta jk's, only 3 are independent. So for a given flux structure, we have a manifold of equivalent Hamiltonians corresponding to the 3 independent thetas, which are defined mod 2 pi. So each one corresponds to an S1, and we have a manifold S1 times S1 times S1 of gauge equivalent Hamiltonians, all giving the same flux structure. And they are gauge equivalent. They are measurably identical. We can get one from the other by simply changing locally the phase of the states. So what it implies for physical implementation, this high connectivity of the omega circulant Hamiltonian that allows us to define this this gauge structure on the 4-level system, and this flux structure is that corresponding to a flux structure, we get an entire manifold, a very large manifold of equivalent Hamiltonians. So, and they're gauge equivalent, so measurably identical. So we have this kind of deeper level of symmetry, which is not so much the omega circulant symmetry itself, but the flux structure. The omega circulant Hamiltonian is one realization of it, but we have an entire manifold realizing the same flux structure. So we get a lot of freedom for the realization of the flux structure. So implementing the symmetry is not something difficult if the symmetry we are trying to implement is the flux structure and not omega circulant symmetry itself. And this flux structure could be implemented with the techniques of artificial gauge fields. For instance, in this reference, they use lattice shaking to start from a Hamiltonian that looks exactly like our off-mode Hamiltonian. They add to it a periodic perturbation, driving these functions vi of t. And looking at the system at stroboscopic time, we get an effective time-independent Hamiltonian that has just the right form to have, for instance, omega circulant matrices. The couplings are now complex and the effective self-energies are equal. So in particular, this could be an omega circulant matrix, or for that matter, a matrix in that large manifold giving the required flux structure. I won't spend too much time on this, but just to mention that the flux structure of the two Hamiltonians, Hx and Hy, that we have used to generate our universal set are different. They have different flux structures, so they are not gauge equivalent. They are measurably different, which is as expected, because each one of them separately is not able to perform universal computation, but if we put them in combination, they are able to perform universal computation. So they somehow don't have the same physical content. And this is reflected in their having different flux structures. Now that I have talked about clusters in isolation, I'll now couple them to the environment to have a more realistic picture, to have the possibility of initializing, reading out the cluster, and also, so I'll discuss cluster interactions later. So for now, we have these semi-identical, semi-infinite leads. A lead is connecting to each level of the cluster, and we require them to be identical. So this is a strict requirement on the system that we're asking in order to preserve omega circulation. So attaching the leads and performing Fishback projector method calculation, we can move from the energy levels of the cluster in isolation to effective levels of the cluster in the presence of the leads. And this is essentially the same thing as tracing out. It's analogous to tracing out external degrees of freedom. But the effective energies that we get by tracing out the leads or using the Fishback method are complex in general. So you see the analytic expression here. The effective energy of mode K depends on Tc, the coupling to the lead, and to lambda K, the bare energy of mode K. But it doesn't depend on the energy of the other modes. So these modes are completely independent because omega circulation is maintained by the identical leads. So lambda K effective, the energy of the kth mode, is in general complex. When it is real, the system is non-dissipating. It is real only when the magnitude of lambda K is large enough. Intuitively, when lambda K is outside the bandwidth of the leads. And because the lambda Ks are completely independent, remember that an omega circulant Hamiltonian has eigenenergies in one-to-one correspondence with points in R4. So we have complete control over the four lambda Ks, lambda 1, 2, 3, and 4. Because of this independent control, we can control the dynamical coupling or decoupling of each eigenmode by tuning lambda K so that lambda K effective be real or complex, depending on what we require for preserving the state of the cluster or sending it through the lead for readout, for instance. So the cluster can be used as a memory unit with a real effective energy. So let me just explain what these graphs are first. So this is an exact calculation of an eigenstate for the system where at position 0 we have one cluster, at position 11 we have a second cluster, and we have a lead of length 10 in between. So for a real effective energy, this is one bound state of mode K, an exact bound state of mode K, and this is the other one. We have two bound states, and they are almost degenerate. The energy separation is quite small. And this implies that we will have slow dissipation if the state is initially well localized on one of the clusters, for instance. Then the state will be a combination of these two bound states. And it will oscillate with time at a rate which is proportional to this energy splitting, very small, a very small rate, so slow dissipation. Whereas when effective energies are complex, these bound states now become scattering states. The two states that we have below correspond to the bound states that have now become scattering states. And in addition to that, we have the continuous spectrum of the leads. But we don't have bound states anymore. We only have scattering states. So in this situation, if the state is the wave function is well localized on one of the clusters, then this wave function will be a combination. The state will be a combination of a large number of scattering states and will dissipate fast. And moreover, the energy splitting between these two scattering states is now much larger than what it was previously. So we have now a fast dissipation. Because we can dynamically decouple clusters from the leads, we can also perform our logical operations in an ideal way, even in the presence of leads. For a logical operation within one of the classes, either X or Y, because the eigenbasis of this class is independent of the parameters, G, when we evolve the parameter to perform the gate, we can see that the gate is actually a function of the time average of the parameter only, not of the details. It acts like an integrator. And it's fairly easy to see that to realize an ideal gate in the presence of leads, one simply has to push the lambda k's off the bandwidth of the leads by rescaling G and time, for instance. So because the leads have this finite width and we have a lot of control on the energies, we can do that. Now that I have considered the operations within the cluster and in the presence of an environment in a more or less realistic situation, I will talk about the possibility of having a large-scale computation, a large-scale architecture, where, of course, clusters need to communicate with one another. So there are many ways that one could think of doing this. For instance, if the cluster is thought of as a Q-quart, then one could think about an interaction between the Q-quart in one cluster and the Q-quart in another cluster. Since I've been thinking of the cluster as two coupled qubits, I'll continue to think of it that way, and I'll discuss a way to perform cluster communication by picking one qubit from one cluster and entangling it with one qubit of another cluster. But to do that, we need to physically realize the splitting of the qubits. Up to now, the two qubits were merely labels to label the four states of the cluster. But now we need to physically separate it to have one qubit in one cluster interacting with one qubit in another cluster. And we do that in the off mode, as I said earlier. So the off mode is where calculation is not occurring within the cluster. So the cluster is either just waiting or interacting with another cluster. So now we're in an effective off mode where the self energies have been modified by the presence of leads, which, by the way, were chosen because they are realistic in many solid state based situations where leads are the main source of decoherence. For instance, for superconducting qubits and semiconductor quantum dots. So they are a physically a reasonable source of decoherence. So now with these leads, the off mode has shifted self-energies, effective self-energies. And if one is able to adjust these energies in order to have a diagram like this where energy differences come pairwise, so between 0, 0 and 1, 0, we have an energy difference h bar omega 1, h bar nu 1, and we also have h bar nu 1 between 0, 1 and 1, 1. And similarly here, h bar nu 2 and h bar nu 2. With these energy differences coming pairwise, we have the following. If the system is coupled to something else at that frequency mu 1, then we see that the state of the cluster is oscillating between these two states. 0, 0 and 0, 1 are oscillating at frequency mu 1 from one another, and 0, 1 and 1, 1 similarly. So if we look at this, we see that it's just an oscillation of the first qubit, the second qubit being untouched. So we have performed the physical separation of the qubit in a sense, which was just a label until now. And similarly, if we now couple the cluster to something else, tune it into resonance at frequency nu 2, we have this oscillation between 0, 0 and 1, 0, 0, 0 and 0, 1, 1, 0 and 1, 1, which is effectively a second qubit oscillation, with the first qubit being unchanged, unaffected. So if we have mutually resonant clusters coupled at frequency nu 1 or nu 2, we have this single qubit interaction between the clusters. And this single qubit interaction through a far detuned resonator, for instance, is known to generate an entangling gate, the I-swap gate. So because operations within the clusters are universal, and now we have entangling operations between them, we have an overall universal architecture. So we can think of, say, an array of clusters where in blue we have these clusters, 4-level clusters. In green are the resonators, and here qubit 1 of first cluster is in an entangling operation with qubit 2 of the second cluster at frequency nu 1. 3 and 4 are being entangled at frequency nu 2, so on and so forth. The more frequencies you have, the better, because you avoid crosstalks. So here I have an artistic representation of a 36, a grid of 36 clusters that would be universal on 72 qubits. So let me briefly discuss generalizations, possible generalizations of this abstract scheme that I've been discussing. We have used 4-level clusters, omega circulant clusters, but it's fairly obvious to generalize it to n-level omega circulant clusters with the generalized n by n Pauli matrices x, y, and z. These have all the nice features I have discussed. They are all diagonalized by the same. They all have a common eigenbasis. So all matrices generated by X, class X matrices have the same eigenbasis. Class Y matrices have a common eigenbasis, and so on. Their energies are in one-to-one correspondence with the points in Rn, so on and so forth. Especially interesting is p-level circulant clusters, where p is a prime number. So generalized Pauli matrices of dimension p times p with prime p, because that allows for full state tomography. Because when p is prime, these matrices allow for the creation of the maximal possible number of mutually unbiased bases, which allows for full state tomography. And that could be of use in higher level, higher alphabet communications. And another generalization, possible generalization, is the consideration of other high connectivity symmetries. So I have mentioned that because the omega circulant Hamiltonian is highly connected, because all states are connected to one another, we have this this U1 gauge potential, U1 representation of the Hamiltonian, and because of that, we have a large manifold of gauge equivalent Hamiltonians breaking the omega circulant symmetry. So if we're willing to break this symmetry, we have this large manifold of Hamiltonians that are no longer necessarily omega circulant, but that have the same flux structure, which is what is physically relevant. They're all gauge equivalent, measurably identical. And this symmetry that seemed to be very restrictive is in fact not so restrictive if the symmetry you are looking for is the flux structure corresponding to that large manifold of Hamiltonians realizing it. These are the references that were placed in the text. And this is the preprint where most of what I've said is written out in details. It's available in archive and now submitted to PhysRev A.
Thank you very much.
Thank you.
Christian, a very interesting talk.
Thank you.
I invite questions at this point. Maybe I shall start, Christian, by asking you if what is the V and W, correct? That's what you call the universal set that you had.
Yes.
What would be the Cartan form of such a of V and W?
The what? I'm sorry.
The Cartan form, so that we can kind of separate out the local and the non-local content of it. Because there is the standard 2-qubit unitary matrices. The Cartan form gives you the simplest non-local form with only 3 parameters. So, I mean, we could place, for example, C0 has a very special place in this thing. So I'm wondering where the V and W are in this space.
To be honest, I don't know. I don't know this Catan form. I'll definitely look it out, and yes.
Because that's yeah. So that would give us a decomposition in terms of known gates, where they are in terms of or standard gates.
Yeah, that would be very interesting to know. Yes.
Thanks. Maybe I revert back to the others for questions or comments. Okay, I come back then. Is there some reason why only, I mean, identity and Y are sufficient, whereas you have to go to X square when you're defining these HX and HY?
Any reason why I would not have Y squared here, for instance?
Yeah.
Yes, there's a reason. So I went over that slide very, very quickly, but the reason is written out in that slide actually.
It's
so
and is only Y and Y cube.
I'm sorry?
Yeah. No, please go on.
Okay. So this is the flux structure of any Hamiltonian in the span of j omega and j omega cubed, where omega could be 1 for class X or I for class Y. And this is the flux structure for the span of j omega squared. So the k here depends on omega. Omega is e to the I k pi over 2. So for class X, k is 0, and this is just not there. But for class Y, all the fluxes here have value minus pi over 2. And combining these, we see that there's no way that these two flux structures combined together will have this form here for a shifted theta. So this form alone is the form that span x cubed has. In fact, span x squared x cubed, because for x this is 0 as well. But if I add this kind of topological term that depends only on the class, there's no way I can make it look like this by redefining theta. So they really have different flux structures. So span x squared and x3 is different from y3. But now if I add y squared, if I add pi here, I can redefine the thetas so that it looks precisely like this. So the conclusion is that the span of y squared, y cubed is the same as the span of x squared, x cubed. But not if y squared is missing. And so if I go back to the Hamiltonians, here I have x squared and the Hermitian conjugate, so I have x cubed as well. But here y squared is missing, so these are really these correspond to non-equivalent fluxes.
Yes, thank you. Other questions or comments, please? Does not seem to be the case, Christian. Thank you very much for a very interesting talk. I think this is very novel. Yeah. Thank you very much. On behalf of the others, unfortunately, our format is such that we have only this limited degree of freedom. Thank you so much for joining us from Canada today.
Thank you.
Thanks. So I hand it over to the organizers.
Thank you, Professor Arul Lakshminayan, for chairing this session and for your time, and all the speakers of the day for their interesting talks. And with this, we come to the end of our day 5th, and we will meet tomorrow, last day of the conference, tomorrow at 10:55 hours IST. Thank you all.